Hello, hi, namaskar everyone. My name is Deependra and I welcome you all in this one short video of sets, relations and functions. Sets and relations and function when clubbed together, last year only JEE Mains has asked 40 questions cumulatively from these two chapters, approximately. I hope you are able to understand how crucial this chapter it is. We'll cover everything related to this chapter, all the theory, all the concepts, all the formulae, everything, and we'll consolidate all these learnings with previous year's questions. This one shot which is provided to you at absolutely free of cost. Along with this, we are also giving you the free of cost short notes, the handwritten notes along with the DPPs. This is also provided to you at no cost. You can access this at our PW app, link to which is already given in the description. You can click on it and access this. PW app is an amazing platform from where millions of students are already preparing for different competitive exams and getting the desired results. With that, without any delay, let's get started. So this is all what we'll be covering in this particular chapter. We'll begin with the different properties, that what kind of relations are there, what kind of sets are there, and what kind of operations can be done on them. How do you understand them with the help of Venn diagrams? But what are different properties, what kind of different relations are there, symmetric, transitive, equivalence, and all of that, because this is the portion from where maximum number of questions are asked from sets and relations. Along with this, yes, when we move to functions, we start discussing how to find domains. The first or the second highest topic from this particular chapter will be domain and range based questions. And of course, we'll talk about the different types of mappings of functions. How does it happen? And then we'll move to different odd and even functions, its properties. We'll talk about periodicity. We'll talk about composite functions as well, how to find the inverse of a function. And the third most important topic from this chapter will appear, which is called functional equation. So if I were to highlight the three most important chunks from these chapters, they'll be simply these. Of course, questions based on functions being equivalence, transitive, symmetric, reflexive and all. Then questions based on domain and range. And then questions based on functional equations. So these are some more important topics where you should put your focus upon. So let's get started, start discussing everything in detail and consolidate them with a lot of examples, illustrations and previous year's questions. First of all, let us understand what is a set. So set is basically a well-defined collection of distinct objects. Mind you, distinct objects. So usually we denote them by capital letters. If I were to make you understand, for example, let's say I am taking a set of all the complex numbers. So if I'm collecting all the complex numbers, which are of course infinite in number, but if I am making that collection, that is a set. If I take the set of all the vowels in the English alphabet, that is a set. So this is how you define a set, a collection of distinct objects. Here, usually we denote the elements of the set by small letters, and here we write the label, we label or we name the set as a capital letter. For example, there is a capital A set here. Now this set A contains any number of elements. For example, 1, 2, 3 are its elements. So this is a set A defined with the help of these three elements, something like that. Here you need to understand that if this is a sign written over here, so this sign reads as belongs to. So if I'm writing X belongs to A, it means X is an element of the set A. I hope you remember that. Now, if X is not an element of A, then I'll write X does not belong to A. I'll read it as that X is not an element of A. So here we can very clearly see that set A is defined as 1, 2, 3, 4, 5. So I can say that 3 belongs to A because 3 is there in the set A, but 6 does not belong to A because 6 is not present in the set A. Now, to define a set, we have two methods. We follow two conventions. What are those methods? First method is tabulation method, or it is called roster form, or some people call it enumeration method. It's a very standard format of defining sets where you simply write the elements. For example, if I'm defining a set A, which is set of prime numbers less than 10. So the prime numbers which are less than 10 are 2, 3, 5, 7. So I have enumerated those numbers 2, 3, 5, 7 and I have written them inside a curly bracket. So this is a way of representing the set in a roster form. Another form is called the set builder form. So set builder form says that if you are wanting to define a set, then you can define it through its properties or definition instead of giving it all the elements or instead of writing all the elements in it. For example, here, I am wanting to define a set A. So set A is the set of elements X such that X has the property P. So there could be a property P, that something like that it divides 4, or it is a multiple of 7, or it is a factor of 13, something like that. So here, how do we read it? Please understand this particular part. We read it as that set A is the set of all element X. So it will have X such that, so this line here is read as such that it fulfills the property P. So the set A contains X, all those X, such that it fulfills the property P. For example, all the even numbers less than 10, or all the odd numbers, something like that. Any property can be defined. So this is how you can define set in the set builder form. Now there are different types of sets. What are they? First of all, null set, or it is called empty set or void set. So if there is no element in a set, which is denoted by the Greek sign phi. So here such set is called or said to be a null set. For example, if I'm writing all x such that x is a natural number and x should lie between 4 and 5. So we know 4 and 5 are natural numbers, two consecutive natural numbers. There is no number which lie between 4 and 5. So I'll say this will be an empty set. This will be a void set. This will be a null set. It does not contain any element. I hope you're realizing that. Similarly, I could say that x, for all x, there is a set such that x belongs to a real number such that x square plus 1 is 0. We know for any real number, x square can never be minus 1. We know that. So yes, it also going to contain, no element phi, which is going to be again a void, an empty or a null set. I hope it makes complete sense. With that, let's move to the next category of set, which is called singleton set or a unit set. What does it mean? A singleton set means it should have only one element. For example, look at this. I am defining a set for which it contains all x such that x minus 3 is equal to 4. So when you solve this, you get x as 7 only. 4 plus 3 as 7. So it has only one element. So what is it? It is 7. So if a set contains only one element, it is called singleton or a unit set. I hope it is understandable. These terminologies are there. They are used in questions, so you should be aware of it. For example, if a question says that set B is a singleton set, then you should be able to crack that singleton means that this set should contain only and exactly one element. Now, what do I mean by subset? So how do we define subset? Every element of a set A is also an element of a set B. Then set A is called the subset of B. I hope you are understanding it. For example, there is a set A, there is a set B. Now set B has elements, let's say 1, 2, 3. And set A has elements 1 and 2. So as I can see that all the elements of set A are also the elements of set B, and that's where we say that set A is a subset of B. So with this sign, we read it as that set A is a subset of set B. I hope you can very clearly see that I can also say that set A is contained in B. So B has a subset which is set A, because set A's all the elements are the part of set B as well. I hope this part is understandable. So here we write that set A is a subset of B. It implies that all the x which are part of A implies that those x should also be part of B as well. This is exactly the meaning of a subset. So this is how we define it. What has started happening these days is that JEE has started using this set form very much in its questions. So JEE is using this standard set form, roster form or enumeration form, mostly this set definition form a lot in its questions. So questions on set theory may not be asked directly, but in any question, they can merge the concept of set theory and they ask you questions. So these simpler or light topics, for example, logarithm or these chapters are not directly asked, but the concepts of these chapters are used everywhere. That's what you need to remember or learn. So here, I hope you are getting it very clearly. How do we define subsets, as we have already discussed or looked at? Now, there comes another part which says total number of subsets. This is what we'll study in permutation and combination as well. This is what we have looked in the previous lecture as well, in the last video as well. So we had a discussion on this, how to find the number of subsets. For example, if there is a set A and it has elements 1, 2 and 3. So it can have a lot of subsets. For example, it can have 5 as a subset which contains only 1, only 2, only 3, or 1, 2, 2, 3, or 1, 3, or all 1, 2, 3. So the number of subsets are going to be 8. How? I could say that I will say that the number of subsets this set A is going to be contained will be 2 cube, and 2 cube will be given by 8. Now, how did I use this formula? We'll understand this in PNC. As of now, please understand 2 raised to the power number of elements are present in set A will be the number of subsets the set A contains. So 2 to the power 3, the number of elements in set A were 3. So it will have 2 to the power 3, 8 subsets. I hope you're getting it. The total number of distinct subsets the set A is going to contain will be 8. I hope this part makes complete sense. Let us move to the next part where we'll discuss equal sets. Now, what does it mean? Two sets, let's say I'm given A and B, and I want to claim that they are equal. I'll be able to say so that if every element of A is an element of B and every element of B is an element of A, which means if A and B are equal, then A should be a subset of B, B should be a subset of A, and it can happen only when all the elements of A are all the elements of B and all the elements of B are all the elements of A, vice versa. So if two sets contain same elements, then we said that these two sets are equal. For example, there is a set A which contains elements 1, 2, 3. There is another set B which also contains the same elements 1, 2, 3. Then what would I say? I'll unhesitatingly say that these two sets are equal. Did you get that part? I hope there is no confusion on that. Let's move to the next part. This is exactly what they are trying to give you here. Power set. Now, what does power set mean? Please understand, this is where the questions are found. They use a terminology that they give you a set and then they ask you the something related to the power set. So what does it mean? It says the set of all the subsets of a given set is said to be the power set of A. What does it mean? For example, here, let me take an example. Let's say there is a set A and this set A has two elements 1 and 2. So power set of A is first of all denoted by PA. So PA means that this is a set which contains all the subsets of this set A. So set A has how many elements? Set A has two elements 1 and 2. So how many subsets will it have? 2 to the power 2, number of elements 2 to the power number of elements 2. 2 to the power 2 is 4. So it will have 4 elements. Which 4 elements? 5. Then I'll have a subset 1. Then I'll have a subset 2. And then I'll have a subset 1, 2. So these are going to be the 4 subsets. So the set which contains all the subsets is going to be the power set of this set A, which is denoted by PA. I hope there is no confusion on this front. Let us move ahead. What is a superset? So when we say that A is a subset of B, can be written as that B is a superset of A. I hope you are understanding the relation. Let's say if I say A is a father of B, so vice versa, we can say that B is a son of A. So if I change the relationship, if I change the terminology, the relation still holds true. That same kind of thing can be said in this manner, that when you say that A is a subset of B, in that sense, we can say that B is a superset of A. So subset and superset, I hope that relationship is understood by you all. Now, let us move ahead towards the next thing, which is called proper set. Now, a set A is said to be a proper subset. So here it is proper subset, first of all. That is what you need to understand. Of set B, if every element of A is an element of B and B has at least one element which is not an element of A and is denoted by A, proper subset of B. So far, what were we saying? We were saying A could be a subset of B. So this line means equality. That means A could be equal to B. But if I say that A is a proper subset of B, it means that A could be a set somewhat like this and B could be a set somewhat like this, where I have ensured one thing, that here B has at least one element which was not there in A. So here I'll call A to be a proper subset of B. I hope you're able to distinguish these terms. These are some simple terms. We'll not be spending more time on them. But yes, to make you recall them, to make you learn them, to make you understand them, because they are used anywhere in this your JEE journey, in this JEE examination, in any question. So you should have these terminologies with yourself. So that's why we are revising all of these terminologies first of all. Similarly, we'll discuss finite and infinite sets. What does it mean? So a set in which the process of counting elements comes to an end is of course a finite. Otherwise, it is an infinite set. I hope I need not even explain this part. Here, if I say that I need to write a set of universities in India, so there are limited universities in India, they are countable, so I'll say finite. But when I say that set of all integers, so of course I'll say that all the integers are uncountable, there is no end to it, and that's why I'll call it an infinite set. I hope there is no confusion on it. Now comes another terminology which is called cardinal number of a finite set. So cardinal number means the number of distinct elements. For example, here in set A, if I look at the elements 1, 2, 3, 4, 5, 6. So there are 6 distinct elements in this set A. So cardinal number of set A, which is denoted by NA, is given by 6. Number of elements in this set A. That's the cardinal number of set A. I hope there is no confusion on it. Now there is another term which is called comparability of sets. So comparability means what? Two sets A and B are said to be comparable if either A is a subset of B or B is a subset of A, or A is equal to B. Otherwise, A and B are said to be incomparable. So if you're given two sets out of which one of them is the subset of the other or they are equal, then we can compare them. Otherwise, they cannot be compared. And when they are not compared, they cannot be compared, then we call them incomparable sets. I hope this part is also making complete sense here. Let us move towards the next part. What do we have in the next section? Universal set. So all the sets under consideration are likely to be the subset of a set is called the universal set. For example, here, let's say I am writing all the numbers. Let's say these are all the real numbers. These are all the real numbers. So this is a set which I'm denoting by R. Now, in the set of all the real numbers, let's say I've divided into two parts. Which two parts? Rational numbers and irrational numbers. So this is a set of rational numbers and this is a set of irrational numbers. Then of course I can delve further and divide it more into, but here I have certain number of sets. And of course, here, out of this real number set, I could divide into two categories, a set of rational numbers and the other set of irrational numbers. So, rational and irrational have a superset which is called a real number set. So, real number set is a universal set in this scenario for rational, irrational and all something like that. Again, you can divide rational into integral or something like that, natural and whole. And again, there is more category here, a category of subsets. But here, the universal set is basically under which we are considering all the other sets. So anything which we are going to discuss as a real number will fall under the category of real number. Irrational, rational, integer, natural, whole or anything like that. So yes, the superset, the universal set is going to be R here. I hope it makes complete sense here. Let us move ahead. Let us go ahead. Let us study the next concept which is called union of sets. Instead of understanding the definition, let's understand it here through an example. Here, let's say set A contains elements 1, 2, 3, 4. Set B contains 4, 5, 6. So A union B, which is denoted by this sign, will have the elements which are contained by A or the elements which are contained by B. So here, what you should understand is that B and A both contain this 4. So I should not be writing this 4 twice. So here, I'll be taking all the elements of A which are 1, 2, 3. I have taken them 1, 2, 3. I'll contain all the elements which are contained by B which are 5, 6. But I'll contain those elements as well which are contained by A and B both, which was 4. But of course, it should appear only once because in set, all the distinct entries are made. I hope it is understood by you all. You can take the union of 3 sets as well. This is how you can take the union of 3 sets. Here you need to understand that if I'm having n number of sets, and if I'm willing to take its union, then the way we use summation, the way we use these signs, union can also be taken. So let's say I'm taking union of A1, A2, A3, A4, A5, something like that. So it can be written as union of AI, where I is starting with 1 and approaching till n. So union of A1, union A2, union A3, union A4 until AN. That single expression also represents the same operation. I hope it makes complete sense. Now, Let us move ahead. Let us move towards the next concept, which is called intersection of sets. What does it mean? Intersection of sets means that you need to consider the common elements between these sets. For example, here, let's say I have two sets, set A and set B. An intersection sign is denoted by this sign. So A intersection B means that you need to look at the elements which are common to both. So A and B both have only one element common, which is 3. And when you take A intersection B intersection C, then you need to look at these element which is common to all three. So again, to A, B and C, if I take its intersection, then it is denoted by A intersection B intersection C, and there is only one element which is common to all three of them, which is 3. I hope this also makes complete sense. Here also the way we wrote union, intersection can also be denoted like this. Let's say I'm taking intersection of n sets. So that generalization looks like this, that you take A1, A2, A3, A4, intersection of all of them, where I is starting with 1 and then going till n. So it means A1 intersection A2 intersection A3 until intersection AN. Now there comes another category of sets which is called disjoint sets. What does it mean? If two sets A and B have no common element, that is their intersection is null, their intersection is void, their intersection is phi, then these two sets are called disjoint or mutually exclusive events or sets basically. What does it mean? Look at this set A, ABC. What about set B? It contains 1, 2, 3. So what is their intersection? There is nothing common between ABC and 1, 2, 3, and that's why I'll say that they contain no common elements. So A and B are disjoint sets. I hope you're able to get this part very clearly. Difference of sets. What does it mean? Let's have a look at this part. Difference of sets is denoted by minus sign. It means if A and B are two given sets, then set of all those elements of A, which do not belong to B is called difference of set A and set B. It is denoted by A minus B or A this sign by B or A upon B or CAB. Here what you need to understand is, let me take an example to make you understand this part more clearly. Let's say A has the elements 1, 2, 3, 4. B has the elements 4, 5, 6, 7, and I'm willing to write A minus B. So you write all the elements of B. But remove those elements of A which are common with B. So I have written the elements of A which are 1, 2, 3, 4, but 1, 2, 3, 4 has 4 which is common with B. So that element is removed. And that's how you write A minus B. And from here, you must be able to understand that union or intersection could be commutative, but difference is not commutative. So I hope you're realizing A minus B and B minus A will be different. Why? Because if I write B minus A here, through this example, if I were to write B minus A, what does it mean? It means I'll write all the elements of B. What are the elements of B? The elements of B are 4, 5, 6 and 7. But here, out of this, subtract or remove or eliminate the elements of A. What are they? The elements of A are, I hope you can see, the elements of A are 4, I think only. So I'll remove 4 from here. So B minus A will be 5, 6, 7. And I hope you can see A minus B and B minus A are not same. So these are the properties where you need to understand. B minus A minus B and A intersection B are going to be disjoint sets. I hope you can see here also. If I write this third set, which is going to be A intersection B, what would that be? That will be 4. Now if I look at these three sets, we all can see A minus B have nothing in common with these two sets. Similarly, B minus has nothing common with the other two sets, and A intersection B does not have anything common with these two sets. So these three sets, when pairwise two sets are taken, are disjoint. They have nothing common between them. Remember this as a fact. Also remember this as a fact that A minus B will always be a subset of A, because we have removed the elements of B which were of A which were common with B. So I'll still be left with elements of set A only. So that will be a subset of A. Similarly, B minus A will be a subset of B only. I hope you can logically understand it. A minus phi will be A and A minus A will be phi, because if from A I'm subtracting null, I'll be getting A. But from A, if I'm subtracting A, all the elements of A, then I'll be left with nothing, which is void. I hope this is also completely understandable. Now there comes another important term on which questions are formed and framed. What is it? Symmetric difference of two sets. So here, when we are trying to understand this term symmetric difference, which is denoted by A delta B or in some books it is written as, at some places it is written as A, this sign B. What does it mean? It means A minus B union B minus A. A minus B union B minus A, or A intersection B minus A union B. Sorry, A union B minus A intersection B. Instead of this definition, I'll request you to remember this as a definition. This will be more useful. How? Let's take an example and understand it more clearly. I'll take an example here. Set A has elements 1, 2, 3, 4, 5. Set B has elements 1, 3, 5, 7. Can you help me with A minus B? It's very easy for us to figure out what is A minus B. A minus B will be all the elements of A except for the elements which are common with B. So A and B have some elements common, which are, I think, 3 and 5, because 3 and 5 are the elements which are there in both A and B both. So from A, if I remove 3 and 5, I'll be left with A minus B, which is basically 1, 2, 4. I think it should have been 1, 2, 4. Or maybe it did not have this. So there is a typing error, I believe. So let me just correct it here. There was no 1 here. So this started with 2 only. All right. So 2, 3, 4, 5 are the elements of A. 1, 3, 5, 7 are the elements of B. And 3 and 5 are common between A and B. That is the intersection of A and B. Now, if I were to tell you that, can you write A minus B? You will say from set A, remove 3 and 5. So I'm left with 2 and 4, which is A minus B. What is B minus A? From B, remove 3 and 5, which is common with A. So we'll be left with 1 and 7. Again, it is writing 7 only, which means there was no 1 here. So again, there is this error. Let me correct this here. This 1 is not here. Okay. So this is 3, 5, 7 only. Set B has 3, 5, 7 only, which means B minus A will be 7, because 3 and 5 are common with A. Now, what you do next is that A minus B and B minus A, you take the union of it. You take the union of A minus B with B minus A. What is it? It is going to be 2, 4 and 7. So this 2, 4, 7 is called the symmetric. It is called the symmetric difference of set A and B. Please remember this. So what is the symmetric difference of A and B? A minus B union B minus A. I hope you will remember it. Let us move ahead towards the next part, which is called complement set. So to understand the complement, you need to understand that universal set comes into picture and plays a crucial role. So let's say there is a set U and it is the universal set. And there is a set A, which is the subset of U. So the set which is complement of A with respect to U is denoted by A dash or AC or CA, or it basically contains all those elements which are there in universal but not in A. What does it mean? If I were to simply make you understand it through this simple standard example, let's say this is a universal set of all the real numbers. So this is a universal set of all the real numbers. From this universal set, if I take the numbers which are rational numbers, so this is a set Q which represents all the rational numbers. So from the set of real numbers, if I could remove all the rational numbers, I'll be left with its complement which are not rational. So QC is a set which is real minus Q, which is irrational numbers set. I hope you are able to understand the meaning of complement set here. So of course, these are some properties which are understandable, self-explanatory. This is also something we have discussed. These are some properties based on cardinal number of subsets. What does it mean? Let's have a look at this part. So of course, if I were to ask you how many elements are there in A dash, how many elements are there in the complement of A, you will say, if I have number of elements in the universal set, and from that if I subtract the number of elements in set A, then I'll be left with the number of elements in the complement of A. Easily understandable. I need not explain this part. This is what you must have been studying. If you have forgotten it, let me rewrite it. A union B, the number of elements in A union B are always equal to number of elements in A plus number of elements B minus number of elements in A intersection B. How do you understand this? Let's say this is a universal set and it contains two smaller sets, which are set A and of course set B. So these are the two sets, set A and set B. Let's say set A and set B have certain elements. So X number of elements are there in set A only, Y number of elements are there in set B only, and Z numbers of elements are there in set A and B both. This is the Venn diagram representation of set A and B. And set A and B belong to a universal set U, which does not play any crucial role here. Now, When you write the number of elements in set A, what does it mean? So number of elements in set A means x plus z. So here I'm writing x plus z plus number of elements in set B. What does it mean? It means y plus z. So it gives you y plus z. And from this, if you're subtracting A intersection B, so what is A intersection B? That is Z. So from here, if you are subtracting Z, let's say this Z cancels this Z. So finally, you're left with X plus Y plus Z. Finally, you're left with X plus Y plus Z, which is A union B. Why? Because A union B is this. A union B is this, which is nothing but what? X plus Y plus Z. So I hope this formula is very much understandable and completely it should be remembered by you all. That's what I'm saying here. Now, here you need to understand that if A and B are disjoint sets, are two non-void sets which are disjoint sets. Disjoint means what? They have nothing in common. Then I can say that A union B will be equal to NA plus NB. I hope I need not explain this part. Here you need to understand that A intersection B complement will be number of elements in A minus number of elements in A union B. What does it mean? Let me try and make you understand through Venn diagram. So through Venn diagram, if I could explain it, let's say this is a universal set and there in the universal set you have a set A. So in that universal set you have a set A. Now there you have another set. Let's take another set as set B here. So that is another set. Let me write it here and that's your set B. So this is set A here and that's your set B here. Now what are we trying to find out here? We are trying to find out A intersection B dash. So if this is B, what will be B dash? I hope you can see it very clearly. This whole part, which is not there in B. So out of the universal set, all the other part, which is there in the universal, but not in B. So excluding B, all of this part will be B dash. Did you get this part completely and clearly? Now, I need B dash intersection with A. The intersection of A with B dash. So I hope you remember, if I look at A and B dash intersection, do you not think it will be this only? Because B dash is everywhere except for the portion where B is. And if I take its intersection with A, it will be this part only, which is A only. Did you get this part? So from here, I hope there is no confusion here. There is no confusion here. A intersection B dash. So this is A, right? And this whole is A basically, but B dash was this entire expression over here. And if I take the intersection of A with B dash, this is what I'll be getting. I hope I need not explain this part. Did you get this part? So what I'll say here is that out of A, if I could remove the part which is contained by A intersection B, then I'll get A intersection B dash. So there is a small correction over here, which means here instead of this sign, this union sign, it should have been intersection. So I hope you are able to understand it completely that here it should be A intersection B. Why? Because if out of A, if I could remove A intersection B, I'll get A intersection B dash. I hope it was easy. Similarly, these results can also be proved. I'll simply ask you to take a screenshot of it and you can prove all these results through Venn diagram as well, which is not going to be a huge task. I hope you can see, you can create them, you can build them and you can see them through Venn diagram. I hope this is self-explanatory and it all can be proved. But what we have discussed so far were more important ones and they should be remembered. There comes this another formula which is called principle of inclusion and exclusion as well. This can be generalized for n number of sets as well. What does it mean? Let's start discussing it. Let's first of all learn its generalization for three sets. Let's say there are three sets A, B and C. I'll draw it so that you understand it more clearly. So imagine there is a universal set or there are three sets, let's say set A, set B and the third set C. So these are the three sets basically, right? So this is set A, this is set B and this here is set C. So set A, set B, set C have certain number of elements. Let's say the number of elements in set A only are A, the number of elements in set B only are B, the number of elements in set C are C only. The number of elements in set A and B but not in C are D, let's say. The number of elements in set B and C but not in A are, let's say, E. The number of elements in set A and C but not in B are F, let's say. And the number of elements which are there in A and B and C are G. I hope you are able to digest this whole part very clearly. Right. Now, If I start writing these things, what do I get here? A in union B union C. What does it mean? It means I should get A plus B plus C plus D plus E plus F plus G. So if I get all these entries, that will represent A union B union C. Let us let us explore the right hand side. So what is set A? So set A means this NA meant A, D, G, F. What is B? It meant B, D, G, E. What is C? C meant C, E, F, G. So I hope you're realizing I have already started receiving things twice or thrice. This D has appeared twice because it was there in A, it was there in B. This E has also appeared twice because it was there in B and C both. This F has appeared twice because this was available in A as well as C. So when I'm writing these, they have already appeared twice. Not just that, this G has appeared thrice because when I wrote NA, this G was there. In NB also this G was there. In NC also this G was there. So to get rid of this, what I'm doing is I'm subtracting A intersection B, B intersection C and C intersection A. So what is A intersection B? A intersection B is going to be D and G. B intersection C is going to be G and E. And A intersection C is going to be F and G. So I had D, E and F twice, out of which one D, E and F are removed. I am left with one D, E and F only. So A, B, C, D, E, F is sorted. But during this process, when I subtracted them thrice, I removed the G totally because G got included because of these three thrice. And when I subtracted them, the G got eliminated. So I got 3G from here and I got 3G eliminated from here. So I have no G here. But when I'm taking the A union B union C, I should have one G. So to have that, I am adding A intersection B intersection C. So when you add A intersection B intersection C, you get this G. Did you understand this whole part? I hope it is perfectly understandable. It is completely making a great sense that how does this formula come into picture and how should you remember it as a principle of inclusion and exclusion. So how do you do it? Let's say I had 4 sets. So first of all, I'll take the sum of them individually. Then I'll subtract the intersection of them, taken 2 at a time. Then I'll add the intersection of them, taken 3 at a time. Then again I'll subtract the intersection of them, taken 4 at a time. So this is how you keep on adding, subtracting alternatively, and that is what is called the principle of inclusion and exclusion. So inclusion, then exclusion. But in that exclusion, we excluded a lot of things which are supposed to be included, so we included. So this keeps on happening. Inclusion, exclusion, inclusion, exclusion. And this is why it is called principle of inclusion and exclusion. I hope this is how you can represent a subset. So if this is set B, the subset of set B is denoted by A because A will have all of its elements as part of B. This is the union. So if I'm writing A union B, so all the elements of A and all the elements of B both are written. That is A union B. But of course, if it is disjoint, then its intersection will be 5 because there is nothing common between them. But here, if I'm writing A union B, it will be A union B. And what about A intersection B? This section over here is representing A intersection B. Here we can clearly see that A is neither a subset of B nor B is a subset of A. I need not explain this. Why? Because in that case, the set should be contained by the other set completely. That is not happening over here. Here, this is the case of subset. Here, this is the case of intersection. Here, there is nothing common between A and B, and that's why their intersection will be 5. But of course, between A and B, there is something common. So I'll denote this shaded region by A intersection B. That is the Venn diagram representation of sets. Now moving ahead towards the next case, difference of sets. As we have already understood, what is A minus B? A minus B means all the elements of set A excluding the elements which are contained in B. So this shaded region which was there, not this one which I have drawn over here, the shaded region, this one is A minus B. Similarly, if I say A minus B here, so nothing of A is common with B, so complete A will be there. I hope you are understanding it very clearly. Any confusions on that? Let us move ahead. Let us move towards the next property, complement. So this is your universal set and this is set A. So all the part in the universal set A, in the universal set U, except for A will be A complement. So the shaded region will be denoted by A dash. So this shaded region is A dash or AC. I hope there is no confusion on that. This is representing, for example, if I'm denoting A union B union C. So what is A union B union C? I hope you're getting it. So if I'm denoting B union C, so this will be B union C, which contains some part of A as well. Why? Because that was part of B and C both as well, B or C as well. But if I'm taking A union B union C, so this is what representing A union B union C. We have seen a formula on it, so I need not explain this Venn diagram at this stage at least. These are some different Venn diagrams representing union, intersection and other cases which are, I believe, self-explanatory, and you should be able to understand them by looking at this part only. For example, here, if I were to figure out A intersection B intersection C, what does it mean? See, here this is representing B intersection C. So B intersection C is this part. But out of this, if I take its intersection with A, it will be this only. So this region is representing A intersection B intersection C. Moving ahead, these are some different properties, associativeness, commutativeness. These are all true, but yes, there is this distributive law which you should remember because it gets changed. This is something I would ask you to remember as a result. Please understand this result that A union of whole of B intersection C is A union B intersection A union C. You can prove it through Venn diagrams. I'm just giving you the result directly. I'm leaving it up to you that you can draw the Venn diagrams of A, B and C. You can draw the LHS, create the shaded region, and then you create the RHS, and you'll see same will turn up through the shaded region, no matter wherever you draw A, B and C in that universal set. The same will be true if A intersection of whole of B union C is needed to be taken. In that case also you say A intersection B union A intersection C. This can also be proved through Venn diagrams theory. I hope it's understandable. Moving ahead, these are the proofs right there in front of you, which need not be proved at this stage in this one shot. So I'll straight away move to the next part, which is called symmetric difference. This is what you need to remember. I hope you remember it very clearly. Symmetric difference is usually denoted by A delta B. And we had a discussion on it that A delta B is nothing but what? A minus B union B minus A. So what if I were to ask you A minus B? So in this case, A minus B will be A only. Union B minus A. B minus A will be B only. So this is B only and this is A only. So if I take their union, basically I'm subtracting A intersection B. So here in this case, in this particular case, for this particular case only, I can write the symmetric difference of A and B as the I hope elimination of A intersection B from A union B. So if I'm removing A intersection B from A union B, then also I'm getting the symmetric difference of A and B. I hope you're able to get this part very clearly here. So with the help of these figures, you can remember a lot of results. I am not asking you to remember them. I am asking you to understand them logically. So you know what is a complement, you know what is a set, and you can draw these shaded regions with the help of Venn diagrams. So all of these cases are not supposed to be remembered or memorized at all. No, you need to understand them logically and you can prove whatever is asked. You can create whatever result is needed to be brought into picture. Set theory has this concept that you can use these formulae on cardinal numbers, and that's exactly what they have done in JEE Mains 2024, and they had asked you a question on it. So let's look at a question on it and understand it and see what can be done through or on this particular question. So let's read it first. What does it say? It says that there are 220 students. Okay. It was found that at least, so instead of given an exact word, they are saying at least 125 and at most 130 are studying mathematics. Okay, so let me write this data here. What are we told? That there are total 220 students. Okay, so this is the data which says total 220 students. What about the data for maths? For maths, we are told that mathematics has at least 125 students and at most 130 students. So maths has students somewhere between 125 and 130. Okay, that's great. At least 85 and at most 95 are studying physics. So for physics, the data says that minimum 85 are there. I hope there is no confusion on it. And maximum 95 are there. Now, I think there should be chemistry next. Chemistry has, let me read it, 75 and 90. So the range of chemistry is said to be the minimum number of students chemistry can have 75 and the maximum number of students can be there in chemistry would be 90. I hope the data is very well understood by you all. Moving ahead, what is next? What is next? The next data is 30 students study both physics and chemistry. I hope this line is completely understandable. So when you take intersection of physics and chemistry, it will give you 30. I hope you're getting it. There is another data, 50 students are studying chemistry and maths. So if I'm taking intersection of chemistry and maths, it will be 50. And the next data, 40 students are studying both maths and physics. So there are 40 students who are taking the intersection of maths and physics. Mind you everyone, the last data, 10 students study none of these subjects. So out of 220, only 210 are divided among physics, chemistry and maths. 10 are belonging to none. Physics, chemistry and maths. I hope you're getting it. And then they're asking you MN and respectively be the least and the most number of students who study all the three subjects, then M plus N is equal to. That we'll discuss later. But let's start working on this formula. What is the formula we know? Sir, we know a formula that if you are wanting to write this formula here, which is saying cardinal number of physics, union maths, union chemistry. Right? Usually PCM is what you do. So I'll write it like this only. Physics, union chemistry, union maths. You keep maths at the least priority, right? Okay, so this formula is given by number of elements in physics plus number of elements in chemistry plus number of elements in maths minus number of elements in physics and chemistry minus number of elements in chemistry and maths minus number of elements in physics and chemistry, chemistry and maths, which means maths and chemistry. Oh, sorry, maths and physics. So physics and maths. But yes, inclusion, exclusion, then inclusion needs to be done. So number of elements in physics and chemistry and maths. I hope there is no doubt or confusion on this part. Now, let us work on this data. How many students were there? Sir, there were total 220 students. So should I say that this union should be 220? No, that will be false. Why? Because out of these 220, there were 10 students who did not study any of these subjects. So out of 220, 10 students are already eliminated. So I need to divide these 210 students, 220 minus 10. So here, this union is going to be 220 minus 10, which is 210. Did you get this part? Now, let us move towards this part. Number of P, number of C, number of maths. I'll talk about this later. So NP plus NC plus NM, because this is given to me in an inequality format. So this is what I'll deal with later. Right? Now, let us move to this part. 30 are for both physics and chemistry, 50 for both chemistry and maths, and 40 studying both maths and physics. So 30, 50 and 40. So this data, although may not be in correct order, 30, 50 and 40 will be there. So I'll be subtracting 30, 50 and 40. I hope there is no confusion on it. 30, 50 and 40. Is it understood by you all? 30, 50 and 40. Great. Now we are left with the number of elements who are studying all three, which is physics as well as chemistry as well as maths. I hope it is understandable. Now let us take this data here from here. Which data, students? 30, 50, 40 and this data. So if I am taking this data, so 30 plus 50 is basically 80 and 80 plus 40 is 120. If I'm adding 120 to 2110, so 2110 plus 120, let me not make any mistakes. So it is going to be 330. So it is going to be 330. So if I'm taking all of that here, so it is going to be 330 minus number of elements are there in P intersection C intersection M, which is equal to number of elements in P plus number of elements in C plus number of elements in M. Any confusion so far? Did you understand this whole data, whole expression very clearly, students? I hope there is no doubt so far. Now, let us talk about this data here. Let us talk about this data here. Then we'll come to our conclusion. What do I mean by that? I am coming to that part. Here in this question, inequality has come into picture. How? Let's look at that. What is NP? So number of elements in physics are basically 85 to 95. What is NC? 75 to 90. And what is NM? Number of elements in the set M, that is 125 to 130. So if I were to ask you number of elements in physics plus number of elements in chemistry plus number of elements in maths, you would say, sir, in inequalities, we can add 2 or 3 inequalities together. which will imply that the sum of their least value will be the least value of their sum, and the sum of their maximum value will be the maximum value of their sum. So 125 plus 85 plus 75 will be the least value. So 125 plus 85 plus the next is 75. This will be the least value of their sum, number of elements in physics or chemistry or maths, something like that. Number of elements in physics plus number of elements in chemistry plus number of elements in maths. The maximum value will be 130 plus the next element is 95 and the next element here is 90. I hope there is no confusion on it. Now, moving ahead, can we calculate it a little further and get more clarity on it? So number of elements in physics plus number of elements in chemistry plus number of elements in maths are going to be the minimum. Minimum is going to be basically 125 plus 75. I think it is going to be 200. So 285 is going to be the minimum value. I hope there is no doubt on it. Similarly here, if I calculate this, so 130 plus 90. So 130 plus 100 would have been 230, but it is 90, so it should be 220. 220 plus 95. So 220 plus 100 will be 320, but this is 95. So 320 minus 5 is, I think, 315. Just check it one more time. It should be 315. Just check it one more time. 130 plus 200 basically is needed to be done. So 130 plus 200 would have been 330. But out of that, 15 is needed to be subtracted. That is 315. Perfect. Brilliant. Correct. Now, let me get back to this result. The right hand of this particular equation is not we are aware of, but we know its range. So the right hand side, this NP plus NC plus NM lies between 285 and 315. Then can I not say that this also is going to lie between that same range? So here I can say that 330 minus number of elements in P intersection M intersection C or P intersection C intersection M, whatever you wish to write, that doesn't matter here because this is also associative in nature. So this is going to be equal to this, which has a certain range, which is 285 to 315, which is 285 to 315. I hope there is no confusion on it. 285 to 315. Great, brilliant, perfect. Now, moving ahead, I am subtracting 330 from all the three sides. So 285 minus 330 is what I'm doing. This is negative of n of P intersection C intersection M, and 330 I'm subtracting from this side as well. So 315 minus 330 is what I'm doing next. Now what will I get here? 285 and 330. So 85 plus 15 is 300 plus 30. So I think it is minus 45. So this value over here is going to be minus 45, which is less than equal to negative of n of P intersection C intersection M, right? And this has its maximum value as 315 minus 330, which is going to be minus 15, which is going to be minus 15. I hope you remember, for an inequality, if I multiply it with a negative sign, its sign changes. So I'll have number of elements in physics as well as chemistry as well as maths are going to be 15 to 45. So if I'm changing the sign, I'll simply invert it. So I have gotten the minimum and the maximum value, which can be there in all three: physics, chemistry, and maths. It is going to be 15 and 45. So I think this small m is basically the minimum, which is 15. The maximum is the small n, which is 45. What are we asked? We are asked m plus n. So 15 plus 45 is clearly 60. So that's your correct answer. Did you get it? Any confusions on that? I hope most of you must have also gotten the same answer. I have tried keeping it very simple, straightforward, and of course it can be done through intuition as well. But if you are not good at applying intuition or logic more clearly, you can always rely on your formulae. So yes, the standard formula is there. You put all the values, you use the basics of inequality, and you can solve this particular question. Tell me in the comment box how many of you were able to do it correctly. How many of you were able to do it before me? How many of you have understood this particular concept very, 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 very clearly? If we have understood this, now let's move towards relation. So we are now going to discuss the Cartesian product of two sets. through which we'll talk about relations, and then after relations we'll move towards the next part, which will be functions. So from relations we'll gradually move towards function, but before functions or relations, let's understand Cartesian product here. Instead of discussing it through this definition, let's understand it through an example. So let me take an example so that I can make you understand what is the Cartesian product. So let's take a set here, two sets. Set A is there, which has, let's say, elements 1 and 2, and there is the other set, set B, which has, let's say, the elements A, B and C, right? So in a different world, if I could try and explain this thing to you, Cartesian product means that you make pairs. Let's say I'm writing A cross B, so this represents Cartesian product of A with B. Of course, A cross B will be different, B cross A will be different. But what is A cross B? Let us understand that first. So you take elements of A and you pair them with B, one after another, one by one. So I'll take one. So pairing of one when with A is done, it becomes 1 comma A. Then I pair one with B, this becomes 1 comma B. Then I pair one with C, it becomes 1 comma C. Similarly, the next element of A was 2. So I'll pair 2 with all the elements of B, that will be 2 comma A, 2 comma B and 2 comma C. So this is what you say or write or call to be A cross B, Cartesian of A with B. Cartesian product of B cross A would have been A comma 1, A comma 2, B comma 1, B comma 2, C comma 1, C comma 2. So I hope you're understanding what is the Cartesian product through this example only. So rather than giving you the complete definition, I'm just trying to give you a visual depiction as well. Let's say these are your sets, set A and set B. Set A had elements 1 and 2. Set B had elements A, B and C. So Cartesian product meant that I clubbed all the elements of A with B, A cross B. Means I paired A with 1 with A, then 1 with B, then 1 with C. Then I paired 2 with A, then 2 with B, then 2 with C. So this is called the Cartesian product, and this is how what I have written, where I have written the Cartesian product of A and B. And that's exactly what they're trying to define by this particular theoretical part, which I'm skipping. And I hope this complete illustration is helping you or making you understand the Cartesian product completely. What I'm trying to make you understand is that how do you understand a relation? So relation means that there is a non-empty set A to another set B. If you take any subset of A cross B, then this subset of A cross B could be a relation R, any relation. For example, let's say out of this A cross B, I'm taking any subset of A cross B. Let's say I'm defining a relation R1 here. I'm defining a relation R1 here. And what is in that R1? So in that R1, basically I'm taking a subset of A cross B. This is your whole A cross B, the complete exhaustive set. Out of this A cross B, let's say I have chosen 3 elements. Which 3? Let's say any 3 I have chosen. So this and this I'm choosing. Let's say these 3 elements I'm choosing. So which 3 I have chosen? I am taking 1 comma A. I am taking 1 comma A. And then after 1 comma A, the next entry I'm taking is, let's say, 2 comma B, and the next element I'm taking as 2 comma C. So this is a subset of A cross B, right? So if this is a subset of A cross B, this is called a relation R1 from A on B. How? Please understand that if I could plot this relation R1, then you had set A and set B. Set A had elements which 1 and 2. Set B had elements A, B and C. And if I'm applying this relation R1 from A to B, then what kind of mapping does it make or look or form like? So here, 1 was clubbed with A, 2 had been clubbed with B, and 2 was clubbed with C. So out of all these possibilities which we were able to bring with A cross B, if I took some of the possibilities, basically a subset, or even all, then this is called a relation from A to B. So relation is basically nothing but what? There is a set A, there is a set B. A and B have their Cartesian product A cross B. And if I took any subset, that will be a defined relation. So there can be multiple relations. How do you define those relations? That is also what we'll discuss. But basically, from A to B, if I were to define a relation, that this relation from A to B would be a subset of A cross B. This is how simple it is. There is no constraint on a relation, anything like that. This is how simply you make any relation from A to B. All you need to ensure is that this relation should be a subset of A cross B. Then it will be defined as a relation, let's say R1, from A to B. Did you get this part? Did you understand this part? Now, if this relation is understood by you all, I hope it makes complete sense whatever is written over here. That exactly is what I have tried explaining through this illustration. Now, let's say there is a set A and I'm taking A cross A. So if I take any subset from A cross A, then it will be said to be a relation on A. I hope it is also very much understandable that there is a set A which contains the elements, let's say 1 and 2. So what will A cross A look like? I hope there is no confusion on it. You have this set A and you are taking its Cartesian product with A only. So A has elements 1, 2. So 1 goes to 1, 1 goes to 2, 2 goes to 1 and 2 goes to 2. So you'll have 4 elements. I hope you are getting it very clearly. Now out of these 4 mappings, any number of mappings if I take, basically the subset of A cross A. So I hope you know that how does A cross A look like? A cross A looks like 1, 1, then of course 1, 2, then you had 2, 1, and then you had 2, 2. So these were the 4 elements in A cross A. If I take any subset of A cross A, then that will be called the relation R, any name you want to give it to, R, R1, R2, R3. So I'm defining a relation R on A. It means I need to take a subset of A cross A. So you can take any number of subsets. It depends on the number of elements present in A cross A. So there, if you take any subset, then that subset will be called a relation on A, basically. I hope you are understanding it. Now, if somebody asks you, how many relations can you make? Then you will say that the number of subsets we can make, because the subset is said to be a relation. So if you are asked to calculate the number of subsets of A cross A, which you know how, because here A cross A has 4 elements. So if A cross A has 4 elements, I'll say it will have 2 to the power 4 number of subsets. 2 to the power 4 means what? It will have 16 subsets. So if I were to ask you or give you a question that how many relations will exist on A, then you will say that, sir, A cross A, the Cartesian product had 4 elements. Which 4 elements? 1, 1, 1, 2, 2, 1, 2, 2. So out of these 4 elements, I could create 2 to the power 4. That means 16 subsets. So there are 16 relations possible on A. Did you get this part? Which kind of 16 relations? For example, I could create only one relation, which is 1 to 1, 1, 1. There could be other relation which could be 1, 2. There could be other relation which could be 2, 1. There could be other relation which could be 2, 2. Or I could take exactly 2 elements, which means I could have taken a relation which may have contained 1, 1, 1, 2. I could have taken a relation which may have contained exactly 2 elements as 1, 1, 2, 1. Or I could have defined a relation which could have contained elements 1, 1, 2, 2. Or I could have taken a set, a relation in which I could have taken a subset as 1, 2 and 2, 1 only, or 1, 2 or 2, 2 only, or 2, 1 or 2, 2 only. Or out of these 4, I could have taken a triplet as well, which means 1, 1, 1, 2, 2, 1, 1, 1, 1, 2, 2, 2, or 1, 2, 2, 1, 2, 2. Or I could have taken a subset as 1, 1, 1, 2, 2, 1, 2, 2. So there are 16 possibilities or 16 ways in which I can create subsets out of A cross A. So there are 16 relations possible on A. I hope you're understanding this very clearly. Similarly, if I take the previous example here, when I had defined A cross B, are you understanding this? On A cross B, how many relations are possible? You will say that it's very simple for us to predict, because now A cross B has basically 5 elements. If I ask you number of elements in A cross B, what would you say? So number of elements in A cross B are 1, 2, 3, 4, 5, 6. There are 6 elements in A cross B. I'm really sorry, not 5. So if I ask you number of subsets of A cross B, you would say 2 to the power 6. What is 2 to the power 6? It is 32 into 2, which is 64. So there are 64 relations are possible from A to B. One of those was this. So R1, R2, R3, R2, R4 up till R64 uniquely can be defined. So there can be 64 unique relations which I can define from A to B. How am I able to calculate this? How am I defining relation? And how am I able to calculate the number of relations? Are you able to understand all of this? This is exactly what we are given or written over here. As we all have seen, set A had m elements, set B has n elements. So A cross B will have m into n elements, as we have already seen 6 elements in A cross B. So the number of relations, different, distinct, unique relations which you can define from A to B would be 2 to the power m into n, as we have just discussed 2 to the power 6. Now, moving towards the next property. Here, what you need to understand is that if I am defining a relation from A to B, if I'm defining a relation from A to B, for example, here we have defined a relation R1 from A to B, then this, let me rewrite this part so that it doesn't become confusing. So there was a relation R1 from A to B. So this set A is called the domain here. I hope you can see it here. And this set B here is called the range of your relation. So range of this relation R1 is going to be this set B here. So domain of relation R1 is set A and range of relation R1 is set to be set B. I hope these terminologies are very well understood by you all. There's no confusion on it. Moving ahead towards the next part, what do we see next? I think if I give you more clarity on relations, the next property could be domain as well as range of the empty set phi is phi, and other properties. Yes, this is all what we have already discussed. Let us talk about different types of relations. For example, what is a reflexive relation? So if I'm defining a relation R on set A and I'm willing to say or call that it is reflexive, there should be ARA. What does it mean? If there is an element A in its domain, then there should be the same element A in its range, and A should be mapped with A for all A which are part of A. If you are not able to digest this, I'll try and explain you with an example. Let's say there is a relation which I'm defining on A. There is a relation which I'm defining on A. So this is, let's say, a set I'm creating. Instead of this, let me create this particular relation. So let's say there is a relation R. So R contains some elements. For example, R contains 1, 1, R contains 1, 2, R contains 2, 1, and R contains, let's say, 2, 3. So these are the some entries R contain. All right, great. So by looking at this, if I were to comment on its domain and range, can you help me with that? You will say, sir, its domain will have 1, 1, 2. So 1 and 2. What about its range? You will say, sir, its range will have 1, 2, and 3. So its range is 1, 2, and 3. And what kind of mapping are you seeing? So in this relation R, there is this relation R, right? So if you look at the mappings, what kind of mappings am I seeing here? So I'm seeing 1 getting mapped with 1 getting mapped with 2, 2 getting mapped with 1, 2 getting mapped with 3. So these kind of mappings I can see from its definition. But can it be called a reflexive relation? Now, what do you mean by reflexive relation? If there is any element in its domain, for example, 1 and 2, I can see 1 and 2. So these elements should be associated with themselves, which means 1 should have an image as 1. Similarly, if there was 2, 2 should have an image as 2. But I can see 2 is associated with 1 and 2 is associated with 3. But 2 is not associated with 2. And that's why this is not a reflexive relation. So what if I want to make it a reflexive relation? That will be possible had it have one more element, which is 2, 2. So now this is clearly a reflexive, because there could be some other entries. For example, 1, 2, 2, 1, 2, 3. That they don't matter. What I need is, if it has 1 and 2 in its domain, then 1 should be mapped with 1 and 2 should be mapped with 2. So for all A which are belonging to the set A should have a mapping ARA. So 1, 1, 2, 2. That mapping, if exists, then only I'll be calling it a reflexive relation. Did you understand this property? I hope it makes complete sense. Moving ahead towards the next, this is what you mean by a reflexive relation, as we have already understood. Now, there comes another property or terminology where I'm trying to give you more clarity about this confusion, that what is an identity relation and what is a reflexive relation. So identity relation means if an element is associated with itself only. For example, if there is a relation R and I'm defining R as 1, 1, 2, 2, and 3, 3. And that's it. These are the three elements are there in this relation R. So 1 is associated with 1, 2 is associated with 2 only, and 3 is associated with 3 only. This is called an identity relation, where the element is associated with itself only. It has its image as its domain only. So if domain has 1, the range will also have 1 and they'll be mapped together. So this is called an identity relation. And if you look at an identity relation, you will end up saying that yes, it is a reflexive relation. But not all the reflexive relations are identity relation. Why? Because if this set contains 2, 4, then of course this is a reflexive relation. Why? Because in its domain, I can see 1, 2, and 3. And do we have 1, 1, 2, 2, and 3, 3 in its mapping. So 1, 1, 2, 2 and 3, 3 is there in its mapping. Of course, there is one more mapping 2, 4, but that doesn't matter. In its domain, there were 1, 2 and 3. And 1 is associated with 1, 2 is associated with 2, 3 is associated with 3, which means it is a reflexive relation. But is it an identity relation? No. Why? Because if 2 is associated with 2, this should have been that there we should have stopped. 2 should not be associated with 4. That's where I'm saying that this is no more an identity relation. It was previously when we were stopping here at 3, 3. So now it is a reflexive relation, but it is not an identity relation. That's what I'm trying to give you or make you understand here. Let's understand a symmetric relation. These three relations, please pay attention to this part, play a very crucial role. Reflexive, symmetric, transitive. Because combination of these three, whichever relation satisfies symmetric, reflexive and transitive, whichever relation fulfills the condition to be symmetric, reflexive and transitive is said to be an equivalence relation. So please put your complete focus on understanding these three relations. So whenever there is a question, which is always asked by IT JEE, this is going to be a sure shot question on equivalence relation or reflexive, symmetric or transitive. A question is no doubtedly going to be asked in your examination. A sure shot question will be there. So please understand, either they'll ask you to form a equivalence relation based on some data given to you, or they'll ask to check whether it is equivalence or not, or they'll give you options what kind of relation it is, symmetric, transitive, reflexive or equivalence or something like that. So here, if I look at the next kind of relation, which is symmetric relation, so put your complete focus here because this is again a very crucial part. So symmetric relation means that a set R is said to be symmetric if there exists A R B, then there should exist B R A for all A comma B which belong to A. What does it mean? Let's say there is a relation R. Let me see if we have an example. Yes, we do have. Let's say there is a relation R1. So R1 contained 1, 2. I hope you can see 1, 2. So do we have 2, 1? Yes, we have a 2, 1 in R1. It is a symmetric relation. So R1 is said to be symmetric if there is A comma B and B comma A. Look at R2. R2 had 1, 2. Then do we have 2, 1? Yes. R2 had 1, 3. Then do we have 3, 1? Yes, it is a symmetric. Both are symmetric. Can you help me whether R3 is symmetric or not? I hope most of you must be seeing that we had 1, 3. Then we had 3, 1. We had 2, 3. But did we have an entry 3, 2? No, there was nothing like 3, 2 in R3. So if for 2, 3, there was no 3, 2, then R3 is not symmetric. Reflexive and symmetric, I hope, are very well understood by you all. You are understanding it clearly, thoroughly. So here, through symmetric, I'll move towards the next relation, which is anti-symmetric. What does it mean? Our relation R on set A is said to be anti-symmetric if A, R, B and B, R, A exist only if A and B are equal. If A, R, B and B, R, A exist only if A and B are equal. Let me define a relation here. Let's say there exists a relation on a natural numbers such that X is a divisor of Y. X is a divisor of Y. Then this relation R is anti-symmetric. What do I mean by anti-symmetric? Because whenever X divides Y, and if Y divides X, then it should imply that X and Y are equal. That's the condition. Let us understand it through an example. Let's say there is a relation. Let's say there is a relation R and it has some elements, for example, 1, 2 or something like, let's say 1, 1, and that's it. Now, please understand what are the different conditions. For example, if I begin with it to be reflexive, can it be reflexive? Yes, it is a reflexive relation because in reflexive, what you need is that in the domain, there is one element 1. And do we have for 1, 1? That is 1, 1? Yes, it is a reflexive. What about this being symmetric? Symmetric, it is not. Why? Because if there is 1, 2, it should have had 2, 1, which is not there. So it is not symmetric. Now, please understand, anti-symmetric is not opposite of symmetric, which means you cannot say that if it is not symmetric, it will be anti-symmetric. No. Anti-symmetric is a different phenomenon. What is it? For anti-symmetric, what you need to understand is if 1, 2 is there and if 2, 1 is also there, then it will not be anti-symmetric. Because if 1, 2 and 2, 1 are there, then 1 and 2 should be equal, which they are not, which means it is not anti-symmetric. Although in this case, it is anti-symmetric. Why? Because 1, 1 is there. I hope you're realizing that fulfills the condition for this relation to be anti-symmetric. I hope this particular definition is also understood by you all, that here, through this, you may understand it like this, that let's say 2 divides 4. Then does 4 divide 2? So let's say I define a relation where x divides y and x comma y are the elements which are there in that relation. So 2 comma 4 will be there because 2 divides 4. 2 comma 2 will be there because 2 divides 2. So 2 comma 2 will also be there, which is 2 comma 2 only because 2 divides 2. And that's exactly what we are trying to say here, that if x comma y and y comma x are there, then this should be possible only when x and y are equal. Otherwise, x comma y and y comma x should not be there if x and y are distinct. So I hope you're understanding symmetric and antisymmetric very clearly. Now, if this is understood by you all, let us move towards the next case, which is called transitive relation. Now, what is a transitive relation? A relation R on set A is said to be transitive if you have A to B and B to C. Then you should have an A to C as well in that same relation. What I'm trying to make you understand is, let's take an example and understand it more clearly. Here, let's say if I have these elements, let's take a relation R1. What do we have in R1? I have an element 1 comma 2. So 1 is directing to 2 and 2 is directing to 3. So we should have an element 1 comma 3 as well. I think we have 1 comma 3. Similarly, 1 is leading to 3 and 3 is leading to 2. So do we have a 1 comma 2 as well? I think we have a 1 comma 2. So yes, it is a transitive relation. If A comma B is there and if B comma C is also there, then there should be A comma C. Then only I'll say that it is a transitive relation. I hope you are able to digest this very clearly. Here, there is this thing which I have missed noticing, that here 2 comma 3 belongs to R1 and 3 comma does not. And that's why, yes, I'm committing a mistake. I'm really sorry. I did not notice this part. I forgot it. And that's the best part. There you should pay more attention. R1 is not a transitive because I missed one part. Why? Because we have 2 comma 3. Please pay attention. And we have 3 comma 2. So 2 is leading to 3 and 3 is leading to 2, which means 2 should lead to 2. But am I seeing anything like that? Do I see a 2 comma 2 there? No. Although for 1 comma 2, 2 comma 3, 1 comma 3 was there. For 1 comma 3, 3 comma 2, there was 1 comma 2. But it should be transitive. This condition should be filled for all the possibilities. So pairwise, if I take this pair, 2 comma 3 and 3 comma 2. So 2 comma 3 and 3 comma 2. So there should be 2 comma 2, which is not there. And that's why, although for other pairs, it was there very close to being transitive, for this pair, it did not fulfill the condition to be transitive. And this should be true for all A comma B and B comma C, which is not there here in this particular case, 2 comma 3 and 3 comma 2. And that's why it is not a transitive relation. I hope you're understanding it. Let's take other example. Let's take R2. Here, I'll say 2 comma 3 is there and 3 comma 1 is there. So 2 is leading to 3, 3 is leading to 1. But am I seeing 2 comma 1? Again, there is no 2 comma 1 in R2. And if R2 does not contain any 2 comma 1, I'll say R2 is not a transitive relation. What about R3? Let's look at R3. So 2 at a time I'll take. 1, 3, 3, 2. So I should have 1, 2. So yes, that's great. Any other possibility? I don't think that there is any other possibility. 3, 2, 1, 2, no. 1, 2, 1, 3, no. So this R3 is definitely a transitive relation, whereas R1 and R2 are not. I hope three things, reflexive, symmetric, and transitive, are very clearly understood by you all, because there will certainly be a question on this. And a question when these three are clubbed can be asked by forming a question on the concept of equivalence relation. It is nothing but what? When you have a relation which satisfies it to be, if there is a relation which fulfills all the three conditions, it is reflexive, it is symmetric, and it is transitive. If a relation is all three, reflexive, symmetric, and transitive, then such relation is said to be an equivalence relation. Did you get this part? It should be all three, reflexive, symmetric, and transitive. Here, if I try and make you understand a case or an example or a question on reflexive, symmetric, and transitive, then this is the perfect example through which we can get more clarity on it. This question was asked by JEE Mains in 2025. We'll understand it and comprehend it more clearly. Let's look at this particular question. An amazing one, a brilliant one, and a very good one, which will give you a holistic clarity on our relation being symmetric, reflexive, and transitive. Let's look at it. What does it say? That number of relation on this set A, 1, 2, 3, a very broad question it is. It will give you a very exhaustive clarity, to be very honest. And I'll be really happy if some of you could try it by yourself. So by the time I'm solving it right there in front of you simultaneously, you can also keep solving it parallel. So even either you can pause the screen and do it, or simultaneously also you can keep solving it. So read it, comprehend it, and tell me what should be the answer in the comment box. Here, the number of relations on set A, 1, 2, 3. So set A is there, containing at most 6 elements. So it should have maximum 6 elements, including 1, 2, which are reflexive and transitive, but I need to ensure it is not symmetric. Can you believe this? What a beautiful question it is. It has made you do everything related to a relation being reflexive, symmetric, and transitive. So all your knowledge will be assessed or checked, or can be, evaluated based on this particular question. So this is such a great example. How? Let's have a look at that. First of all, I have this set A 1, 2, 3. Great. I want this relation to be reflexive. Okay, so I want this relation to be reflexive. So if I want this relation to be reflexive, what should I mandatorily have? 1, 1, 2, 2, and 3, 3. So these are the three entries I should definitely have, because I want it to be reflexive. So I think the condition for it to be reflexive is very well maintained. Because if 1, 1, 2, 2 or 3, 3 are not there, then this will not be reflexive, because then its domain 1, 2, 3 are there. It is a relation on A. So A cross A will be the Cartesian product. So 1, 1, 2, 2 and 3, 3 are going to be there if we want to call it a reflexive relation on A. Along with this, they are wanting one more condition, that they want you to include 1, 2 as well. So these are the minimum 4 elements which you need to have. This is the minimum basic requirement which you need to fulfill. So these 4 entries are anyway going to be there. That's it. Your job is done. Now, what you can do is you can create a set or a relation of maximum 6 elements. So I think I have this clarity that I'll begin with minimum or exactly 4 elements, then exactly 5 elements, then exactly 6 elements. So 3 cases I'll be making. And then on all these 3 cases, I need to imagine or assume or have clarity that I'm maintaining that the relation is reflexive, transitive, but not symmetric. So I need to do things. Reflexive, I have ensured that these 3 are entered here. And when these 3 have entered here, I have ensured that yes, the relation is reflexive. So I need not bother about that. So I need to take care of 2 things. While doing all those possibilities and creation and all those mingling and merging, I need to ensure that the relation maintains to be transitive. And while maintaining it to be transitive, I need to ensure that it is not becoming symmetric. So I need to take care of these 2 things. So let's begin with that part right now here. These are the 4 terms which I'm mandatorily supposed to have. So first of all, let us create the case 1, the possibility 1, where I'm saying that can I have, let me divide this board into 3 parts so that we can keep it segregated, so that what is happening here? Just give me a second, participants. So case 2 I'll be writing here, and case 3 I'll be writing there. So this is case 1. Here I'll be writing case 2, and here I'll be writing case 3. Now what do I mean by case 1? Case 1 means exactly 4 elements. Case 2 means exactly 5 elements. And case 3 means exactly 6 elements, because at most I can have 6 elements. So these are the 3 cases. Now, when you talk about exactly 4 elements, I think I have already discussed that case. So when you talk about these 4 entries in that set, that is the minimum requirement you are supposed to fulfill, because it is going to be there. Whatever you are going to create, these 4 entries are going to be there. And if these 4 entries are going to be there, you need to ensure that it is maintained as reflexive, transitive, and not symmetric. So reflexive we have ensured. Can we check whether it is transitive or not? Okay, so let us check whether it is transitive or not. What do you mean by transitive? I hope you know A comma B, B comma C, then A comma C should also be there. So let's take any 2 pairwise. I hope you can see. You need not look much or delve further here, because the only clarity which will be given or attained by you is this, that 1 comma 1 is there, then 1 comma 2 is there. So I repeat, 1 is leading to 1, and then 1 is leading to 2. So I should have 1 comma 2. I repeat, A comma B, B comma C. So I should have A comma C. Do I have that? I think I have that. So yes, it is transitive. Why? Because 2 comma 2, then there is nothing 2 comma something like that. 3 comma 3 is there, then nothing like 3 comma something like that. So I think we are fulfilling this condition very clearly, that if 1 comma 1 is leading, then 1 comma 2 is there. Then if this is AB, this is BC, then I have AC. So it is maintained to be transitive. So this is your case 1. This is going to be the case 1, which meant exactly 4 elements. So yes, there is a possibility, one possibility which we have already created or generated here. I need to count the number of such possible relations. So this is the first relation, which is this one only. I hope there is no confusion on that. So this is your first relation, which is this only. This qualifies as that one relation. Any confusions on that? Now let's talk about exactly 5 elements. Now, how do you ensure that it will have exactly 5 elements? Sir, 4 elements are already there. They are supposed to be there. So I can add one more. Okay, let us start adding one more. But the moment I start adding one more, can I think of all the possible creations which would be there, so that picking and choosing and adjusting and satisfying or checking will be more comfortable? So what I'm trying to make you understand here is, if there is a set A 1, 2, 3, and from this set A I'm creating one more set, I mean A cross A Cartesian, a relation R on A, if I'm willing to define, the total possibility will be 3 into 3, which means 9 pairs will be created. So A cross A, the Cartesian product, will contain 9 elements. Out of those 9, I have already taken 4. So I am again left with 5 choices. Let me write those 5 choices, right? So I'll begin with the first choice, 1, 1, 1, 2 I have already taken. So in that A cross A, I'll be having these 4 choices, which I have already written, this, which I'm not writing. I am now moving towards the next set of choices, and let's see how does it look like. So here I can see that here 1, 1, 2, 2, 3, 1 with 1, 1, 1, 2 is there. So I think the other possibility will be 1, 3. I think with 1, this is the only possibility. Now let's move to 2. So 2, 1 could be a possibility. Then 2, 2 is what we have already included. So I'll write 2, 3. I think the next possibility would have been 3, 1. So 3, 1 is a mapping which could have been possible. 3, 2 we didn't have. We haven't included so far. So 3, 2 could be other possibility, and 3, 3 is what we have already included. So these are those remaining 5 cases. So 4 cases are written over here. These are those remaining 5 cases. Out of these 5, I'll pick one and then check and test and verify whether it satisfies that condition of being reflexive and transitive but not symmetric or not. So let's have a look at that. So, to this, if I club it, let's call this as a set to make us understand here. Let's call it a set, let's say R naught, right? So here that one case is our R naught, right? Now with R naught, right? Let me club it with the first case. What is the first case? 1, 3. So if R naught is clubbed with 1, 3, so I'm clubbing it with another possibility 1, 3. So to this set 1, 1, 2, 2, 3, 3, 1, 2, if I'm appending this one more possibility 1, 3, then the set will contain exactly 5 elements. Then does it still remain reflexive? I think first of all I need not bother about this being reflexive, because this is what we have already ensured. So 2 things I will keep checking now: transitive but not symmetric. Let us see whether it is transitive or not. So yes, now let's have a look at this part. 1, 1, 1, 2, 1, 2 transitive, this was there only, we have already checked it. Now with 1, 3, see, if I wish to check whether it is transitive or not, 1, 1 and then 1, 3, then I hope you can see that 1, 3 is there. Are you getting my statement? My statement is A, B, B, C, then A, C is there. Are you getting my statement very clearly? Along with this, this one is not attained from anywhere else. So this clearly fulfills the condition to be transitive. But while maintaining or keeping it to be transitive, let me check whether I have made it symmetric or not, because I need to exclude that possibility. If it is symmetric, I need to exclude this case. So when does it become symmetric? Sir, if 1, 3 is there, 3, 1 should have been there to make it symmetric. Or if 1, 2 is there, 2, 1 should have been there to make it symmetric. So if I have this 1, 2, I will keep this thing in mind that 2, 1 should not be included. I hope you are understanding it. So I will not include this case, because if I am talking about exactly 5 elements, then this is acceptable. But instead of 1, 3, if I am including 2, 1, then with 1, 2, 2, 1 will make it symmetric. I hope you're understanding it. So with that, we have come to the conclusion that this will, when clubbed with R naught, will make it a perfectly acceptable case, but 2, 1 should not be accepted. What about 2, 3? Let me think of this as a possibility, that what about 2, 3? So you have R naught, and with R naught, I'm clubbing the other pair 2, 3. Does it fulfill that condition? So let's check this part here. So again, I'm beginning with this part. See, it is clearly violated. 1 is leading to 2. 2 is leading to 3. Do I have 1 comma 3? I repeat this part. You will see it by yourself. To make it transitive, A comma B, B comma C. So do I have A comma C? I do not have 1 comma 3 now, which means this is not an acceptable case. So 2 comma 3 is also discarded now. I hope this makes complete sense here. Now, let me take the third part. What is the third part? With R naught, if I club the other possibility, which is 3 comma 1. So let's check it with 3 comma 1, whether it fulfills the condition or not. So with 3 comma 1, again, so far we were great, we were going great, we were absolutely fine. But let's check whether now 3 comma 1 helps us or destroys us. Let's look at that. So here, I'll say 3 comma 3, then 3 comma 1. So A comma B, then B comma C, then A comma C should be there, which is there. So I think it is still transitive. I need to check whether I have made it symmetric or not. So to have ensured this symmetry, if 3 comma 1 is there, 1 comma 3 should have been there, which is not because it was there as 3 comma 1. So it is still not symmetric. You could have checked it by this also, that if 1 comma 2 is there, I haven't included 2 comma 1. So if I'm not including 2 comma 1, I am absolutely not making it symmetric. So you need not worry about this being symmetric as long as you are not having 2 comma 1. So in this case of 5, symmetric it is not going to be. All you need to check is whether it is transitive or not. So the next case, the final case in this 5 elements case is going to be 3 comma 2. So let's check it with 3 comma 2 whether we get it satisfied with 3 comma 2 or not. So now I'm clubbing it with 3 comma 2. So when you club it with 3 comma 2, let's check whether it makes that possibility or not. So with 3 comma 2, I think what we have is let me just keep checking whether we are fulfilling this to be transitive or not. So with the 3 comma 2, right? So I think what do we have here is, I don't think, but let me cross check it because transitive let me check it. So 3 comma 3 is there. This 3 comma 2 is there. So A to B, then B to C. Then of course A to C should be there. So it is transitive, right? So 3 comma 3, 3 comma 2. But I hope we are not moving towards any problematic area or zone with this particular result. So we are going great. I hope that is what I'm imagining, because I don't think, let me just write this union here. This is union basically. Don't confuse it with O. This is union, right? So I think it is transitive except for any other part if I'm making any error, because 3 comma 2 won't create any issue at all. That is what I believe. So that is perfectly acceptable, because apart from that 3 comma 2 wouldn't create any problem, right? And what about 1 comma 3? 1 comma 3 was also fine, I believe, because with 1 comma 3 we were going absolutely great. What about 3 comma 1? 3 comma 1 was also fine to me, because 3 comma 3 was there, then 3 comma 1 was there, then 3 comma 1 was there. I think it was great. I don't think any problem was there. No, there was this problem. I'm really sorry, I didn't notice. Yes, 3 comma 1, 1 comma 2. I hope most of you must have noticed. I have mistakenly included it. With the 3 comma 1, there is a problem. I hope you can see A comma B. Can you notice it? Then B comma C. Then A comma C would mean 3 comma 2. So do we have a 3 comma 2? No, we don't have. So if we don't have 3 comma 2, which means this is not an acceptable case. I'm really sorry. I have taken it mistakenly. I did not notice it. So this is how minutely you should be taking care of everything. And that's where you should be more cautious and alert with these kind of scenarios. So I hope this is very well understood by you all. 3 comma 2 is perfectly an acceptable case. Why? Because I don't think that 3 comma 2 will create a problem, because 3 comma 2 is leading us to 2 and 2 comma 2 is there. Even 3 comma 3 is leading us to 3 comma 2 and 3 comma 2 is there. So I don't think that there is a problem with that. I don't think that there is any problem with that. So these two are going to be perfectly acceptable cases. I hope you are getting complete clarity on it. So far we have gotten this one case and two cases from here. So these are the two cases which when clubbed will also become our acceptable answers from this particular scenario. I hope there is no confusion on it. Now let's talk about the third case, when we are having exactly 3 elements. Now let's start working on that. Okay. When we are having exactly 6 elements. So 4 are already there. Out of these 5, I'll choose 2. Let's choose them in such a manner so that we maintain them to be transitive but not symmetric. I hope you are getting a good clarity on this part here. So I'll of course be clubbing R0 with a certain set of elements. Now I'll be choosing two, of course, pairwise, but I should be more clever, more cautious and more alert in choosing, because out of these five, any two can be chosen. So out of these five, if any two can be chosen, I should choose them more wisely and more clearly. So let's begin with this part where I take first of all, let's say 1 2 is there. When I don't take 2 comma 1, let's say I am ensuring deliberately that with 1 comma 2 I am neglecting 2 comma 1, let's say for a while. So if I am not including 2 comma 1, then I am automatically ensuring that this relation is not becoming symmetric. Did you get this part? What does it imply? Let us try to not have this 2 comma 1 from here. So deliberately we are excluding 2 comma 1. Why? Because if I have excluded 2 comma 1, so if there was a possibility of it becoming symmetric, I have excluded it. Although there can be some cases when I will include 2 comma 1 and then other possibility will be created, there I'll ensure that it is not becoming symmetric. I will make you see those scenarios as well. But here in this particular case, please understand, let us deliberately not take 2 comma 1 and let's see what happens in that case, right? So here with these four, let me club the first case, let's say 1 3 and 3 1, because 1 3 and 3 1, or rather because let's take 1 3, but I have ensured that 2 comma 1 I'm not going to take. So let's take 2 comma 3 first. Okay, let me take 2 comma 3 first, then I'll move towards the next part. So with 1 3, let's be more systematic so that our calculation does not hamper by getting confused. So 2 comma 1 I'm not taking as of now. So with 1 3 I'm taking this 2 comma 3, or rather than thinking it like this, let me be more systematic and let's calculate it in a more structured manner only. So let me take all of these one by one, pairwise. So let me begin with 1 comma 3. So I'm keeping one pair fixed, which is 1 comma 3 here, which is 1 comma 3 here. So I'm keeping one pair fixed, 1 comma 3 here, and the other pair, let's say I'm taking as 2 comma 1. Will it create some problem here? Let's check it here. So with 1 comma 3, do I see a problem? First of all, it is not symmetric, because even for 1 comma 2, if there was 2 comma 1, for 1 comma 3, there should have been 3 comma 1, which is not there. So it is not symmetric. But let me check whether it is transitive or not. So to ensure or verify whether it is transitive or not, let us say that we have this thing, which thing, students? We have this 1 comma 2, right? So I think, let me just see, because it is a game of observation, I'm just looking for a possibility through which I can discard it to be transitive. And if I could find that possibility, then we'll eliminate this case, we'll not consider this case. So I'm looking for those examples through which I can make you understand that it is not transitive or transitive. So let us try to prove that it is not transitive. If we are able to do so, we'll discard it. And if we are not able to do so, we'll have to take it. So I'm looking for a reason so that I can prove that it is not transitive. So let us look for it. For example, if I look at 1 comma 1, then 1 comma 1, 1 comma 2 is there. Great. Even for 1 comma 1, 1 comma 3 is there. So that is also making it transitive. I think that's not a problem at all, right? So with 1 comma 1, I don't see any problem so far, right? Because 1 comma 1 is leading us to either 1 comma 2 or 1 comma 3. For 1 comma 2, 1 comma 2 is there. For 1 comma 3, 1 comma 3 is there. I hope you are understanding A comma B comma C, then A comma C. That is the condition I'm verifying, right? Let us look at 2 comma 2. For 2 comma 2, we have 2 comma 1. So for 2 comma 2, if we have 2 comma 1, then of course, I'd say that 2 comma 1 is there. 2 2 AB BC. Then I should have AC, which is 2 comma 1, which is also fine, which is also perfectly fine, right? Along with this, I think this 2 is not leading us anywhere else except for this part. So that is also great. Now look at this part. 3 comma 3 is not leading us anywhere. So that can be skipped. That can be perfectly skipped here. That is again not a problem. Now let's look at this 1 comma 2. So we have this 1 comma 2 and we have this 2 comma 1. So I should have a 1 comma 1, which we already have. So to me, it looks like an acceptable case if we don't see or face any problem at all, right? So 1 comma 3 and 2 comma 1 is what we have included so far. Let us cross check it again if there is anything which we are missing to make it a little more, to have more clarity on this. 1 comma 2, 2 comma 1 is there. So I think 1 comma 1 is there. Yes, 1 comma 1 is there. 1 comma 3 is there and 3 comma 3 is there. So 1 comma 3 should be there. With 2 comma 1, I think 2 comma 1, yes, I am missing one part. When you look at these two only, there you will see that this one part was a little more tricky. 2 comma 1 is leading us to 1 comma 3. I hope you're understanding it. So 2 comma 3 should also have been there, which we haven't included. I hope you can see A comma B and then B comma C. Then we should have A comma C, which means 2 comma 3. Are we seeing a 2 comma 3 here? No, which means this is not an acceptable case. So what we need to put our efforts in proving it wrong. So if by some means we could find any glitch, any error, any catch, then we'll reject it and we'll discard it. And that is where you need to put efforts. That is where you need to put efforts. So if 2 comma 1 is discarded with 1 comma 3, with 1 comma 3, I'll club 2 comma 3. So now I'm clubbing a 2 comma 3 here, right? So let's see whether it matches as 2 comma 3 or not, right? So let's take 2 comma 3 now. Okay. So with the 2 comma 3, what is the possibility here? Whether it is acceptable or not. So let us again check it one more time. And transitivity is what I need to verify. So let's say 2 comma 3 is leading us to, or even if I take 1 comma 2 is there, 2 comma 3 is there. So I should see 1 comma 3. Yes, it is there. So it is perfectly acceptable. Great, brilliant. Similarly, if I am seeing 1 comma 3 and then 3 comma 3, that is perfectly fine. That I need not verify. And if I am seeing, yes, there is a catch, I think, no, that's not a problem. That is also fine. Let us keep checking, right? So that is where you need to be more observant, more vigilant, and that's how you verify it. So how do I proceed further? 1 comma 2, then 2 comma 3. I have 1 comma 3, that is fine. Then you have 2 comma 3, 3 comma 3, then you have 3 comma 3, 1 comma 3, 3 comma 3, 1 comma 3 is there. 1 comma 3, is it leading us to anywhere else? No. Then we have 2 comma 3, that is also there. So 1 comma 3, 2 comma 3 should be an acceptable case. But apart from this, how do we keep checking it further? Do we have any other possibility apart from this 1 comma 3 and 2 comma 3? I don't think that 1 comma 3 and 2 comma 3 are creating any trouble. Let us keep checking, because there you need to be more cautious, more alert, because if you miss any part, you will end up marking it incorrectly. So if I keep checking it further, let's be very much assured so that we don't commit any error. So let us be more systematic. 1 comma 1 was there, 1 comma 2 was there, that is fine. So 1 comma 1 was there, 1 comma 3 was there, that is also fine. 1 comma 3 was there. So 1 comma 1 is not there at all a problem. Now let's look at 2 comma 2. So with 2 comma 2, I think it is not a problem, because 2 comma 2 was leading us to 2 comma 3, and 2 comma 3, 2 comma 3 is perfectly acceptable. With this 2 comma 2, do we have any other possibility? I don't think so. So here, let's look at the other case. 2 comma 3 comma 3 is also not a problem, because 3 comma 3 is not leading us anywhere. So that is also acceptable. With this 1 comma 2, if I move ahead, that is what we have already verified. This is leading us to 2 comma 3. So 1 comma 3 should be there, which is already there. So it is also making it transitive, right? And although it is clearly visible that it is not symmetric, because for 1 comma 2, 2 comma 1 should be there, which is ensuring that it is not symmetric, right? Again, if I look at this part 1 comma 3, then 3 comma 3 is also there. So I think it should be an acceptable case apart from any other part where I'm seeing it to be happening. Now let's look at the next part. So I think with 1 3, 2 3 is perfectly acceptable. Let's look at the next part. So with 1 3, if we have club 2 3, let's look at 3 1. So next case will be this RO, this RO. I am clubbing with this R naught or RO, whatever you wish to call it. 1 3, I am clubbing with, let's say, 3 comma 1. Is it an acceptable case? Let's check it, right? So you need to be more vigilant, right? That will consume some time. So let's say 3 1 is there and 1 2 is there. Yes, it is discarded. Why? 3 1 and then we had 1 2, which means we should have a 3 2, and we don't have a 3 2. So if we don't have a 3 2, this is clearly going to be excluded. Did you get this part? I hope you are perfectly able to understand this. So 3 1 is discarded. Now let's look at the next possibility, which is 3 comma 2. Now let's look at 3 comma 2. Will it be an acceptable case? Let's try and find it out. So here again, we have 1, 3, right? So we have 3, 2. So with the 3, 2, I don't think there is any problem because this is going to be acceptable. First of all, it is not symmetric. Why? Because for 1, 2, we need 2, 1, which we haven't included. So it is, of course, not symmetric. For transitive, I think we are fulfilling the condition because I'm not seeing any evidence to discard it. But still, we need to be more vigilant, cross-check it completely. So I think, let me just check it one more time. How I see it personally, see 1, 3 and then 3, 2. So I need 1, 2, which I am seeing here. So transitivity, I think, is maintained very well because even for this 3, 2, 2, 2 is not a problem. For this 1, 3, 3, 3 is not a problem. You are very much assured now that reflexive is not what you need to cross-check again. So this is the part where I needed to check it again, and 1, 3 is very much acceptable with 3, 2 because the only challenge was this, that if 1 is leading to 3, 3 is leading to 2, then there should have been 1 comma 2, which is there. So I think it is transitive. Any other possibility, 3, 2, then this is 2, 2 only. 1, 3, then there is 3, 3 only. So it is perfectly an acceptable case. So these are the two acceptable cases. Now, abhi, so far I have taken 1 comma 3 with this, this and this. Now I will take 2 comma 1 with this and this. So that is going to consume a lot of time and you don't have any other choice apart from that. So this time I'll take R naught union, right? R naught union. Now I'm going to take 2 comma 1. So once you take 2 comma 1, what choices do you have? With 2 comma 1, 1 comma 3 we have already seen. So with 2 comma 1, I'll have 2 comma 3. Can I take that? Can I accept that? Let us check and verify it, right? So again, if I'm having 1 comma 2 and 2 comma 1, I think I'm making it symmetric. But yes, for 2 comma 3, 3 comma 2 should have been there. So it is not symmetric. That is checked. Is it transitive? Let us check that. So here, yes, it is not transitive. Why? 1 comma 2, 2 comma 3. So I should have 1 comma 3, which I don't have. So I should discard this. So for 2 comma 1, 2 comma 3 won't be there. Let's check 3 comma 1. So for 2 comma 1, let's have 3 comma 1. Is it symmetric? No, it is not, because 3 comma 1, 1 comma 3 should also be there, which is not there. So not symmetric is fine. Let's check its transitivity. So to make it transitive, again, it is not transitive. Why? Because look at this part. 3 comma 1, I hope you can see it very clearly, and 1 comma 2. So I should have a 3 comma 2, which I am not seeing. So 3 comma 1 is also discarded. After 3 comma 1, let me take 3 comma 2. So let me take 3 comma 2 now. So with the 2 comma 1, let me take 3 comma 2. Again, there is a problem. I hope most of you must have noticed. The problem is this, that here, if you are noticing that this part 3 comma 2, 2 comma 1. So I should have 3 comma 1, but I cannot see a 3 comma 1 here, which means this is also not a transitive case. So for 2 comma 1, I don't see any possibility. So this and this are done. Now I'll club 2 comma 3 with these two. Okay, so let's go ahead with this part. The next set 2 comma 3 is what I'll begin with now. So I'll be taking 2 comma 3. So first of all, I'll club 2 comma 3 with 3 comma 1. Let's have a look at this. So this is what we have, right? 2 comma 3 with 3 comma 1. All right. So 2 comma 3 and 3 comma 1. So I again am able to discard that 2 comma 1 should be there. And I don't see a 2 comma 1 here, which means this is also discarded. So that is also not going to be an acceptable case here in this case. Now, let's look at the next possibility. With 2 comma 3, let me club 3 comma 2. So let me club 3 comma 2. Okay, great. So here, if I am seeing this, let me check it for all the values here. 2 comma 3, 3 comma 2. Of course, it is not symmetric because for 1 comma 2, 2 comma 1 should be there. I'm checking it for transitivity basically. So 3 comma 2 is there, right? R naught 2 comma 3 and 3 comma 2 is what we have clubbed here. So 3 comma 2, 2 comma 3, 3 comma 3, which is there. There is no problem at all. 2 comma 3 and 3 comma 2, 2 comma 2. Yes, I think, no, that's not a problem. But if I move ahead, if I keep checking, let us keep checking. So 2 comma 3 is there, right? Yes, there is a problem. 1 comma 2, I was not looking at this. 1 comma 2 and 2 comma 3. So I should have a 1 comma 3, which I'm not having. And if I am not seeing a 1 comma 3, which means this is again not a transitive. So I am left with the last possibility and I need to verify it with that last possibility now. What is that last possibility? 3 comma 1 and 3 comma 2. So the last possibility is 3 comma 1 and 3 comma 2. Let us check it for this. So what do we have here is that I think I haven't made it symmetric at all, because for 1 comma 2, 2 comma 1 is not there. So yes, it is not symmetric. But if 3 comma 1 is there and if 1 comma 2 is there, then we should have 3 comma 2. Yes, so far it is transitive. If 3 comma 2 is there, I think there is not a problem at all. If 3 comma 1 is there and 1 comma 2 is there, then 3 comma 2, I think I have already checked it. So 3 comma 2, 2 comma 2, I don't think any of the problem would arise, because 1 comma 2, no problem at all. No problem at all. So it is perfectly an acceptable case. So how many cases are found in this particular result? Through this particular result, I could find 3 cases from here. I hope you can see. So 3 cases were derived from here, 2 from here, 1 from here. 3 plus 2, 5 plus 1, 6 would be the answer. Lengthy it was. In terms of calculation, it was heavy. More importantly, it took a lot of time, because through this question, I had this opportunity to make you understand reflexive, transitive, and symmetric more clearly. So how do we make a relation as per their expectation? I hope you are getting it more clearly. So maintaining relationships is not easy these days. Because even in sets and relations also, you must be realizing and noticing it, that it took a lot of time for us to cross-check everything. Because even a single mistake, if you forget noticing, if you avoid, if you just, miss it, you will end up making or marking the wrong answer. I hope you are understanding. So you need to be more cautious, more alert, very much focused in this category of questions. And that's why they love asking. Because even a slight error, slight mistake, or a slight, casualness will lead you towards marking a wrong answer. So that's where you need to look at everything very exhaustively and very, very thoroughly, very, completely, in a very thorough manner, so that you cover everything. Be more vigilant, be more cautious. Let us move ahead towards the next part. I hope this question gave you a holistic, complete, and a brilliant, great clarity about reflexive, symmetric, transitive, and of course, our relation being equivalence. This is a question I'd like to give you as a homework question, or you may call it a bonus question. Of course, I'll give you the hints, don't worry about that, but I'll be hoping that you do it by yourself. Now, what are the hints? First hint, that there is a set A, which is defined on, of course, x comma y, r cross r. R cross r means all the real numbers. So you can go on the Cartesian plane and imagine all the numbers. That Cartesian plane is r cross r. Now, on that Cartesian plane, I need to plot mod x plus y greater than equal to 3. So whenever mod x plus y is set to be greater than equal to 3, and if you want to remove its mod, it can be written as mod x plus y should lie between minus 3 and 3. So first, you draw the straight line. Which straight line, students? The first hint will be, draw the straight line x plus y is equal to 3. And then this straight line will be dividing your region into two parts, dividing your entire xy plane into two parts. So check which region satisfies it and shade that region. And then draw this line, x plus y is equal to minus 3. This line will also be dividing your xy plane into two parts. And see, check, verify with any point and check whether that point satisfies your condition or not. For example, I take 0, 0. So 0, 0 is greater than minus 3. Yes. So in whichever region origin lies will be the region which I need to highlight. So I need to take intersection of those two regions. I get a region from this, I'll get a region from this, and I'll take the intersection. That will be this particular set A. So this is what I'll be solving through geometry. Now, I'll move to set B. Now, set B, what does it say? It says, again, you need to look at R cross R, which means what? Again, your entire Cartesian plane. Then on R cross R, we need to fulfill or satisfy this possibility. Now, what you do is here is that you divide your XY plane into 4 quadrants. So in the first quadrant, x and y both are positive. So this will become x plus y is less than or equal to 3. In the second quadrant, x is negative, y is positive. So it will become minus x plus y less than or equal to 3. Similarly, here both are negative. It will become minus x minus y less than or equal to 3. Here x is positive, but y is negative. So it will become x minus y is less than or equal to 3. Again, the moment you start plotting these two lines, or rather 3 lines, you will see that it will create a rhombus or a square. So by that, another shape, another region will be created by you here, which will be fulfilling these 4 inequalities, which is the single inequality only. How? Again, the part remains same. I will treat it as a straight line. X plus y is equal to 3. I'll plot it 3 comma 0 0 comma 3 intercept form. Then that line will be dividing our xy plane into two regions. Now let's satisfy it with origin. Does origin satisfy it? Yes. So the region in which origin lies will be my acceptable region. So through this, you will basically get four lines somewhat like this. One line, second line, third line, and fourth line. Of course, there'll be more proper. I have just drawn a rough figure, rough sketch here. And through that, you'll get a rhombus or a square basically. Of course, through this also you'll get a shape. Now, what are we asked? We are asked A intersection B. So through this, you'll get a region. Through this, you'll get a region. And then you need to find the intersection of it. I hope you know how to do it. So two geometrical shapes you'll get. You merge them into one. And then you need to find the intersection, the common part of these two shapes. Once you have found the common part of these two shapes, then find that how many values of x and y are satisfying it here. Here, what you need to understand is that in this set C, here you need to understand that in this particular set here, what is missing, I think, is that integral values of x and y, because yes, this A intersection B is what you need to find when either x is 0 or y is 0. So you put either x is 0 or y is 0. So you will look at all the values which are lying on x-axis, and then you'll look at all the values which are lying on y-axis. Because for y is equal to 0, basically you're looking at x-axis. For x is equal to 0, you'll be looking at y-axis. So three things will happen here. First, you will draw this region, then you will draw this region, and in that intersection of these two regions, you will locate the points which are lying on x-axis and y-axis. Once you have found those points, just find the summation of those points. That will be your final answer. Did you get that part? Did you understand this part? I'll make it even simpler for you. Instead of putting a C here, I will do this thing more simpler for you, that xy is a set which belongs to A intersection B, and of course I'll add one more thing here, that let's say you are taking some integral values only. So here from this set C, x and y are some integers only, You are adding one more condition here in this set C. That will make your calculation more simpler and easier. I have made this problem easier. Trust me, I have solved it completely. We cannot call it a bonus question or a homework question. It is a very simple question now because I have almost done it. You just need to do the calculation part, and of course a little bit building of this particular construction of this particular region, which you can do now because I have told you the entire approach. So I'm hoping that some of you, or rather most of you, must solve this and find the answer and mark the correct option. Although with this condition, the question may change, the answer may change, and of course, do write your response in the comment box. I hope now you are more comfortable with set theory, their representation, and how should you deal with them, and how should you deal with operations on them. Once you have gotten this particular part, let us move to the next part, where we now finally discuss what is a function. Sets and relations we are now done with. Now we are gradually shifting towards functions. Now we'll discuss functions, domain, range, composite function, inverse, functional definitions, and lot more in a very detailed, a great format. This is a different chapter. We have clubbed these two chapters, sets and relations and functions, together, and we are discussing all of this together in this one single video. So now let's put our focus on discussing the chapter functions. What is it? Function is basically a relation only, but with more constraints, with more restrictions. What is that? If I could simply tell you or make you understand through this one example, then let's say we have a relation. Of course, in a relation we have a domain and we have the range. So this set, which we have been calling this from A to B, from B to C, whatever set we are taking as domain, the other set where images are mapped, I'm calling that set to be the codomain here. So I repeat, there you have a set A, which is that domain set. There you have this set B. So the Cartesian of A and B is taken, then you take any subset of it and then you define it as a relation R from A to B. Perfect. Relation, I hope, is very well understood by you all. Now we are moving towards understanding function. Now what is function? Function is a very specific, very standardized case of a relation, a very restricted case of a relation, where you put a condition on a relation. What is that condition? For example, let's say there is a set A which has the elements A, B, and C. There is a set B which has the elements D, E, F, G. Now, our relation will be called a function. So function is basically a type of relation, a special type of relation. And I'll be calling this relation a function if only one condition is fulfilled. What is that condition? Let me highlight it here. If I have each element of set A with unique element of set B. I'll try to give one more definition here, that if there is a element in A and the element in B which is assigned to A is called the image of A, then the image of A should be unique. So each element of A should be mapped with a unique image in B. What do I mean by that? Let me give you more clarity here. Say there are some elements in A. So first of all, function says each element of the domain set. The domain set is set A. So from A to B, I'm defining a relation, but instead of calling it a relation, I'm calling it a function more specifically. Why? Because first of all, each element of the domain set, which is A, so each element should have a unique image in set B. B is your codomain set. So each element, for example, A. So A should have a unique image here. A should have a unique image. Unique image means that if A has an image F as well, then A has two images, D and F. In that case, I would love to call it a relation, but sorry for this, it is not a function. Why? Because A does not have a unique image. A has an image D, A has an image F, and these are two images of A which are not unique. I hope you can see that. So I need to take either of them, either D or F. So let's say I have chosen D. So A, yes, indeed has an image D. What about B? Let's say B has an image F. Perfectly fine. And again, I'd say B cannot have more than one images. B should have only one image, one unique image. That's what makes it a function. But at this stage, will I be in a position to call it a function? No. Why can I not call it a function? Because the problem is that the definition of the function says, the very definition says that each element of set A. Have I included all the elements, every single element of A? No. I have so far included two elements, but I'm still left with one element. So this C should also have a unique image. For example, this C I have mapped with F only. Is this what you call a function? Sir, are we having a unique image? Yes. Look at this C. C is having a unique image F. But sir, F has two pre-images. Then there is no problem at all. When did I mention that F should not have more than one images, pre-images? That is a perfect possibility. That is not a problem at all. Why? Because B has a unique image? Yes. Does C have a unique image? Yes. Do B and C have the same image? Perfectly fine. All I need to ensure is two things. No element in the set A should be left behind. First condition. Second condition, that all of them should have a unique image. Have I ensured it? Sir, but E and G don't have any pre-images. No problem at all. And that's where you bring the concept of range into picture, that D and F are the elements in the codomain set which have pre-images. That's why if I talk about the range of this function, if I talk about the range of this function, then I'll say it is D and F. So there are three things. Domain is from where the function is defined. To a codomain, DEFG, to the function is defined. And then there is a subset of codomain, which is range, which have the pre-images in the codomain set. So range means what? For these values, you had certain images. The set of those images is called range. Did you get this part? And range, I hope we can very easily conclude, will always be a subset of codomain. Did you get this part? Any confusion on that? I hope you have understood functions very clearly here. Now, if you have understood functions, let us seek more clarity on its domain, its range, as we have already seen and understood this part. I think I need not explain this part. This is also we have already seen and understood. Now let's talk about this mapping part. So number of functions or mapping from A to B. So let's say A has certain elements, B has certain elements. So let's say A has m number of elements, B has n number of elements. Now, I now want to understand that how many functions are possible here. How many possibilities are there? So first of all, I need to have images of all of these x. X1 should have a unique image, X2 should have a unique image, X3, X4 until Xm. all of these should have a unique image. Now, if I use permutation and combination, if I use the basics of PNC, would I not say that I'll approach X1 and ask how many choices do you have? X1 will say I can go to either Y1 or Y2 or Y3 or Y4 or up till Yn, or means either this or this or this or this, but not both, not all three, not all four, not all n. So what if I ask X1 about its number of choices? It will say I have either Y1 or Y2 or Y3 up till Yn. So I have n choices. So X1 will come up with the response saying I have n choices. The same response will be brought by X2 as well, because there is no problem with this function being, many one, because if X1, let's say, is mapped with Y1, X2 can also go to Y1, because this relation, while maintaining it to be a many one, will still qualify as a function, because it is not a problem, because X2 still has a unique image. So there also, if I approach X2 and ask how many choices do you have, it will also come up with a response saying I have again n choices. The same n choices X3 has, the same n choices the last xm also has. So I'm multiplying n m times. So if I'm multiplying n m times, I'm having n to the power m possibilities. So I repeat my statement very clearly. If I have m elements here, n elements in the codomain, m elements in the domain, then the number of possible functions will be n to the power m. Instead of remembering like this, remember the logical approach, which is more convenient as to figure out. What did I just say? I simply said this particular part. Please remember this, that the number of functions or mapping from A to B will be the number of elements in codomain whole raised to the power number of elements in domain. Did you get this part? If you wish to take an example, I can take an example and make you understand it more clearly. Let us take an example. Let's say there is a set A, there is set B. Set A has, let's say, 3 elements, A, B, and C. Set B has, let's say, 4 elements, D, F, G. Now, if I were to ask you how many functions can you create from this domain and codomain? So, total number of functions, if I were to ask you. So, you would say that, sir, A has 4 choices, and B also has 4 choices, and C also has 4 choices. So, basically, 4 cube are the total number of functions which can be formed. Distinct 4 cube. 4 cube means 64 functions I can create. One of those functions will be this, that let's say A is mapped to F, B is mapped to E, C is mapped to G. This is one of those functions. So such 64 possibilities are there. Are you understanding this result? Now, if you have understood this, there is this graphical representation of functions through which you can understand more clearly. But before we come to the graphical understanding of these functions, there is one thing which you need to remember. Let's say I am drawing the graph of a function. Let's say I have drawn a graph of the function like this, and I wish to verify or validate whether it is a function or not. So there is a test which is called vertical line test, VLT, which says that if you are able to draw a line parallel to the y-axis, a vertical line basically, which intersects this graph of the function at more than 1 point, then it will not be a function. Why am I saying so? Because, for example, let's say this is y-axis and this is x-axis, and here you are seeing this as a graph of the function. Now, let's say I am drawing a line which you should be able to find in such a manner that if you are able to draw a line parallel to the y-axis, vertical line basically, and if it is intersecting the graph at more than 1 points. For example, look at this part here. Look at this part here. So this will be a certain x. Let's call it x1. So for this x1, I'm getting this value, which is y1. For this same x1, I'm getting another value, which is y2. So here, if I'm putting f of x1, I'm getting y1. And if I'm finding x1, then I'm finding y2 as well. Again, are you not seeing it as a violation of the very definition of function? Because for x1, there should be a unique image. But for x1, I can see 2 images, y1 and y2. That's a clear violation here. So it is not a function. It is not a function at all. I hope you're realizing. So through vertical line test, you can always verify and validate whether what you're seeing as a graph is function or not. All you need to do is draw a line, try to draw a line which is intersecting the graph at more than 1 point. And if you are able to do so, you can claim unhesitatingly that the graph representing the graph which is represented by a relation is not a function. Now, There comes these three things through which you define the domain of a function. Let's say I am adding two functions. Let's say I am adding two different functions and I am asked to find their domain. Then all you need to find is find the domain of first function, find the domain of second function, and take their intersection. The same is true for their subtraction, the same is true for their product. But if you're dividing one function by another, then the denominator, then you should ensure, of course, the intersection of d1 and d2 is still needed to be taken when you add, subtract, multiply, or divide. But in the case of division, you need to exclude the possibilities when the denominator is becoming 0. For example, let's say I am asked to find out the domain of, let's say, sin x upon x. So of course, I need to ensure that what is the domain of sin x, I need to ensure what is the domain of x, and I'll take the intersection of the domains because of the division. But out of this, I need to exclude those possibilities. When this denominator is becoming 0. And I think the denominator x becomes 0 at 0. So I will exclude this possibility. Because sin x has the domain R, it is true for all the real values of x. X has the domain R, it is true for all the real values of x. But the denominator can never be 0. That's the possibility you are supposed to exclude. Did you get that part? How do we understand functions? Let me give you more clarity through this particular result. That this is all what we'll be discussing, and then we'll discuss questions based on domain and range. But before we discuss questions based on domain and range, I'll try to give you this clarity that this is the broader classification of functions. So I'll get out of this frame so that you can see it completely. Take a screenshot of it if you want to. But we'll of course discuss this in more detailed format. We'll talk about algebraic functions. We'll talk about transcendental functions. We'll talk about piecewise functions as well. We'll talk about more functions as well. But this is the broader classification or categorization of functions. How? Let's get started with them one after another. First one of them is algebraic. Now, if we start our discussion with algebraic functions, it's a very simple thing that let's say you have algebraic expressions. For example, x and 1, they are simple to algebraic expression, and if I'm putting addition sign on them. For example, here x cube, 16x, x and root x are there. You are adding, subtracting and dividing them. So that's how you create an algebraic expression. So first of all, these are called algebraic functions. So whenever you have algebraic expressions in picture, when you add them, subtract them, multiply them or divide them, and that's how you create a function basically. So such functions are called the algebraic functions. Of course, when you talk about different types of algebraic functions, then they can be, first of all, them could be monomial function. Now, what is monomial? If a function which has only one term. Of course, here this should be of the form ax to the power n, and here n should be a non-negative integer. So this is called a monomial function. What does it mean here? For example, y is equals to x square. As you all can see it here, y is equals to x square is a monomial function. If you look at this particular function's graph, y is equals to x square goes something like this. So this is your function y is equal to x square. Or of course, function in x is written as f of x. So this represents a function which has the variable x, and the variable is x, and the output will be x squared. So if there is only one term, one algebraic term only, in that case you will have it monomial function. Since it is giving you a parabola, if you draw y is equals to 2x, it will give you a straight line. If you draw y is equals to minus x, it will also give you a straight line. So these are all monomial function. Now, when you move ahead, there is polynomial function. So monomial had only one term. Polynomial means it will have more than one terms. For example, here, look at this. Look at these examples. They will give you a complete greater clarity. See, here this fx is x to the power 1920 plus 5x to the power 1919 plus 6x. So this is a polynomial of degree 1920. We have been studying polynomials since our childhood days. So I think I did not explain this particular part where you define a function to be a polynomial function if it is of this particular category. What does it mean? A naught, which is a coefficient of x to the power n, then there is another coefficient a1, which is the coefficient of x to the power n minus 1, and so on until a last constant term an. Of course, here you need to understand that a1, a2, a3, they all are the real constants. Along with this, there is a power n which is a non-negative integer. So if something like that is given to you, you call it a polynomial function. And of course, a naught, the coefficient of the highest degree term, should not be 0. And that's when we call it to be a polynomial of that degree, the power. Here, as you all can see here, if we have hx as 7. So this is also a polynomial of degree 0 because it is 7 into x to the power 0. This is a quadratic which is polynomial of degree 2. That something is what you already must be aware of, and at least I need not explain this part. Now, polynomial of degree 1 with no constant term is called an odd linear function. We all know that. Something like fx is equals to ax, fx is equals to 3x, fx is equals to 5x, or something like that. Now, similarly, if in case fx is equal to 0, it is constant function for which degree is not defined. So if fx is equals to 0, we call it constant. Fx is equal to 2, we call it constant function as well. Although it can be a polynomial of degree 0, but it can be said to be a constant function as well. Now, if I'm talking about a polynomial of odd degree, so whenever you draw a polynomial of odd degree, let's take an example here. Let's say I'm taking an example ax cube plus bx square plus cx plus d. So always remember, let's say this is a polynomial. Now the coefficients of x cube, x square, x in constant term could be anything, but the polynomials of odd degree will always have its range from minus infinity to plus infinity, which means if you are drawing its graph, although it could be drawn something like this, that it may start from minus infinity and it will go to plus infinity, or it may start from plus infinity and go to minus infinity. So the graph of a polynomial odd degree function could be somewhat like this, or it could be somewhat like this. It could be like this as well. It depends on the degree of it. But if it is an odd degree polynomial, in that case, always remember that this polynomial will have its range from minus infinity to plus infinity. Always remember, an odd degree polynomial always has the range from negative infinity to plus infinity, which means all the real numbers. Always remember this as a fact. Now, if I move ahead, all polynomial functions are algebraic functions, but not the converse. Because if there is an algebraic function, let me show you here. If there is an algebraic function, let's say somewhat like this, then it is not necessary that this was a polynomial. But if there is an expression which is a polynomial function, it has to be an algebraic function. I hope you are able to differentiate these two with these examples. Let's move ahead. Let's discuss few more things related to this part, which I hope has given you a great clarity. If I talk about a constant function, this is how you draw the graph of the constant function. Let's say I'm drawing the graph of y is equal to 3. So what do you mean by fx is equal to 3? This is 3 for all the values of x, which means it will pass through the point 0, 3 on the y-axis, and it will always be 3 no matter what value of x you put. So this is a constant function. So if you were asked what is the domain of this function, so you will say that domain of this function will be nothing but what? Sir, I can see its graph from minus infinity to plus infinity. So its domain basically is nothing but what? Domain of this function is all the real numbers from minus infinity to infinity. What about its range? Sir, it is occupying or retaining only one value, which is 3. So if you are asking the range of this function, it is going to be only one element, which is that constant value only, which is 3 in this case. Did you get that part? But if I take back you to the polynomial scenario for a polynomial function, so whenever you deal with a polynomial, polynomials are defined for all the values of x. I repeat, whenever you are drawing the graph of a polynomial function, an even degree polynomial and an odd degree polynomial, you would see their graphs to be going somewhat like this. This could be a graph of an even degree polynomial. This could be a graph of an odd degree polynomial. Now, what I'm trying to make you understand is whether it is even degree or odd degree, you will see its graph, having it is lying on the for all the points on the x-axis, which means for all the values of x, the graph will exist. Which means if you talk about the domain of the polynomial functions, it is always real number, whether the degree is odd or even. Even for an odd degree polynomial, the graph will exist from minus infinity to plus infinity. That will not be a problem. But the catch here is that whenever you deal with an odd degree polynomial, please understand this here is an odd degree polynomial. I hope you are understanding what do you mean by odd degree, 3, 5, 7, something like that. And this here is an even degree polynomial. So whenever you deal with an odd degree polynomial, the graph of odd degree polynomial ranges from minus infinity to plus infinity on y-axis. So if you're asking the range of an odd degree polynomial, it will be from minus infinity to infinity. That is all real numbers. But the catch here is if you talk about the range of an even degree polynomial, so it could be either from minus infinity to a fixed largest value, or it could be from a least value to plus infinity. So what you need to understand is for even degree polynomial, the range is not minus infinity to infinity. The range will be from minus infinity to a fixed highest number, which could be found through its methods, or a low value, a least value, a minimum value to infinity. This could be the range of an even degree polynomial. But if it is an odd degree polynomial, its range will also be minus infinity to infinity. That is what you should remember. Now, let us get back to our discussion we were having about constant function. I think this is what we have discussed so far. Now, identity function. For an identity function, you define it as y is equals to x. So this is the identity function. And if you talk about identity function, as you all can see, its graph is there from minus infinity to infinity on x-axis. We can trace the entire graph from minus infinity to infinity, which means its domain is going to be all the real numbers. And when you talk about its range is also going to be minus infinity to infinity, which means its range is also going to be all the real numbers. I hope it is understood by you all. Now, moving ahead, what do we have next? A rational function. So we have two polynomials, let's say px and qx. So px is a polynomial, qx is a polynomial. So if I'm dividing px by qx, where of course qx should never be 0, then such functions are said to be rational functions. If you were to take an example, I'll simply say that let's say there is the polynomial x square plus 3x plus 2. Let's say this is px, and there is another polynomial qx, let's say, which is 3x cube plus 2x plus, let's say, 5. So this function, if I'm defining, then this is something px upon qx, a quadratic upon cubic polynomial. In that case, I'll call it a rational function. Of course, here I need to ensure that this denominator should never be 0. So in the domain of this function, I am supposed to take all the values of x except for those values of x for which the denominator is 0. So I'll find the roots of the equation 3x cube plus 2x plus 5, and if I see that it is becoming 0 at certain values of x, then those values of x should be discarded from its domain. So domain will be all the real numbers except for certain values for which this is becoming 0. The denominator is becoming 0. Did you get that part? Now, here is an example here. For example, if I have this function fx, which is x square minus 3x plus 5 upon x minus 1, x minus 2. So its domain will be all the real numbers, but I am not supposed to include 1 and 2 because at 1 and 2, it becomes 0. The denominator becomes 0 and the function becomes not defined. I hope you're getting it. The same will be true for this here. 1 minus cos 3x should never be 0, as we know that cos 3x will always lie between minus 1 and 1. So, sorry, 2 minus cos 3x should never be 0, and we know that cos 3x can never be 2 because cos 3x is always less than 1. So, in that case, this will never be 0, and if it is never 0, then we can say that its domain is all real numbers. So, through understanding of these functions, we are gradually understanding how do you deal with domain of different category of functions. So, keep your eyes open. Keep your focus very, very well, here only, so that you keep understanding the domains of all these standard functions, because through the understanding of these standard functions only, we solve questions based on domain. We'll see, of course, questions on domain, but as of now, you need to understand that this is how you deal with them. For example, here, this is an irrational function. Now look at this. An algebraic function having non-integral rational exponent is called irrational. Look at this. X to the power 1 by 2. So the power 1 by 2 is a non-integral rational exponent. And here we all can see that if you are looking at x to the power 1 by 2, I'll say that x cannot take any negative value. Because if you put the negative values, x to the power 1 by 2 won't be a real number. And that's where we say that if you talk about fx is equal to x to the power 1 by 2, which if I were to define in a different world, it is nothing but what fx is equal to under root x. So I cannot have this x as a negative value. So if I want to ensure that x is not negative, I'll say that x should be non-negative. And if x is non-negative, I'll say its range is 0 to infinity. I hope you understand the brackets, the conventions, close bracket, open interval, and something like that, and you are able to make some sense out of it. Now, this is also an irrational function because, of course, it is a rational in terms of two polynomials, but the numerator and denominator don't have a polynomial over there. I'm having algebraic expressions, that too some irrational terms. I hope you can see them. So this I'll still be calling it as an irrational function. Did you get that part? Let us move ahead towards the next part. Here, this is something very important. This is something IIT JEE loves asking. So IIT JEE is in love with this particular concept. What is it? This? What is it? What is it? What is the concept? Let's have a look at that. So here what you need to understand is, let's say there is a polynomial and they are giving its functional definition. So they are telling us that there is a function which fulfills or satisfies a condition such that fx into f of 1 by x is equal to fx plus f of 1 by x. Always remember, whenever you're given this kind of a condition, you say that fx could be either 1 plus x to the power n or fx is equal to 1 minus x to the power n. So basically you say that fx is 1 plus minus x to the power n, where n is basically a positive integer. It could be plus or minus, it all depends on some more data given to us. One more clue could be given to us, and on the basis of that, we can figure out whether it will be plus or minus. And with the help of one more clue, we could be able to find the value of n as well. So this is how you solve questions based on it. Although we'll solve a question on it, and we have had a discussion on this particular concept in quadratic equations as well. So go and watch the first video, the last question, which was the bonus question, which was the homework question. That question was based on this concept only. So functional equations was used in quadratic as well. Can you believe that? And that's exactly what IT does. So this particular concept, that whenever you have fx dot f of 1 by x, if it is said to be equal to fx plus f of 1 by x, then don't hesitate in assuming fx as 1 plus minus x to the power n. Take it like that. And of course, with some more clues, some more data given to you, you can find whether plus or minus sign will come and what will be the value of n. That can be worked out with some data or information given to you. Moving ahead, what do we have next here? Exponential function. So yes, exponential function is basically of two categories. First of all, please understand, if let's say I take something like this to make you understand it more clearly. Here, let's say you have this. Let's say I am defining a function y is equals to 2 to the power x. So of course, you keep taking the different values of x, for example, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. And I hope you can see that the values are increasing exponentially. 2, 4, 8, 16, 32, 64. So they are growing exponentially. But what if I'm taking the base to be lying between 0 and 1? So let's say if I'm taking it as 1 by 2. So the question is 1 by 2 to the power x. So 0.5 to the power x. So if that is so, then if I start taking different values of x, so if I take greater values of x, for example, 1 by 2 to the power 1, then I take 1 by 2 to the power 2, then I take 1 by 2 to the power 3, then I can very clearly see that the values are constantly decreasing. Sorry, the values are exponentially decreasing. So if the base lies between 0 and 1, the graph decreases. If the base is greater than 1, the graph increases. So what if the base is 1? Then it becomes a constant function. Can we take the base less than 0? No, that is forbidden. So what you do is, you always take your base greater than 0. That's your first condition. That's your first condition. Second thing, base should never be 1. This also lays the foundation for logarithm if you are able to understand this fact. And then you divide it into two categories. First case, if the base is between 0 and 1. Second case, if the base is greater than 1. Again, if the base is between 0 and 1, the graph decreases. So we can try all the values of x from minus infinity to infinity, but the graph decreases. I hope you can see it as strictly decreasing. If the base is greater than 1, the function increases exponentially. So we can again try all the values of x from minus infinity to infinity, but the graph strictly increases. I hope you can see this. Here what you should notice is that the graph lies between 0 and infinity in either of the cases, here and here as well. The graph lies on the positive side of y-axis only. I hope you can see it very clearly. So if somebody asks you what is the range of the function, what is the domain of the function, you would say that, sir, domain of this function is all the real values, because it is true or exists for all the real values of x. But if you talk about its range, we'll say, sir, its range, the range of the exponential function, will be 0 to infinity because it lies on the positive side of x-axis only. So this is one of the ways of writing open intervals, and this is also another way of writing the open intervals. I hope you will remember that. Now, let us move ahead towards the next function, logarithmic function. So once you have understood exponential, that lays the foundation for logarithmic function. So let me make you understand this logarithmic function first of all. We had this 2. So let's say 2 to the power 3 was 8, right? So this is how you write the exponential function. So we said that 2 to the power x could be y. So inverse of exponential function is logarithmic function. What do I mean by that? What logarithmic function says is that if you take log of, let's say, 8 at base 2, so this means that 2 should be raised to what power so that it results into 8. So 2 should be raised to power 3 so that it will result into 8. So here we say that log x at base a is equal to y. I hope you are understanding that this is inverse of it. Here, I hope you're realizing that 2 cube is 8. And that same exponent form in the logarithmic form is written as log 8 base 2, which is 3. To make you understand log more clearly, I'll take one more example. Let's say if I were to give you log 1000 at base 10, what will be your response? Let's say log 10,000 at base 10. What does it mean? Would you not say that log 10,000 at base 10 means that what power should this base 10 be raised to so that it results into 10,000? So we all know that 10 to the power 4 is 10,000. So log 10,000 at base 10 is 4. Although if I wish to write in it exponent form, I'll be writing it as 10 to the power 4 is 4,000. Oh, sorry, 10 to the power 4 is 10,000. So what you need to understand is the relationship between logarithm and exponent. Here, please pay attention that here, what most of the students don't notice is that they ask questions. That, sir, if we already had it this exponent form, then why are we having the logarithm over here? Please understand, we know the exponents and then we can convert the logarithm. But what if I were to ask you that find the power of 2, which it should be raised to so that it can give you 10? So we know 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16. But what power should 2 be raised to so that it gives you 10? And that we don't have, and it is humanly impossible to figure out. So we will have to use certain methods to do it. So there could be a number, of course there could be a real number, but we don't know its exact value. So that value, let's say 2 is raised to a certain power and it results into 10. That value could not be found directly. So here we use logarithm. So here we say that if 2 to the power x is 10, we say log of 10 at base 2 will be x. It means that 2 should be raised to this power x so that it will result into 10. So if I'm asking you that what is the power of 2 which it should be raised to so that it gives you 10, that power is going to be x, which is log 10 base 2. Did you understand this part now? I hope you are comfortably understanding it very clearly. Now, if you have gotten that part, that exactly is what we'll be doing here. So log x, first of all, is an inverse function of a to the power x. Again, it will follow the same protocol, the same set of rule. Here again, if I'm having log x at base a, I'm supposed to keep this base greater than 0, which means positive. And additionally, this base can never be 1. Again, the way we divided exponent function into two categories, when base was between 0 and 1 and base was greater than 1. In the same fashion, log x will also get divided into two categories. So first case, when the base is lying between 0 and 1, and the second case, when the base is greater than 1. So when the base is between 0 and 1, your function is again strictly decreasing. And when the base is greater than 1, then your function is strictly increasing. Here, if I look at the domain of this function, now when you talk about log x, this x will be the values between 0 to infinity only. Because this is the value which you got by raising a number, the base to a certain power. So that number will always be positive. 2 cube, 2 to the power 5, 2 to the power minus 7, 2 to the power 7, 2 to the power 8, 2 to the power minus 10. Whatever you raise this base to power to, it should always give you a positive number. So that number has become an input here, the x here in logarithm, because it is the inverse of exponent. So here we know that this x will always be positive. So it should always be greater than 0. When it is the inverse function, the range of exponent function becomes the domain here. So I hope you remember the range of the exponent function was all the positive numbers. So here all the positive real numbers, which was the range of exponent, will become the domain of logarithm. Are you understanding it? So here, what I'll try to make you understand is that from 0 to infinity will be the domain of logarithm. But here, what you also need to understand is that the range is going to be from minus infinity to infinity, even if the base is between 0 and 1, or even if the base is between 1 greater than 1. In either of the cases, the range is going to be from minus infinity to infinity. That is all the real numbers. So I repeat, the domain of logarithmic function is set of all positive numbers and the range is set of all real numbers. Did you understand that part? Let us move ahead and let us move to the next part. I hope logarithm is making complete sense. Now we have moved or we'll talk about trigonometric functions. This is what we'll discuss in trigonometry as well, but let us have a look at this part here. So I'll begin with the first function, sin x. Sin x, very standard function, very straightforward function. So if I could draw the graph of sin x, it is a sinusoidal wave. So at 0, it passes through 0. On pi, it passes through x-axis. On 2 pi, 3 pi, minus 2 pi. So on all the multiples of pi, at all the multiples of pi, the graph passes through the x-axis. The graph intersects the x-axis. So for all the multiples of pi, sin x becomes 0. That is what you need to notice. And at all the odd multiples of pi by 2, it is going to be either 1 or minus 1. So if the multiple is of 4n plus 1 category, it is going to be 1. If the multiple is of 4n minus 1 category, it will be passing through minus 1. I hope these are some observations you can make. Now, here also, if you are noticing, sir, graph on x-axis can be traced from minus infinity to infinity, which will help you in understanding that the domain of the function sin x is going to be all the real numbers. But what if I were to tell you that find its range? What will you say? Sir, the graph is never going below minus 1 and above 1. It is always lying between minus 1 and 1. So it is attaining all the values between minus 1 and 1. That's why its range is going to be minus 1 to 1. If you have understood the function sin x, I think it's easier now to understand cos x, because if you shift it by pi by 2, then you will get the graph of cos x. So the same graph from minus infinity to infinity, but this time here, some more observations you need to make. Which observations? At all the multiples of pi by 2, so pi by 2, minus pi by 2, 3 pi by 2, 5 pi by 2, the cos x, the graph of cos x passes through x-axis. And of course, at the multiples of pi, it becomes either 1 or minus 1. So if you are talking about an odd multiple of pi, it will be minus 1. But if it is an even multiple of pi, it will be plus 1. Are you noticing these observations? Do take care of these things in mind. They'll actually help you a lot while solving a lot of questions. Here, what you need to understand is it was from minus infinity to infinity. So again, the domain is going to be all the real numbers. But here again, the function lies between minus 1 and 1 only. It never passes this range. So in that case, I'll say the range of this function will be from minus 1 to 1. I hope it is easily understood by you all. And if you have gotten this part, let us move ahead towards the next function, 10x. Now 10x has a problem. 10x basically is sin x upon cos x. So if it is sin x upon cos x, the problem is that the denominator cos x should not be 0. So the points where cos x was becoming 0 will create some problem for us, because these are the points minus pi by 2, 3 pi by 2. At all the odd multiples of pi by 2, we can see cos x to be 0. And if cos x is becoming 0 at all the odd multiples of pi by 2, I can see that the graph of 10x does not exist. It is not defined at those values. So that's why you need to understand from minus infinity to infinity, I can see its graph getting periodically repeated. The same graph is getting repeated time and again. So its range is going to be all the real numbers, which is true, which is definitely true. But if I talk about its domain, sir, I could see its graph from minus pi by 2 to pi by 2, but not at minus pi by 2 and pi by 2. Then again, between pi by 2 to 3 pi by 2, the graph was there, but it was not defined on pi by 2 and 3 pi by 2. So I will say, sir, domain is all the real numbers except for the odd multiples of pi by 2. Except for the odd multiples of pi by 2. Because at all the odd multiples of pi by 2, the graph became not defined. And these parallel lines to y-axis became asymptotes to this curve. Forget the concept of asymptote as of now. But what you need to understand right now is that yes, this is how you define the range of 10x, and this is how you remember the graph of 10x. So again, some observations. 10x becomes 0 at all the multiples of pi because it is basically having sin x in the numerator. 10x is sin x upon cos x. So whenever sin x becomes 0, 10x will also become 0. So at 0, pi, 2 pi, 3 pi, 4 pi, 10x will also become 0, and whenever cos x becomes 0, 10x will become not defined, which means at the odd multiples of pi by 2. So these are some basic observations which will help you in understanding this trigonometric functions. Along with this, we have cosec, we have sec, we have cot. This is what I'll explain you while we'll study trigonometric ratios, identities and functions, so don't worry about that. But of course, this is something which you need to remember when you talk about inverse trigonometric functions. Always remember, although we'll discuss it when we discuss the topic inverse functions, but do remember that when we talk about inverse trigonometric functions, the line y is equals to x, if you take the mirror image of a function with respect to this line, you create its inverse. What I'm trying to make you understand is, let's say we had a function sin x. We had a function sin x. I hope you could see that this is the graph of the function sin x, this one, which I'm drawing right now. So if this is the graph of sin x, and if I take its mirror image in the line y is equal to x, then I'll have its inverse. But again, inverse function has a problem when you talk about trigonometric functions. Trigonometric functions are periodic in nature. Periodicity brings many to one relationship. So if you look at a function, if you look at a trigonometric function, they are many to one. So all the trigonometric functions are many to one. I hope you're realizing my concern here. So if I look at the graph of sin x, and if I notice few things, for example, for multiple angles, I'll get 1. For multiple angles, I'll get -1. For multiple angles, I'll get 0. For multiple angles, I'll get 1 by 2. For multiple angles, I'll get root 3 by 2. So if it is many to one relationship, if it is a periodic function sin x, and if I take its inverse, it will become 1 to many. Then if the function becomes 1 to many, then it should not be said to be a function. It should be a relation now. But how can I ensure that it still remains a function? I can ensure it to, I can maintain it to be a function if I put some constraints on it. If I restrict it to a certain principal domain, I will ensure that the function, when its inverse is taken, does not violate the condition to be a function. What do I mean by that? See, the problem is, if I say, or if I ask you what is sine 30 degree, you will say, sir, sine 30 degree is 1 by 2. But the problem is 30 degrees is not the only angle which gives you 1 by 2. For example, if I ask you what is sine inverse 1 by 2, then you may say that's a 30 degree, and then there are infinite angles on which you will find 1 by 2 when you take the sine ratio of those angles. So that's the problem. So while taking the inverse, if I'm taking the inverse of a certain number or a value, then it should give me a unique value. That's the first very basic condition of a relation to be a function. But if it is not fulfilled, it will not be a function anymore. So if you are defining an inverse function, then you need to ensure that inverse trigonometric functions, for them to be defined as functions, you need to put a condition, you need to put a constraint, and that constraint is that you should restrict them to a certain domain. See, sin x was a periodic function. Sin x was a periodic function. It was getting repeated time and again, and it was making it many one. And when you take its inverse, it will become 1 to many, which will not let it become a function. So what we did was we restricted it to a certain domain. So I saw that between -1 and 1, this is the best zone. So if I take this chunk of this graph, so if I simply remove this part of the graph, and if I consider this part only, if I consider the part from minus pi by 2 to pi by 2 only, this part, and if I take its inverse now, its inverse can be taken, because now the function is 1, 1 and on 2, which means it's bijective. It's surjective and injective. So whenever the function is bijective, its inverse can be found. So in order to make a function invertible, it should be bijective. It should not be many one, it should not be into, because in that case, when you take its inverse, it will violate the condition of a function. So first of all, when you are willing to define a function, or basically when you're willing to take the inverse of a trigonometric function, you should restrict your trigonometric functions to a certain domain. then only their inverse can be taken. Because when you restrict those functions to a certain domain, to their principal domain, then you ensure that yes, they become bijective, they become invertible, their inverse can be taken. And that's the condition. For example, here, if I restrict sin x from minus pi by 2 to pi by 2, if you have restricted sin x from minus pi by 2 to pi by 2, as you can see here, this is the graph of sin x from minus pi by 2 to pi by 2. And if I take its mirror image with respect to the line y is equals to x, I can very clearly see that this is going to be the graph of sine inverse x. This yellow part is going to be the graph of sine inverse x. So whatever was there on the x-axis gets converted to the y-axis. Whatever was there on the y-axis as now appears on the x-axis. So previously we were taking angles on the x-axis, but in the graph of sine inverse x, all the angles will go on the y-axis. Previously, we were taking all the values on the y-axis, all the values of sin x. Now they'll appear here on the x-axis. So previously, sin x had a range -1 to 1, which was there on the y-axis. But for sin inverse x, this -1 to 1 will now appear on the x-axis. I hope you can see for the graph of the sin inverse x, I can see its graph lying between -1 and 1 only. Previously for sin x, we had angles on the x-axis, but now that principal domain from minus pi by 2 pi by 2 will appear on the y-axis. So if you look at the graph of sin x, if you look at the graph of sin inverse x, the range now becomes minus pi by 2 to pi by 2. Because inverse function, I hope you are realizing the concept now. For inverse function, whatever was the domain of sin x, the principal domain is becoming the principal range, and whatever was the range of sin x has now become the domain of sin inverse x. And if you are asked to draw the graph of inverse function, you can always take the image of that function with respect to the line y is equals to x, and through that you can draw it. Third condition which you should remember or take care of is that if there is a function whose inverse you are supposed to take, then it should be invertible. What is the meaning of a function to be invertible? It means the function should be bijective. What is the meaning of being bijective? That means the function should be 1, 1. It should not be many 1. That means the function should be onto. It should not be into. What is 1, 1, many 1, onto and into? That is exactly what we'll discuss further. But at this stage, while discussing inverse trigonometric functions, this is something which was needed to be discussed. And I am hoping that through this, you will remember its graph. Let us move ahead. Let us go further. Let us discuss something else. So sine inverse x is exactly what we have discussed so far. Now, if I talk about cos inverse x, now I'll straight away give you the graph. So the graph of the cos inverse x lies between -1 and 1 on the x-axis. I hope now you must understand the reason. And if you look at its principal range, it is going to be 0 to pi. So for sine inverse x, we took minus pi by 2 pi by 2. For cos inverse x, we'll take it from 0 to pi. Moving ahead, if I talk about tan inverse x is again a beautiful example here. If you look at its domain, so range of tan x was minus infinity to infinity, so that will become our domain now. So the graph is existing from minus infinity to infinity. That means it is going to be its domain. So its domain is going to be all the real numbers. But now if you look at its range, so there were many branches of this tan x function because it was periodic. So I'm choosing the branch which was there between minus pi by 2 to pi by 2. So that branch of tan x is now becoming the range minus pi by 2 to pi by 2 of the function tan inverse x. So here the range of tan inverse x is going to be minus pi by 2 to pi by 2 open interval. Did you get that part? I hope there is no confusion on that. Let us move further towards the next set of inverse functions. Cot inverse x, cosec inverse x, and sec inverse x, don't worry about them. I'll explain them when we discuss the chapter inverse trigonometric functions. We'll discuss these concepts in more detailed format with a lot of properties and a lot more details there only. So here comes a question. This is a question on the domain of a function, right? There are two things in this question. First, logarithm based question, whose domain is what we are willing to figure out, and a sine inverse based question. How do we deal with it? Once you have done this part, the rest of the question is simple. How do we do it? Let's focus on this part first. Fx is given something like this. Okay. It is given as log of, right? So 3 logs are there. Let me write it on a different page. So here we have log 4, base is 4. Then inside this, we are taking log 3, base is 3 basically, then log at base 7, and then we have this 8 minus of this 8 minus, again we have log of log of something quadratic, I believe x square plus 4x plus 5, something like that only. Yes, at base 2, right? So that's your question. Great. So this is what I think we are given as fx, and I need to find its domain. Simple question it is. Again, if I'm solving it, most of you can also start attempting it by the time I'm also solving it. What do we know about logarithm? We have discussed that when you talk about log x at base a, there is something related to this base a, that this base a should always be greater than 0 and this base a should never be 1. But in all the cases 4, 3, 7, 2, so the problem is not the base. But here we know that whenever you define log, then this value whose log you are taking should always be positive. This is a constraint we know. So if that constraint needs to be imposed here, I'll say initially we are taking log of this. So this expression, this expression, its log is being taken. So this should be positive. So if I put a positive sign here, this means that this expression should be positive. So that's my constraint inequality or condition through which I'll work on its domain. Did you get that part? I hope there is no confusion. Now, how do you take NT-log? So I hope you remember that, let's say if I'm given log, let's say m at base a greater than 0. So I can write it as m greater than a to the power 0. This is how you take NT-log if your base a is greater than 1. But if the base is between 0 to 1, the sign of the inequality changes. This is a property based on inequality which you deal with. So if I could apply this particular property over here, the NT-log when taken, so log of this, I hope you can see it very clearly, log of this at base 3 is needed to be taken. So if this NT-log is taken, that this 3 is raised to the power 0. The base 3 over here is greater than 1, so the sign of the inequality wouldn't change. So here I'll say that if this 3 goes to the other side, I'll write it as 3 to the power 0. I hope there is no confusion on it. So I will write it as greater than 3 to the power 0, and 3 to the power 0 we all know is 1. I hope there is no confusion on it. Again, I'll take NT-log from here. So if I now am taking an NT-log, I was supposed to keep this also positive because this was inside a log. And I am wanting to keep this as positive, but this is already greater than 1. So should I bother about this expression being positive? Because basically I was taking log of this expression. So this expression also should be positive, which means this expression should be greater than 0. But as per this condition, this expression is already greater than 1. So I need not be concerned about this expression being positive, because if it is already greater than 1, it will be positive. So that condition I need not impose additionally. I hope you're understanding the reason. So with that, 7, again I'll take NT-log. So 7, log of this at base 7 is greater than 1. So again, if I'm taking NT-log, what will happen here? This 7 will be raised to the power 1. So 1 to the, I hope you're understanding, 7 raised to the power 1 is what I'll have here. And 7 raised to the power 1 is nothing but what? 7 only. I hope there is no confusion on it. Everyone comfortably understanding all of which we are discussing. Now, if I remove this bracket and take this 8 on the other side, what will I have next? I'll have log of x square plus 4x plus 5 at base 2 greater than 7 minus 8, which is minus 1. I hope there is no confusion on it. Now, again, if I'm taking logarithm, if I multiply both the sides of this inequality by negative sign, the sign will change. The sign of the inequality gets changed if you are multiplying both the sides with the negative sign. So here, if I am multiplying both the sides with the negative sign, this sign and this sign will get inverted. So this will become less than 1. I hope there is no confusion on it. Again, the next constraint, the next condition will be that this expression's log is what we are taking. So if I'm taking log of this expression, then of course, first check, this should be positive, this should be greater than 0. Okay, I'll talk about that later. But again, if I'm taking logarithm here of this expression, and if I wish to take NT-log on this inequality, then this 2 is raised to the power 1. So here, I'll have this expression as x squared plus 4x plus 5 to be less than 2 to the power 1. And what is 2 to the power 1? 2 to the power 1 is 2 only. But the check, the final check, what is it? Here, we were taking log of x square plus 4x plus 5. So if we were taking log of x square plus 4x plus 5, which means this should be greater than 0. Because we have had a discussion on this, that if you're taking logarithm of this, then it should be positive. It should be greater than 0. I hope there is no confusion on this front. You're able to understand and digest everything which is said so far. Now, two things I'll work upon. First of all, I will look at this quadratic. X square plus 4x plus 5. If this is a quadratic, can you help me with its discriminant? Its discriminant is given by b square minus 4ac. So 4 into 5 is 20. So 16 minus 20. B square is 16 minus 4ac is minus 20. And we can see that its discriminant is negative. And we know if the coefficient of x square is positive and if the discriminant is negative, then this quadratic is always positive for all the x which are real. Do you remember this? Do you remember this discussion we had previously? I hope you remember. The graph of this quadratic will be an upward facing parabola and it will lie above the x-axis because its discriminant is negative. So on the basis of this, can I not say that yes, that if I was concerned about x square plus 4x plus 5 to be greater than 0, it will be greater than 0. I need not worry about that. So that condition, if I was concerned about, that is checked here. So now, for all the x, it will be greater than 0. So I need not worry about it. So my concern will be solving this part. Which part here, students? The part where we say that x square plus 4x plus 5 should be less than 2. So whatever is the answer to this question will be the domain of our first part of the question. So here it is x square plus 4x plus I think 3 less than 0. 5 minus 2 is 3. Now 4x can be splitted as 3x plus x. I hope you are understanding why. So it is going to be x square plus 3x plus x plus 3 less than 0. Now, if I wish to factorize it, the factorization will be x plus 3 will be one of the factors. I hope you are seeing it very clearly. The other factor will be x plus 1 and this should be less than 0. I hope there is no confusion on it. And as per the wavy curve method, I hope you must remember, we have had a discussion on this, that if this quadratic is needed to be negative, then it is negative between its roots, and its roots are minus 3 and minus 1, minus 3 and minus 1. So from here, I have gotten the domain of this part, which is open interval minus 3 and minus 1. We are told that its domain is alpha to beta. But as per our discussion, as per our calculation, this is found to be minus 3 and minus 1. So from here, I think I have the value of alpha, which is minus 3. I have the value of beta, which is minus 1. So are you understanding how are we solving questions based on domain? How are we dealing with inequalities? How you should take care of everything? Now, let us get back to this part. Sine inverse of 7x plus 10 upon x minus 2. I need to find this domain as well. So let's start solving sine inverse of 7x plus 10 upon x minus 2. Okay. So in the numerator, we have 7x plus 10 and in the denominator, we have x minus 2. So we are now looking forward to get the domain of this function. How do I begin with this part? I'll simply say that what we know that this expression, the value whose inverse, sine inverse we are taking, that value should always lie between minus 1 and 1. I hope you remember, for the existence of sine inverse of x, that x should lie between minus 1 and 1. I hope you remember this discussion we had while discussing inverse trigonometric functions. So here, would I not say that if I am talking about its domain, I'll be concluding that here, for the existence of this function, this value 7x minus 10 upon x minus 2 should lie between minus 1 and 1. Did you get this part? So I'll convert this question into two branches. Which two branches? First branch when this is greater than minus 1. Second branch when this is less than 1. And then I'll take the intersection. Why will I take the intersection? Because this and this, both of them should be satisfied. So if I begin with the first part, what is the first part? The first part says that minus 1 should be less than 7x plus 10 upon x minus 2. And means whatever answer I'll get from here and whatever answer I'll get from there, the second part, I'll take the intersection of those answers. So, and I need to ensure that 7x plus 10 divided by x minus 2 should be less than 1. Did you get this part? Any confusions on that? Now, if anybody is thinking that, sir, this x minus 2 can be multiplied here, then you are wrong. Because in inequalities, you don't do this cross multiplication thing. So what should we do then? We'll take this minus 1 on the other side. We'll take this 1 on the other side. How? Have a look at this. So here I'm writing 7x plus 10 in the numerator divided by x minus 2 and minus 1 if goes to the other side, it becomes plus 1. And this expression will be greater than 0 now. Along with this, here I can write it as 7x plus 10 upon x minus 2 minus 1 should be negative. Did you understand this part now? How are we solving this inequality? Let's work on this result. So here we have 7x plus 10 plus x minus 2, right? So 7x plus x should be giving us 8x, and the next result is 10 minus 2, that is clearly plus 8 whole divided by x minus 2 in the denominator. And this expression is given as positive. So this is needed to be positive. And along with this, what is the next result? 7x minus x. It is going to be, I think, 6x. So let me write 6x here. Then the next point is 10 plus 2. I hope you are realizing my LCM is what I'm doing here. So 10 plus 2 is going to be 12. So the numerator will have a 12 here. And that too divided by this expression, x minus 2 in the denominator. And this expression, I think, was supposed to be kept negative. All right, great. So we have these two inequalities. We need to solve them. I think wavy curve method will be the most appropriate method again. So here, if I look ahead, if I take 8 common, I'm left with x plus 1. I'm left with x plus 1 upon x minus 2. And this is needed to be positive. And if I look at this part, if I take 6 common, I'll be left with x plus 2 upon x minus 2. And this is needed to be negative. I hope there is no confusion on this front. Now, let me solve this part. If I solve this part, I hope you know that through wavy curve or through your intuition only, you could say that this is a quadratic. This is like a quadratic only, where two factors are x plus 1 and x minus 2, and you want this quadratic to be positive. So quadratic is found to be positive beyond the roots. So before the smaller roots and after the greater roots, it is found to be positive. And here the quadratic is supposed to be negative. It can be treated as a question on quadratic where the factors are x plus 2 and x minus 2. So quadratic is found to be negative between the roots. I hope you remember that. So here in this case, you need not even apply that wavy curve method. Yes, this generalization is remembered by you. That also can be applied here. So here the roots are going to be minus 1 and 2 and plus minus plus. What do we need? Plus. So plus is happening before minus 1 and after plus 2. That's exactly what I was saying. Here if you apply wavy curve, here you will apply wavy curve. It is minus 2 and 2 plus minus plus. So we need it to be negative, which is happening between minus 2 and 2. I hope you have understood this part. Now, what I'll do is I'll take their intersection because this and this, both of them should be satisfied. If both of them are supposed to be satisfied, I'll be taking the intersection. So when you move towards taking the intersection, what do you have now? So I'll draw the number scale. I'll plot these numbers. So the smallest number among them is minus 2. Greater than that is minus 1. And then beyond that is 2. Now, let me draw this. It says it should be either less than minus 1 or greater than 2. Fine, that's brilliant. What does this say? It says that it should be between minus 2 and 2. So the other part says that it should be between minus 2 and 2. So it says it should be between minus 2 and 2. So now if I look at the intersection part, the intersection lies here between minus 2 and minus 1. Did you get this part? So it should be there between minus 2 and minus 1. So from here, the final intersection turns out as minus 2 and minus 1 open interval. It should again be minus 2 to minus 1 open interval. Let me get back to this part. Here it says open interval minus 2 to minus 1, but it is given as closed interval. So let's find it out whether it should be open or closed. A very simple, silly mistake I committed. We know that sine inverse for 10, I would say minus infinity to infinity, and there I could have used open brackets, but for sine inverse, I should have used closed interval because sine inverse lies between minus 1 and 1, where minus 1 and 1 are included. Mistakenly, I forgot taking care of it. So this minus 1 and 1 will also be there, and then this equality sign will also be there. So when this is there, let me just keep correcting it. The equality sign will be here as well. The equality sign will be here as well. So now, instead of treating it as a quadratic, let me make those corrections here. So please be very much vigilant. This is an opportunity to learn something new and interesting. What is that? Please understand. Here, I hope you're realizing I can include minus 1 because x minus 1 is there, x plus 1 is the numerator. So minus 1 can be included, but still 2 need not be included. 2 cannot be included because 2 is there in the denominator. I hope you're realizing it. Here, I could still include minus 2. I hope you're realizing it here because minus 2 was there in the numerator because minus 2 is still satisfying our inequality. But here again, I cannot include 2 because x minus 2 is there in the denominator. So this is excluded. So finally, if I club it, here it says minus 1 to 2, sorry, minus 1, less than minus 1 or greater than 2. So less than minus 1 where minus 1 is included, but 2 is excluded. It said minus 2 to 2 where minus 2 was included, So yes, there is a small correction. I'm really sorry for that. It should be between minus 2 to minus 1, including all these values. So instead of using an open interval, the correction should be, it should have been a closed interval. So the correct answer will be minus 2 to minus 1. Did you get that part? So if I get back to the conclusion we had drawn here, it should be between minus 2 to minus 1. So gamma and delta will lie between minus 2 and minus 1. And that's how we have found the values of gamma as well and delta as well. So gamma is minus 2 and delta is minus 1. Now, after working out this result, I think it's easy to figure out the answer because alpha square is basically 9. What is beta square? Beta square is 1. Then you have gamma square is 4. And then you have delta square, which is 1. So 9 plus 4, 13, plus 2 is 15. And on the basis of that, option A goes marked correctly. Did you understand this part? Any confusions on that? Now, let us move ahead and let us understand the next few set of concepts. But I hope this excellent example gave you a complete clarity that how should you deal with questions based on domain. Now, we are moving towards the next category of functions which are treated or called the piecewise functions. Now, what is it? Look at the first category of those functions, absolute value function or modulus function. Now, how do you define it? You write it as mod x. It is x as long as x is non-negative. When it is minus x, there is a correction here. It is minus x as long as x is negative here. So I hope you can see that the line y is equals to x is drawn like this for all the non-negative values of x, and the line y is equals to minus x passes through origin and drawn like this with an inclination of 135 degree with the positive x-axis, and it is drawn like this for all the negative values of x. Did you get this part? Now, the next part. So this is how you define it. What is the meaning of it? For example, let's say I'm taking a mod of minus 5. So we all know we need to take the absolute value, the numerical value of the number here, which is 5. But how do we get this 5? This 5 is attained by taking negative of minus 5. So why did I take the negative minus 5? Because the number written inside the mod was negative. So whenever it is negative, you take the negative of that number. But what if the number is non-negative? Let's say 3. So we know that mod of 3 is 3. Why? Because this number which was written inside the mod was positive, or rather it was non-negative. So if it is non-negative, I'll take the number as it is. I hope you'll remember, as per the very basic definition only, I'm defining the modulus function. Remember this definition, it is very useful in continuity, differentiability, and even differentiation. Do remember it. Even in integration, this definition will be more useful. So do take care of it. Of course, we all understand the application of modulus, the phenomena of modulus, the way modulus works, the operator. But do remember this definition. It is also very useful along with its graph. Because we know when we talk about its continuity, it's continuous from minus infinity to infinity. But if you talk about its differentiability, it is non-differentiable at 0 because at 0 it has a sharp turn. Although we'll talk about this when we discuss the chapter LCD. What you need to remember is that this chapter function lays the foundation of your entire calculus. The chunk which is considered to be the most important chunk of your entire mathematics. When you talk about algebra, coordinate geometry, trigonometry, vectors in 3D or calculus, calculus plays the huge part, the most important chunk. So if you are on the verge of starting the calculus, this is the chapter which you start with, the functions. And functions, the better understanding you have on functions, the better chances are that you will be able to understand the other chapters. So do put your complete focus on this chapter when you are understanding the concept of modulus function, right? So I hope it makes complete sense. So if I were to talk about its domain, we know its domain will be all the real numbers because the graph can be traced on the x-axis from negative infinity to positive infinity. So it exists for all the real values of x. But what if I ask its range? So we know that the graph of this function was found from 0 to infinity, including 0. So its range would have been all the non-negative values. So here, this is how you define geometrically this, that it is treated in a sense of distance, which is as of now at this one short video is not very much useful. Let's learn this particular property, these particular property, out of which this second one we have had already discussed. Always remember, under root over x square is not x, it is always mod x. what you need to remember is that if I am taking under root over under root over, let's say minus 2 square. So most of you may end up writing minus 2, which is wrong, which is mathematically wrong. It should be written as mod of minus 2, which is basically 2. So do take care of this, that under root over x square is not x. It is always mod x. I hope you're understanding why. If you end up doing this, you're committing a mathematical error. If you write it like this, then you're proving that 2 and minus 2 are equal. Because minus 2 square will be what? 4. And under root 4 is 2. So if you say that this is minus 2, I'll say this is 2. And 2 and minus 2 are equal as per that logic, which is mathematically incorrect. Do remember this as a result. I hope you remember, whether I take mod of mod x or mod of minus x or mod of x, it will remain same, because modulus is like what? It gives you the absolute value. So once you have already taken the absolute value, what is the point of taking absolute value again? So no matter how many times you apply a mod on it, applying it once is also sufficient. I hope you're realizing why. Similarly, whether you take x square or whether you take mod x square, they are interchangeably used and they are very useful. So sometimes you're given some quadratic or biquadratic, and there I'll use this property that I may use x square as mod x square, because they'll be same. I hope you're realizing, whether you take the square of a number or you take square of its magnitude, square of its mod, it will be same. Are you realizing why? So remember these three results, they are very crucial. They are used in a lot of questions, and students are prone to commit errors based on these results. Do remember these results. They are very useful as far as properties of modulus function are supposed to be remembered by you. Let us move to the next part, which is called signum function. What is signum? On the basis of modulus, the foundation of signum is laid. What is it? Please understand, signum function says that it is always mod x upon x as long as x is not 0. But if x is 0, it is 0. What is mod x upon x? We know mod x upon x will be either 1 or minus 1. Why? Because whenever x is positive, this will be x upon x, which will be 1. But if x is negative, it will be minus x upon x, which is minus 1. Are you realizing it? So as long as x is non-zero, it will be either 1 or minus 1. But if x is 0, it will be 0. So this is how you define this signum function. I hope you are understanding the piecewise functions. What is the meaning of piecewise functions? They are defined piecewise. So for certain values, it is minus 1. For certain values, it is 0. For certain values, it is 1. So piecewise definition is given of this particular function. So this is called signum of x. Did you understand this part? And if you have understood signum of x, this is how you draw the graph of signum of x. Why? Because for all the negative values of x from minus infinity to 0, where 0 is excluded, it is minus 1, constant function. But at 0, it becomes 0. And for all the positive values of x, which is 0 to infinity, where 0 is excluded, positive, so it will be plus 1. So this is how you draw the graph of signum function. As you must have seen that this is again a function which has domain from minus infinity to infinity. Because at 0, it becomes discontinuous, because the graph goes like this. It breaks, it takes a jump, and then it continues. But at 0, the graph is discontinuous. Again, despite being discontinuous, I can see the graph having its existence from minus infinity to infinity on the x-axis, which means its domain will be all the real numbers. What about its range? I hope most of you must have noticed. Maybe its domain could be all the real numbers, but when you talk about the range of the function, it has only three values: minus 1, 0 and 1. Because for all the negative values, it is minus 1. For 0, it is 0. For all the x which are positive, it is plus 1. So the range will contain only three numbers: minus 1, 0 and 1. Did you get that? Now, if I go ahead with the greatest integer function, very simple, very straightforward function, but it is used at a lot of places. In differential, indefinite integration also they use it. They love using it there as well. We'll see an example there in that chapter only. But as of now, if I could explain you GIF and its properties, that will be more useful here at this stage. What is GIF? Most of you must have seen it like this, that let's say if I'm taking the GIF of 3.5, then you should take the integral part here. So it is going to be 3. But that's not absolutely true, because when I'm taking the GIF of minus 4.7, then you don't say that the integral part is minus 4. No, that's wrong. The integral part here is minus 5. Now, why is it minus 5? If you look at the definition, what does the definition say? Definition says that look at all the integers which are less than or equal to this given integer and choose the greatest integer among those integers. So if I look at 3.5, what are the integers which are less than 3.5? It could be 3, 2, 1, 0, minus 1 and so on. Which is the greatest among them? 3. That's why GIF of 3.5 is 3. look at all the integers which are either equal or less than minus 4.7. So minus 4.7 numbers line. I hope you're able to imagine. If you're imagining, let's say on the number line, we have minus 4.7 here. So on the left of it, we'll have minus 5, then we'll have minus 6 and so on. So the integer which is greatest among all these integers is going to be minus 5. And that's why the GIF of minus 4.7 will be minus 5. Did you get that part? If you are able to make some sense out of it, here are some more examples. Always remember that the GIF of any number lies between two consecutive integers. Of course, it will be less than or equal to the number, and of course, it will be less than the next integer. So there, it should have been GIF. It should have been a GIF of x. Here, let me try and make you understand its graph. It looks like a step function. It looks like a stair. Why do we call it step function as well? Because see, for all the values between 0 and 1, 0, 0.1, 0.2, 0.3, 0.9, 0.999, the GIF will be 0. For all the values between 1, 1.1, 1.2, 1.3 like that, the GIF will be 1. For all the values like 2, 2.1, 2.2, 2.3 until 2.9, the GIF will be 2. Similarly, for all the values between minus 1, then 0.0, I hope you are realizing minus 0.9, minus 0.8, minus 0.7 up to minus 0.1, the GIF will be minus 1 and so on. So here, the values of x for a particular integral part will be there, keep on changing, but the value of GIF of it will remain constant. So I hope you're realizing its graph where this is the values, these are the darkened circle which they are containing or which they are holding true, but these are excluded. These values are not included. I hope you're understanding why. Because until 1.9, the GIF will be 1, but as soon as it becomes 2, the GIF will be 2. It will not be 1. Did you get that part? So on the basis of it, the graph is drawn. Again, GIF function is discontinuous at all the integral values. As you can see, minus 2, minus 1, 0. At all these points, the function breaks, the graph breaks. But still, you must be noticing that I can still trace the graph on the x-axis from minus infinity to infinity, which means if I were to define its domain, it is true for all the real numbers, which means you can take the GIF of any real number. Getting it? Along with this, if I talk about its range, so if I trace the graph of this curve along with y-axis, I'll say that I am finding the graph on the integral points only, minus 3, minus 2, minus 1, 0, 1, 2, because between these integral values, the existence of graph is not there. So I'll say the range of the graph is all the integral values, the set of all the integers. Did you understand this part? Let us move ahead. Let us understand some properties. I'll begin with this part where, let's say I'm given a number. So that number will always lie between its GIF and plus 1 of its GIF. What does it mean? Let's say, I'll just give you an example here. Let's say I have a number 3.5. What is its GIF? Sir, its GIF is 3. So 3.5 will always be less than equal to 3, greater than equal to 3, and it will always be less than 4. Let's say if it is 4. So 4's GIF will be 4 and it will be greater than equal to 4 and it will be less than 5. So I hope you're understanding this particular property. In the same fashion, this property can also be proved. It is not huge in a sense. Here, if there is a number and its GIF, I think these are the same properties. I think I need not explain it. This is the same which we have studied in mod. If you have taken the absolute value of a function or a number, then you need not take its absolute value again. The same logic can be applied here. So GIF applied once will give its integral part. Now, no matter how many times you keep taking its integral part, that will remain same. For example, if I'm taking the GIF of 2.5, so at this innermost stage only, the GIF of 2.5 will be 2. So does it make any sense that I take its GIF twice? Because the GIF of 2 will be 2 and the GIF of 2 will be 2. So I can write the GIF of 2.5 as GIF of 2.5 only. The way we were looking at it in terms of modulus sign as well. The same logic can be applied or learnt or thought here in this scenario as well. Here are some more properties. Look at this and remember it. This is a very useful one. It is something, these are the ones which are used at a lot of places. So I'm requesting you that you do take note of them and you do remember them. The first one of them is going to be very clear and very simple. GIF of x plus GIF of negative of x. So if there is a number and you take the negative of it and then you take their individual GIFs and then you add them. Always remember it will be either 0 or minus 1. It will be 0 as long as x is an integer, because if x is an integer and negative of it, it will be 0. But if x is not an integer, let's say 3.5. So 3.5 will have GIF 3, but the GIF of minus 3.5 will be minus 4. So 3 minus 4 will be minus 1. Did you understand this part? In the same fashion, these other properties can also be proved, learnt, or discussed. More importantly, these are the two most important ones based on GIF, which you should remember. So I hope you are taking notes of all these and you will remember it. The next one. This is also we will love to use at some places. This is something which you should take care of. Let's say I'm given a variable plus an integer and I need to take its GIF. So the beauty here is that you can take the integral part out. You can take the integral part out. So you can write it as GIF of x plus 10. Did you get my part? So whenever there is some integral part there inside the GIF sign, and you have identified that it is an integral part, you can skip it, you can remove it, you can take it outside. Skipping means keeping outside, and you can deal with the GIF of that unknown part only. Are you understanding the definition here, the formula here? In the same fashion, these are some basic observations which you should remember. If I could directly exemplify them through some examples, then please understand. Let's say I am told that find the GIF of x, find all x for which GIF of x is less than, let's say, 3. What will you say? So here I'm looking for those numbers whose GIF when taken gives you a number less than 3. So of course it is going to give you an integral part. So I am looking for all the integers which are less than 3. So any integer which is less than 3 is basically 2, 1, 0, minus 1 and all that. So I am looking for all those numbers whose GIF is less than 3. Now try and imagine or keep a number. Let's say, can I keep 3.1 here? Because if I keep 3.1, its GIF will be 3. Is 3 less than 3? No. So I cannot take any number greater than 3. I hope you understood it. Can I take 3? No. Can I take 2.9? I can definitely take that because 2.9's GIF will be 2 and is 2 less than 3? Yes, it is satisfying our condition. So from here, I can conclude that if you are wanting to say that x, the GIF of x is less than 3, then you need to take all the values of x which are less than 3, but not 3. So I'll be taking all the values which are less than 3. From where? From minus infinity, because all the values which are less than 3 are basically what? Minus infinity to 3, open bracket. 3 is not supposed to be included. Did you get that part? Any confusions on that? Now, moving ahead, let's say I take one more example. Let's say here I say that GIF of x should be greater than or equal to 5. Now, what do you say? Of course, it does not make any sense that I take 4.9 because if I take GIF of 4.9, 4.9's GIF will be 4. Is 4 greater than or equal to 5? No. So I think I need to take numbers greater than 5. Can I begin with 5? I think I can because the GIF of 5 will be 5 and here equality sign is given there. So 5 is equal to 5, that is included. So I'll begin with numbers such as 5, Can I take numbers greater than 5? Yes, 5.1, 5.2, 5.3, 6, 6.1, 6.9. They'll have their GIF as 5, 6, 7, 8, 9. And yes, they are greater than 5. So yes, all the numbers which are greater than 5 can be included. So whenever questions are there given to you based on inequalities of GIF, applied on GIF, then this is how you deal with them. I'll always suggest try with some numbers rather than learning or remembering any formula. Being logical is more important than mugging up or creaming things. Because something which you have mugged up may go wrong because you may forget it, may use it incorrectly. But if you have understood something more logically, the chances of you applying it correctly are high because you have understood it logically. Then you will be able to apply it because you know the reason, you know the logic behind it, and that's more important. Right. Now, moving ahead towards the next properties, there comes another function which is called fractional part function. Before I explain this fractional part function, I'll try and give you an example. Let's say we had a number 3.5. So what I did was I took its integral part. What was its integral part? Sir, the integral part of 3.5 was 3. But what was its fractional part? So apart from 3, what was there? Sir, apart from 3, something which was left there was 0.5. I hope you're understanding my motive, my intent very clearly. So all the numbers in the world, all the real numbers in the world can be represented as a sum of their GIF and their fractional part. So whenever I'm asking you to find the fraction part of a function, what you'll do is you'll subtract the GIF of that number from that original number. Did you get my definition here? My definition is pretty simple here, that I am saying that any number, any real number in this world can be written as a sum of its GIF, its fraction part. So whenever I'm asking you to find the fraction part of a function, you will say that it is written as x minus GIF of x. Did you understand that? Now, if I were to ask you to find certain values, for example, can you help me with the GIF of 1.7? What would you say? You will say, sir, sorry, not GIF, fraction part of 1.7. You will say, sir, from 1.7, subtract the GIF of 1.7. So from 1.7, if I am subtracting GIF of 1.7, GIF of 1.7 is 1. So 1 minus 1.7 is 0.7. So yes, the fraction part of 1.7 is 0.7. Some of you again might say that, sir, for fraction part, this decimal part is needed to be taken. Again, you're wrong. You are absolutely wrong. Because please understand, had this been the definition, why would I not tell you the basic definition? Why would I unnecessarily complicate it? So if I'm telling you a different definition, there must be some reason or logic behind it. So the logic is pretty simple. Let's say if I'm asking you to find the fraction part of minus 3.2. What was the definition? The definition was from this original number, subtract its GIF. Subtract its GIF. I hope you're getting it. From the original number, subtract its GIF. So from the original number, minus 3.2, if I subtract its GIF, what is the GIF of minus 3.2? It's minus 4. So minus of minus 4 is plus 4 and it gives you 0.8. So I hope all the concepts must be vanished when you think something like this. So don't conclude that whatever is written as the decimal part will be the fraction part. That's wrong. That's wrong. So the fraction part of minus 3.2 is 0.8. So most of you must have understood this thing very clearly, that fraction part always lies between 0 and 1. And if you draw its graph, its graph is drawn like this. For all the values between 0 and 1, 0.1, 0.2, 0.3, the fraction part will be 0.1, 0.2, 0.3 only. If I look at the values between 1 and 2, 1.1, 1.2, 1.3, their fraction part will be 0.1, 0.2, 0.3. So this graph stays between 0 and 1 in terms of y-axis. But on the x-axis, you can trace it from minus infinity to infinity. So again, if I look at its domain, if I were to ask you its domain, you will say, sir, I can trace its graph from minus infinity to infinity, which means its domain is all the real numbers. What about its range? You would say, sir, we can see the graph lying between 0 and 1, but 1 is not included because you can never have a number whose fraction part is 1. It will always be less than 1 and it will always be greater than 0. Which means if I'm asking you the range of fraction part function, then it is always between 0 to 1, where 0 is included and 1 is excluded, as you can see through its graph. And again, this is discontinuous at all the integral values of x. I hope you must be realizing it. So again, as GF, fraction part is also discontinuous at all the integral values of x. Did you get that part? Moving ahead with the next conclusion. This is something which you need not remember. If you have understood the graph, you will be able to remember all of these things very clearly. So yes, this is something which is of course very much useful. Even in definite integration also we'll use this property. And this is something you should remember, that whenever x is between 0 and 1, fraction part of x can be treated as x. So do remember this as a property. And yes, if x is an integer, it does not have any fraction part. Because if x is an integer, its fraction part will be 0, because its integral part will be that same number only. I hope you're understanding the logic very clearly, very easily here. Now, when I move ahead towards the next set of properties based on FPF, fraction part function, this is it. Negative of the fraction part of negative of a number is equal to 1 minus negative of fraction part of that number, as long as x is not an integer. This can be proved by taking an example. Let's say I'm taking fraction part of, let's say, minus 3.2. So I can call it 1 minus fraction part of 3.2. I hope you must have remembered it very clearly. So fraction part of 3.2 is 0.2. 1 minus 0.2 is 0.8. And I hope you must be able to recall this is exactly what we have discussed. So remember it. Always remember, fraction part was a periodic function. It was repeating itself after a certain period, 1 unit. So that's when you need to understand that x plus minus integer, if you are taking its fraction part, it will be equal to the fraction part of x only. Here, what I'm trying to make you understand is, let's say 0.2 plus, let's say 3, and you are wanting to take its fraction part. So whether you take the fraction part of 0.2, 1.2, 2.2, 3.2, 4.2, its fraction part is going to be 0.2 only. That's the advantage of periodicity. And that's what I'm trying to make you understand, that if it has an integral part, that again can be skipped, and you can just simply write the fraction part of 0.2 only, which is 0.2. Are you understanding this part here? Is there any confusion on that front? Now, similarly, the way we have understood GIF and FEF, you have this least integral function as well, which we can skip at this stage, which is not very much useful as per your syllabus right now. Let us now move to the next category of functions. These are the properties of least integer function. So I think the most important chunk, the major important chunk, the standard functions, the piecewise functions and trigonometric functions and all that, logarithmic functions, major functions we have covered so far, and domain is also, I think, very well understood by you all. I am very sure of that. Now, when you talk about range of a function, then how do you deal with the range of a function? What are the different methods? And how should you solve questions based on finding the range of a function? That's exactly what we'll discuss in this particular part. So first of all, again, I'll begin with this part, that how do you find domains? How do you find range of different set of questions? So first set, if domain contains finite number of points, range is the set of corresponding fx values. What I'm trying to make you understand is, let's say there is a function fx which is given by x plus 2. And here we know that it is a strictly increasing function. This is what we'll discuss in AOD. And let's say I am defining the domain of this function as the values between -2 to 2. So it has finite values. So if I could find its minima and maxima, that will be the range of the function. So if you are asking the range of this function, I'll say, since it is a strictly increasing function, so at the lowest value of x, I'll find its minimum value. At the greatest value of x, I'll find its maximum value. So if I put -2 here, -2 plus 2 will be 0. And if I put 2 here, 2 plus 2 will be 4. So the range of this function will be 0 to 4. Did you understand it? Although this will be true only when this is a strictly increasing function. If it was a strictly decreasing function, then it would have been opposite of it. At -2, I would have found the greatest value. At 2, I would have found the least value, if they are strictly increasing or decreasing. But if that is not the case, let's say the function goes like this. Let's say the function goes like this. This is the domain of the function. Let's say this is the domain of the function. So function holds its value from this point to this point, from this point to this point. Let's say alpha and beta. These are the 2 points between which the function lies. So you won't say that if alpha and beta are the extremities of this function, the domain of the function is alpha comma beta, then you won't say that on alpha it will have its least value and on beta it will have its greatest value. That's a problem, because this function is neither strictly increasing nor strictly decreasing. This is basically, first of all, decreasing from alpha to a certain value, let's say gamma, and then from gamma to beta, it is increasing. So first of all, through AOD, which we'll learn, of course, this particular concept of finding the range or the maxima or minima or the global maxima or global minima, we'll discuss while discussing the chapter application of derivatives. After differentiation, we'll have a discussion on this. There we'll discuss how to find the global maxima and minima, through which you can put a comment on the range of a function. So here, first of all, I'll trace the curve, I'll find the nature of the graph, I'll find the nature of the function, and through this I'll predict that this is a decreasing function, then increasing, which means if it was decreasing first, then increasing, then it must attain its minima at f of gamma. So that will be the minimum value. And of course, between f of alpha and between f of beta, I'll find which one is greater. That will give me the idea that it will be either greater at f of alpha or f of beta. And if I compare these values, I could see that f of alpha is lying above on the y-axis, then f of beta, then its range will be, the minimum value will be f of gamma and its maximum value will be f of alpha. I hope you are realizing why. So you cannot say that its range will be f of alpha to f of beta. No, it does not work that way. Students confuse it like that. So you cannot always put the minimum value and find its minima and put the highest value and find its maxima. No, it does not work that way. I hope you're realizing why. But this is exactly what we'll discuss while discussing the chapter AOD. So keep it saved for that moment, that day, that one shot. We'll have a more clarity on this particular part on finding the range of a function through application of derivatives, through differentiation, through maxima and minima, through monotonicity, and a lot more. So keep it saved for that day. As of now, we'll restrict our discussion to some limited category of questions, and that I'll make you understand through a particular example only. For example, this question asked by JEE Mains in 2025, it says that this is a question, this is an expression, and you need to find its range. Okay, that's fine. And we are told that x does not take two values. Which two values? X does not include two values 1 and 2. Okay, that's fine. That's absolutely fine. And we are told that its range is this. Okay. And by comparing them with this range, I need to find alpha and beta. Okay, we will. But how do we do that? So there is a standard method of solving this category of questions. What is that method? Let's start working on that. So to find range based on this category of questions, what you do is, let's say y is equal to 5 minus x whole upon x square minus 3x plus 2 is needed to be done. This is what I'm solving right here. Now, this is true for all x except for 1 and 2. So I cannot put x as 1 and 2. Otherwise, I can put all the other values. That's brilliant. That's brilliant. So it says that in its domain, I can take all the real numbers except for 1 and 2. That's the best part which they have stated so far to help me in solving this particular question. If I cross multiply this is the standard operating procedure you are supposed to follow while dealing with this category of questions. So look at the question, again, add it to your pattern list and remember the method which we are going to discuss now. Please put your complete focus here. So now, when this x square minus 3x plus 2 is multiplied with y, this becomes yx square, then this becomes minus 3yx, then this becomes 2y is equal to 5 minus x. I hope there is no confusion on that. Now, if I take everything on the left hand side, what do I get? Yx square is what I'm left with. Then we have this minus 3yx plus x. So here we have plus x minus 3yx plus 2y minus 5 is equal to 0. Even from here, if I take x common, it will be 1 minus 3y. So it will be 1 minus 3y. So I can write it as 1 minus 3y whole times x. And this is going to be the other term. Why did I write in this particular manner intentionally? The reason was that there is a quadratic which I'm seeing right now. A quadratic in x. And this quadratic in x is true for all the real x except for 1 and 2. Which means this quadratic is taking real roots except for 1 and 2. Okay, I'll take care of 1 and 2 later. But as of now, I'm told that this will have a real roots, a set of real roots. What does it mean? It means that its discriminant should be greater than or equal to 0. Are you understanding my motive? We were initially told that this expression is true for all the real values of x, which I have converted into a little different format in terms of y basically. So this is a quadratic in x, which has y as well. Y I'm treating as coefficients. So here, this quadratic in x is true for all the real values of x, which means it has real roots. And if a quadratic has real roots, its discriminant should be greater than or equal to 0. On the basis of this, can I not conclude that its discriminant should be greater than or equal to 0? From here, what is going to be the discriminant? B square. What is B square? 1 minus 3y whole square minus 4ac. What is 4ac? 4a. What is a? Y. What is c? C is going to be 2y minus 5, and this expression should be greater than or equal to 0. Did you understand this whole part? Any confusion so far? Are you able to understand the whole process, the entire approach, the complete method? Now, let us move ahead. 1 minus 3y whole square. What is it going to be? So 1 minus 3y whole square is going to be 1 plus 9y square minus 6y. Let me check if I'm correct. I think it is great. 1 plus 9y square minus 6y. This is exactly what I have written. Minus 4y plus 2y. That is going to be minus 8y. Right, minus 4y plus 2y is going to be minus 8y. Minus 4y minus 5 should be plus 20y. It should be plus 20y. Let me just check this. Yes, I'm making an error. Minus 4y plus 2y should be minus 8y square. So plus 20y, because it is plus 20y, yes, it should be greater than or equal to 0. So this is what I'm solving further now. Now, what do I do next? Let me check this part here. So 9y square minus 8y square will give me y square from here. I hope there is no confusion on it. Then what am I getting next? 20y minus 6y is going to be plus 14y, and then what are we left with is plus 1. So that is what we are having. I hope we are going great, because this is y square plus 14y plus 1 is equal to 0. So this is what we have received so far. Let me just check it, because the roots are looking a little difficult. Alpha and beta are found to be a little complicated. Well, that's not a problem. We'll do it. But still, let me just check it. So I think we are going great, because b square 1 minus 3y whole square minus 4ac 4ac. It should be 9y square plus 1 minus 6y, which is what I've written, 9y square plus 1 minus 6y. And then minus 8y square plus 20y. Yes. And when you do it, 9y square minus 8y square y square 20 minus 6 is 14, and then you're left with 1. Great. So I think this quadratic has two roots. Which two roots? Let's say this is a quadratic which when solved gives you two roots. Let's say those two roots are alpha and beta. And why is it equal to 0? It should be greater than equal to 0. So let's say the two roots of this quadratic are alpha and beta. So I'm not finding the roots right now. Let's say there will be roots because the roots can be found. Don't worry about it. So the quadratic will be written as y minus alpha, y minus beta greater than equal to 0. Can I do so? Now, when you say that this quadratic with a positive coefficient of y square is needed to be greater than equal to 0, we know it will be before the smaller root and after the greater root. And here I'm assuming that alpha is less than beta. This is what I am assuming. I hope you are not getting confused by that. So we know that if this is the inequality we are dealing with through even Wavy-Kerr method, I would be concluding that y will be either less than alpha or y will be greater than beta. Do you remember it? So my answer will be that y should lie between minus infinity to alpha or beta to infinity. But that's a problem. Sir, you have concluded the same answer coincidentally, but you need to find alpha and beta. Rather, alpha square plus beta square. Okay, great. So I need to find alpha square plus beta square. What is alpha square plus beta square? Here, if I am asked to find alpha square plus beta square, which is nothing but what? Which is the roots of this quadratic. So if I were to solve this as a quadratic, y square plus 14y plus 1, it would have been the roots. Alpha beta would have been the roots of this quadratic. So if I'm asked the roots of this quadratic, alpha square plus beta square, can I not say it will be equal to alpha plus beta whole square minus 2 alpha beta? Do you remember this is the result we had discussed in the chapter quadratic equations? So these results keep on getting used in other chapters as well. So yes, now alpha plus beta, sum of the roots. What is sum of the roots? Minus 14 upon 1. So this should be minus 14 square. I hope you are realizing that. Minus 2 alpha beta. So minus 2 alpha beta should be minus 2. Alpha beta is basically 1. So that's your 1. Minus 14 square we all know is 196. So that is going to be 196 minus 2 and it should be 194. Let me just check it. Yes. Minus 14 square is 196, minus 2 alpha beta is minus 2. So 194 should be the correct answer, which we are given in option D. Some of you may have possibly made an error that it's not an error, but it would have made your calculation more lengthy. You may have found alpha and beta from here, the two roots. Sridharacharya method, and once you have found that Sridharacharya formula, through that Sridharacharya formula the roots, you would put those values alpha and beta here, and that would make your calculation a little more lengthy. And that's where you should be more cautious and alert that if you have identified that this is a solvable quadratic, which means it will have two real distinct roots. So I imagine them to be alpha and beta, and I treated it as alpha square plus beta square, and I know how to find the sum of alpha square and beta square. That's exactly what we have been discussing throughout this journey so far. In every single chapter, we have learned something, and we will keep on applying those learnings in some other chapters. And that's what JEE does. They merge concepts from different particular chapters. Any confusions on that? I hope you have understood how to deal with the concept of range. Now we move to the part where we discuss concept of odd and even functions. What is it? Let's start looking at this particular slide now. Okay. Functions are categorized into two categories, odd and even, and the third category is neither even nor odd. This is also one of the classifications you do based on their, pattern. Now, what is that pattern? Simple, very simple it is. For example, let's say there is a function f of x and it is given as x square. I'm replacing x by minus x. So technically I'm finding f of minus x. So when you do that, I can still see that it is square of minus x, which is x square only, which is equal to f of x. So whenever you see a function f of x turning out to be as minus f of x, or rather f of minus x turning out to be f of x, if both of them are equal, then such category of functions are said to be even functions. Similarly, let's say we have a function, let's say f of x, which is given as, let's say, x cube. And let's say again, if I replace x by minus x, so it will become cube of minus x. We know if it has an odd power, it can be written as negative of x cube. X cube we know was f of x, so I can write it as negative of f of x. What does it mean? It means if I'm finding f of minus x, and if by these simple calculations, if I find f of minus x as minus of f of x, then such functions are called odd functions. So if a function is even, it is even. If it is odd, it is odd. So if a function is not even, can it be odd? No, it cannot be said. So functions are either even or odd, or they are none. Remember this. Now, what else is true for odd and even functions? So whenever the function is odd, it is symmetric in opposite quadrants. Look at the graph of x cube. So if you draw the graph of x cube, it looks like this. So it is symmetric in the opposite quadrants. So you will see that it is symmetric with respect to the origin. I hope you can see it here. That is the logic here. And similarly, when you talk about even functions, these are the scenarios of odd functions. When you look at even functions, they are symmetric with respect to y-axis. For example, look at the graph of x square. I hope you remember the graph of x square looks like this. So it is basically symmetrical with respect to the y-axis, because if f of 2 is something, f of minus 2 will also be that same value only, because minus 2 square and 2 square are same. So modulus function, square, or something like that will be called the even functions. And the example of even functions are written over here like this. But the questions are formed based on even and odd functions. See, let's say I'm asked to check whether a function is even or not, or odd or not, or neither. In that case, I will keep certain things in mind, and based on these results, I will be able to predict a lot of things even without calculating them. How? Have a look at that. Always remember that whenever you are multiplying two odd functions, or let's say two even functions, then it is always an even function. I hope you'll remember it. So whenever you multiply odd functions or even functions even number of times, then you will always have an even function. Did you get that? And of course, let's say I'm multiplying an odd function with an even function. So odd into even will be odd. I hope you'll remember it. It is like positive, positive, negative, 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 positive. You can remember it like this. Along with this, there is third result. Let's say there is a function fx. You can always write any function in the world as a sum of an even and an odd function. How? Let me just try and give you the idea on that. The idea is very simple. Let's say here you are having a function f of x. So I can write this function f of x as a sum of an even function and an odd function. What is that? If I am adding fx to f of minus x, and if I'm subtracting f of minus x from f of x, and if I divide both by 2, first of all, let me show you that why is it f of x only, because f of my, I'm really sorry, there is this small correction over here. This should be f of minus x, because f of minus x cancels this f of minus x. Then you're left with f of x plus f of x. 2f of x divided by 2 will leave you with f of x. Now, let's put our focus on these two functions. Which functions? This one and this one. Please pay attention here. F of x plus f of minus x. Let me show you this function f of x plus f of minus x. Whole divided by 2 is also there. Let's say this is a function which we are calling as g of x. Let me replace x by minus x. Basically, I'm finding g of minus x. So if I am working on g of minus x, what would it be? It will be f of minus x plus f of minus x, which means f of x divided by 2. And I hope you can see it is nothing but what? G of x. So I can very easily predict that g of x is an even function, which means this is an even function. Let me talk about the next part. Let's call that other function as h of x. Which other part? The second part of our this expression, f of x minus f of minus x whole divided by 2. So here I am writing h of x as f of x minus f of minus x whole divided by 2, right? Here I am trying to find h of minus x. What is it going to be? It is going to be f of minus x minus f of x whole divided by 2. Can I take negative sign common out of it? Yes. So when you take negative sign common out of it, you are left with f of x minus f of minus x whole divided by 2. What is it? Minus of h of x, minus of h of x. So I was trying to find h of minus x and I found minus of h of x. What does it mean? It implies that this was an odd function. So I hope you understand the motive, the intent, which is that any function in the world can be written as the sum of an even function plus an odd function. Did you get that part? Do you remember we had a discussion that any matrix, square matrix of course, can be written as a sum of symmetric matrix and skew symmetric matrix? That same sort of logic is being applied here, if you could remember it. So remember this as a result. A very useful result it is. It is used at a lot of places. Now, some other properties are also there. Let's discuss them one after another. What is it? The derivative of an odd function is an even, and derivative of an even is always odd. Remember it. For example, x cubed. If you find its derivative, it will be 3x square. Odd, even. Did you get that? Vice versa is also true. A function which is even or odd when squared always becomes an even function. I hope you're square understanding it. Because when you square it, you're multiplying odd with odd or even with even. So odd into odd or even into even is always even. So that logic can be applied here. Next property. The next property says the only function which is both even and odd is 0. I hope you're realizing 0 is a constant function. So f of minus x will be f of x and it will be equal to minus f of x because plus minus 0 does not mean something, it is always 0 only. So I hope you're realizing 0 is the only function which is odd as well as even. So let's say in our question, they use this different language. They don't say 0 directly. They say that there is a number or a function which is even as well as odd. We will say that the function should be 0. That's the only function you have. No other function is even as well as odd. I hope you will remember these results which we have been discussing. Now, there comes another concept which is called periodicity or periodic function. I hope you must have seen trigonometric functions. I hope you must have seen the fractional part function. Those were the functions which were periodic in nature. Why? Because let's say if I could draw the graph of periodic function, let's say if I am drawing the graph of this fraction part function, how does it look like? So sir, for 0 to 1 it looks like this, then again from 1 to 2 it looks like this, from 2 to 3 it looks like this, and it goes on like this. It keeps on going like this. I hope you remember it. So from minus 1 to 0, it attains values between 0 and 1. From 0 to 1, it attains values between 0 and 1. From 1 to 2 also. And you must be noticing that this is a scenario of a periodic function. Because it repeats itself. It is showing the same pattern again. And it has a period t, 1 in this case. Because after one integral value, it is repeating its own values same again. So the fraction part of 1, the fraction part of 1.2, 2.2, 3.2, 4.2, all of it is going to remain same. That is 0.2. Why? Because it is a periodic function. The same is true for sin x, cos x, tan x, sec x, cos x, and cot x. They are also periodic functions. So even if you look at those functions, it will also give you a certain period. Of course, we'll talk about that later. But as of now, are you understanding the concept of a function being periodic? Are you able to make some sense out of it? That when do you call a function to be periodic? Now, I'll put some comments on a function and its periodicity and some generalizations, which you are again supposed to remember the way we have had a discussion on odd and even functions. Look at these properties. Again, what do we have here? The first result is sin x to the power n, cos x to the power n, sec x to the power n, cosec x to the power n. They will also have the period pi if n is even, and it will have a period 2 pi if n is odd. I hope you will remember it, that sin x, cos x, sec x and cosec x, whenever they are raised to a certain power, if the power is even, the period will be pi. If the power is odd, the period will be 2 pi. Do remember it. Some facts I'm giving you because questions are asked on a function's period. And if you remember these properties, you can apply them and get the answer very quickly. So this is something which you should memorize. You can learn them as well. You can logically understand them as well. When you draw the graph of these functions, when you raise them to a certain even power, you will realize that they are becoming periodic with the period pi. But if you raise them to an odd power, you will see the functions, the graphs are showing a period or a repetition after 2 pi interval. Right. Similarly, if you look at the other two functions, other two trigonometric functions, tan x and cot x. So whenever tan x and cot x are raised to any power, even or odd, natural numbers, integral values I'm talking about. So if they are raised to any power, even or odd, the period is always pi. Tan x and cot x, the period is always pi, no matter what power you raise it to. But for sin x, cos x, sec x and cosec x, if the power is even, the period will be pi. If the power is odd, the period will be 2 pi. Please remember this. If you remember this, this will be more helpful and advantageous for you in the real examination hall, or even if you are writing the mocks. There also will see that if you could remember these results, you will be able to solve a lot of questions. Indefinite integration in area under the curve will be asked to deal with different graphs. So you can predict a lot more about a graph if you know whether it is odd, even, periodic, or what is it, what is the period of that function. If you know such nuances of a function, about a function, you can say a lot more about that function and its graph, and graph will be more useful when we'll be discussing the chapter area under the curve. So yes, that foundation is laid with this particular chapter only. So we are understanding those basics related to the functions and we'll be using it in throughout the calculus. Not even in calculus, through even in some other chapters as well. Here, if I look at the third possibility, sin x, cos x, tan x, cot x, sec x, and cosec x, if I put mod over them, the period becomes pi. The period becomes pi. Please remember them. X minus GIF of x, which is nothing but what? I hope you must remember fraction part of x. Fraction part of x is a periodic function with period 1. Do you remember that? Algebraic functions, they don't have any period. Remember it. Similarly, any constant function is called a periodic but with no defined or specific period. Because it is a constant function, it is always same. So it does not have any defined specific period here. I hope you are getting it. Now there are some more conclusions. Do remember them. Questions are asked on these properties. What are these conclusions? The first conclusion. Let's say fx is a periodic function with period t. We can take the example of sin x for a while. So let's say there is a function fx which I'm defining as sin x. Now, I hope you know the sin x. What is the power of sin x? The power of sin x is 1. What is 1? Odd. So the period must be 2 pi. I hope you remember the discussion we previously had here. Sin x to the power odd, then the period is 2 pi. Even if the power is fraction, then also the period is 2 pi. So here I am taking the power of sin x as 1, basically sin x only. So the period here is the value of t I'm assuming as taking as 2 pi. Now I'll be drawing some conclusions and I'm strongly asking you to remember them, urging you to remember them. Please remember them. First conclusion, if you are multiplying sin x by a constant value, let's say I'm multiplying sin x by a constant value, any value. Let's say I'm writing here any value 5 sin x. Then also the period will be 2 pi. The period is not affected if you're multiplying that function, that periodic function with a constant value. Even for any value which is constant, which is added to x, then also the period remains intact. What do I mean by that? Let's say I'm writing sin x plus 20. Then also it will be a periodic function with the same period t, which is 2 pi in this case. Fx plus minus c is also a periodic function with the same period. For example, here, if I'm writing sin x plus 30, so I'm adding 30 to sin x, then also it will remain a periodic function with the same period 2 pi. I hope you, that same example, luckily they have written or given over here. So that's brilliant. Perfect. Now, let us move ahead to the next case. What are we given next? If x is multiplied by a certain value, then that period should be multiplied by divided by that mod of that value. What do I mean by that? Let's say 7 sin 2x plus pi by 9 minus 12. So we know this 7, this pi by 9 and this 12 won't affect the period at all. My concern will be this 2 which is multiplied to this x. So this function will also be a periodic with the period 2 pi divided by mod of this 2, the coefficient of x. So 2 pi by 2 is pi and pi will be the period of this particular function. So are you understanding? Let's say even if this function is given to you and you are asked to find its period, you can find it within seconds. And we'll use such properties in solving questions based on definite integration or area under the curve or something like that. Similarly, even when you add, subtract or multiply some functions, then also the period comes into picture. For example, here, there are two functions f1x and f2x. They are two periodic functions with period t1 and t2. And I'm adding them f1x plus f2x. So the period is going to be LCM of t1 and t2. What does it mean? What does it mean? Achha, there is one more thing. If hx is not an even function, what does it mean? It means that if, please understand, if hx is not an even function, we'll say LCM of t1 and t2. But if f1x and f2x are complementary pairwise comparable functions, what does it mean? For example, sin x and cos x or something like that, then it will be half of LCM of t1 and t2. I'll take an example and make you understand it more clearly. Let's say, this is also what we'll discuss. Let's say I'm taking the example of sin x plus tan x. So what do you understand by sin x and tan x? Sir, we know that the period of sin x is what? The period of sin x is 2 pi. What is the period of tan x? The period of tan x is pi. Now take the LCM of pi and 2 pi. So the LCM of pi and 2 pi will be 2 pi and that will be the period of sin x plus tan x. But students forget or commit an error that if, let's say, I'm asking you the LCM of 2 pi by 3, pi by 6 and pi by 12. So this is a fraction. So in that case, I'll take the LCM of the numerator, which is 2 pi, pi and pi, and I'll take the HCF of the denominator, which is the 3, 6 and 12. So I hope you're understanding. LCM of 2 pi, pi and pi will be 2 pi, and HCF of 3, 6 and 12 will be 3. So in that case, let's say there are three functions which have periods 2 pi by 3, pi by 6 and pi by 12, and they are added. And then I need to find the period of the summation of these three periodic functions. So that will be the LCM of 2 pi by 3, pi by 6 and pi by 12, which is 2 pi by 3 through this particular method. I hope you are getting a great clarity on this front. Now let's move ahead towards the next part, that this is something where you need to be more cautious, that you cannot take the LCM of a rational number with an irrational number. I repeat, a LCM of an irrational number with an irrational, a rational with rational is possible, irrational with irrational is possible, but rational and irrational's LCM is not possible. So what I'm saying is that you can take the LCM of 2 pi and 6 pi, you can take the LCM of 2 and 3, but you cannot take the LCM of 2 pi and 1. That's the problem, because 2 pi is a rational and 1 is an irrational. Oh, sorry, 2 pi is an irrational and 1 is a rational. So that is something you should take care of. I hope you will remember it. So let's say there is a function whose period is 1. Let's say there is a function whose period is, let's say, 2 pi. And if I add them and if I ask you whether it will be a periodic or not, you would say no. Because the problem is I cannot take the LCM of 2 pi and 1. That's a problem. Did you get that part? Moving ahead towards the next part. Sometimes this LCM rule is not applicable if the function reduces to constant. For example, this sine square x and cos square x. Now, some of you might say that sine square x has a period pi, cos square x has a period pi, pi and pi, the LCM is pi. So the period should be pi. But there is a problem, there is a catch, that sine square x plus cos square x is 1. And if it is 1, it is constant, and constant has no defined period. So are you understanding that catch, that problem? So you need to be more cautious and more alert while dealing with such questions based on periodicity. Look at this example. JEE Mains 2014 has asked it, that there is a function mod of sine 4x plus mod of cos 2x. Now you need to find the period of this periodic function. Some very standard question it is. We know that mod of sine x and mod of cos x have period pi. So mod of sine x has period pi, mod of cos x also has period pi. But with the sin x, we are multiplying it by 4. In sin x, the x is multiplying by 4. So I need to divide this pi by 4. So this will be the period of mod of sine 4x. Here, this x is getting multiplied by 2. So mod of cos of 2x will have the period pi by mod of 2, which is 2. So here, the period of sum of sin x and cos x, sum of mod of sin x, sum of mod of sine 4x plus mod of cos 2x will be LCM of pi by 4 and pi by 2. Again, I hope you remember. How do we take the LCM? We take the LCM of fractions as LCM of the numerators, which is pi and pi, and HCF of the denominators, which is 4 and 2. So I hope it is very simple. LCM of pi and pi is going to be pi. Nothing needs to be told here. But HCF of 4 and 2, highest common factor, the greatest possible number which can divide both of them, will be 2 here. So the answer will be pi by 2, which is given in the option D. Did you get this part? I hope you are able to make a great sense out of it very easily. Now this is the part which again becomes very important chunk. The different kind of mapping of functions, one, many, one, into, onto, and that's where again questions are framed. Permutation and combination is mixed in this particular topic because you use PNC, the logics of PNC here, to understand the number of mappings. So that is also what we'll discuss here through examples only. But put your complete focus and attention in this particular chunk of this video, because mapping is again a very crucial part from where questions are asked and framed. How? Let's have a look at that. First of all, let us understand what is one-one mapping. So one-one mapping, if I could show you or demonstrate you through example, this is the standard description of a one-one mapping. So you have 1 which is mapped to 3 only, 3 is mapped to 7, 5 is mapped to 11, like that. For example, if let's say there was some other element which is mapped with 7 as well, so it is many one. So one-one mapping, I hope you're able to understand that distinct images should be there in codomain. For every single element in domain, it should possess distinct images in the codomain. Such mapping is called one-one mapping. The word itself is self-explanatory, one-one mapping. So I hope opposite of it, if something is not one-one in functions, it will be many-one. What does many-one mean? So let's say if there is another element and that is also associated to the same image. So two elements of the domain have the same image. Such mapping is called many-one mapping. I hope this part is making complete sense out here. Now, this is basically not 1, 1. Which one? This particular part. I hope you can see it very clearly. Even this is an example where you're seeing a not 1, 1 mapping. So if something is not 1, 1 in functions, it will be many 1. So if something is not many 1, it is surely going to be 1, 1. So that is true there. Now, if I could make some more comments on how to check whether a function is 1, 1 or not. So I'll put f of x is equal to f of y and I'll check it. And ultimately after checking, if I'm able to conclude that it is true only for x is equal to y, then I'll say that it is 1, 1. I hope you are understanding it. Technically, this is the definition we follow. But sometimes, of course, if I could draw the graph, if I could check its monotonicity, if the graph is meeting x-axis more than one times, or even if I could see periodicity, I hope you're realizing these are the basis on which we can conclude that the function is not going to be 1, 1. Because see, if there is a periodic function, let's say this is a periodic function. So if it is a periodic function, it will have more values of x for which the same value of y will be generated. If you see the graph of the function which is intersecting the x-axis at more than 1 point, that is also a many 1, which is not 1, 1. So such are the phenomena, such are the basis. For example, whenever you see the graph of a function, let's say I am seeing the graph of a function, something like that, and I could do a horizontal line test. So if I could draw a straight line parallel to x-axis, which is intersecting the graph of this curve at more than 1 points, then of course it is going to be a many 1 function. So these are the some basics through graphs through which you can always claim that this function is many 1 or 1, 1. Of course, if a function is strictly increasing, monotonically increasing or monotonically decreasing, then it will be 1, 1. Why? Because look at the graph of e to the power x. So e to the power x has a graph like this. It is strictly increasing. So it is going to be 1, 1. So such are some basic observations, understanding of graphs that will always help you in deciding whether a function is 1, 1 or many 1. Now, let's move ahead. Let's move further. There is this third method, which is again by calculus. I will check the function is only increasing or only decreasing. This is exactly what I have tried making you understand. And yes, please understand, graphical or calculus method is the most reliable method to check whether a function is 1, 1 or not, or many 1 or not, because through that you will get a holistic, a complete clarity on a function being 1, 1 or many 1. Now, let's say there is a function defined from set A to set B. And of course, we can define a different set of functions from A to B. We have already had a discussion on this. But this time I'm putting a constraint. What constraint? Let's say I want to define a function from A to B. The domain is A. This is your domain set. Always remember. This is your codomain set. Of course, it is not a range. It is codomain. It is codomain. Remember it. But what I'm trying to make you understand is that I'll map the domain's element to codomain's element. But the kind of mapping is going to be 1, 1. So I'll ensure that it is 1, 1. So the number of 1, 1 mappings which can be done. Again, what is the condition here? The constraint is that this time it should be 1, 1. So let's say the first element I pick from here x1 and I ask it, how many choices do you have? It will say I can be mapped either to y1 or to y2 or to y3 or yn. So this first element x1 will come up with the response saying that I have n choices. I have n number of choices. And means multiplication. Now I go to the second element. Now I go to the second element x2 and I ask x2 how many choices do you have? So x2 will come up saying that I have now n minus 1 choices. Why? Because x1 will get assigned to a certain number. Let's say x1 is assigned to y2. X1 has chosen its partner, its image. Now, when I go to x2, how many choices does it have? So x2 will say that I can go to either y1 or y3 or y4 or yn. So this time, this x2 has how many choices? This time, x2 is left with n minus 1 choices. Are you understanding the pattern I'm saying? So, and now x2 has n minus 1 choices. I hope you are understanding the pattern, the method through which I am calculating this. So, if I were to give you the generalized formula of finding the number of mappings, you will say, sir, it is what I'm trying to give you or convey here through this particular method, which finally leads you to this, that if your domain has, see, in your domain there are m elements, then in your codomain there are n elements. I repeat, I'll draw it here as well. So in your domain there are m elements, and here in your codomain set also there are n elements. I hope there is no confusion on this front. Let me just check and verify this so that you stay very clear to this. So m and n, brilliant. So there were m in elements in domain and n elements in codomain set. So first of all, out of those n elements, I hope you can see it very clearly here. Out of those n elements, first of all, I need to map these m elements in such a manner that the relationship, the mapping stays 1, 1. So how do I do it? Out of these n elements, I'll choose m elements. So out of these n elements, of course, the condition is that this n should be greater than m. Then only 1-1 mapping is possible. In the worst case, both of them should be equal. But the number of elements here in the codomain should not be less than the elements positioned here. Otherwise, the mapping can never be 1-1 because some elements have to go to the same elements, and that's where it will become many 1. So if you want to have the mapping to be 1-1, the first condition is that if the certain number of elements are there and certain number of elements are there, then the number of elements here should be more than the number of elements present in the domain. So the number of elements in the codomain should always be greater than equal to the number of elements in the domain. Equal, worst case will be equal, not less than equal, because if less than equal, less than codomain, then it will have no 1-1 mapping. I'll get back to this part. So out of those n elements, I'll choose m elements. So out of those n elements, m elements can be chosen in NC m ways. And then those m elements can be arranged at these m places in m factorial ways, which is nothing but what? Which is n, p, m. That's exactly what we are doing here. So this is the formula to figure out the number of 1-1 mappings. If you didn't get this part, I'll try and make you understand through an example. Let's say here we have some elements A, B, and C. Let's say here we have some elements D, E, F, G, and H. Of course, what do we have? This is your domain set, right? And this is your codomain set. I hope there is no confusion on it. This is set A and this is set B. So from set A to set B, you're mapping it through a function. But the constraint here is that the mapping should be 1-1. The mapping should be 1-1. So what I need is, sir, with these three of these should be mapped. So out of these available 5, I should choose 3. So out of 5, I can choose 3 in 3 ways. And those 3 with these 3 can be mapped in 3 factorial ways. It's like there are 3 people. They can be asked to sit on 3 chairs. So 3 persons on 3 chairs can be asked to sit in 3 factorial ways. And this is nothing but what? This is 5p3. So basically, choosing 3 objects and then mapping them. Choosing 3 objects out of 5 available objects and then mapping them with 3 objects can be done in 5p3 ways. So I hope you're understanding that's the formula. But along with the formula, are you understanding the logical approach? Because more importantly, you'll be asked to apply the logical approach. So I hope you understood the 1-1 mapping. Now, many-1 mapping. I hope opposite of 1-1 is many-1. As we have already discussed and seen, I need not explain this part. My concern will be to make you understand how do you calculate that number of many-1 mapping. So I'll say, if I'm asked to calculate the number of many-1 mappings, so I'll go back to the basics. What was the basics? The number of functions, the total number of possible functions. The function could be either 1-1 or many-1, but it can never be both. So out of total number of possibility of functions, if I could remove the possible number of 1-1 functions, then will I not be left with many-1 functions? So let's say there is this set A, which is the domain set. There is this set B, and there is this function F. So I can calculate the total number of functions. Total number of functions from A to B. We had a discussion on this. From this, if I'm subtracting, what am I subtracting? If I could subtract the total number of 1-1 functions from A to B. So what will I be left with? Will I not be left with total number of many-1 functions? So I hope you are understanding the very basic formula that if I were to calculate the number of many-1 mappings, I need not have a different formula. What I need to have is total number of functions, which I can calculate. We have had a great intensive discussion on that. If there are certain elements in A, there are certain elements in B, then the total number of functions which can be created from this domain to codomain. I hope you remember that formula. From that, if I'm subtracting the total number of 1-1 functions, we have had a discussion on this as well, just in the last slide only. So if I could take this difference out, I'll be left with total number of many-1 functions. Did you remember it? The reason is very simple. The function could be either 1-1 or many-1. Did you get that part? Let us move ahead. Let us move towards the next portion where we discuss the other category, onto or into. Onto, which is also said to be the surjective mapping. What is onto? Let's say you have a function. I'll discuss all of this, but before I discuss onto and into, let me take an example here. Let's say this is your domain set, this is your codomain set. So whenever I draw these two sets, you should assume this as the domain and this as the codomain set. domain has certain elements. Let's say it has nothing to do with 1, 1 or many 1. That is different now. Now I'm classifying function on the category of basis of onto or into. Now what is onto and into? Let's have a look at that. So here this domain set has certain elements A, B and C. This has elements D, E and F. Right. Now if A, B, C, let's say this has D as well. Okay, D was used there. So D can be there. Let's say, let's call it some other, let's say D, E, F, G, right? So this is the domain and codomain set. Now from domain, let's say I mapped A with E, B with F, and C with G, and D with also G. So this is a mapping where if I'm finding the range, of this function, this is the range of this function. And what is the domain of the function? This is the codomain of the function. This is the codomain of the function. So whenever you see or observe or analyze that the codomain and range are equal, of course, range is always going to be the subset of the codomain. But if the range and codomain are equal, if number of elements are exactly same in the codomain as well, number of elements in range are exactly same as the number of elements in codomain, then such mapping is called onto mapping. Or in a different language, I'll say if no element is left in the codomain set which does not have a pre-image in the domain set. I C, G, F, E, all of them have a pre-image in the domain set. In that case also, I would say that this is a case where I'll call this function or mapping to be an onto mapping. So when does it become into? So let's say there was one more element, let's say H for a while. So of course, codomain can have elements which do not have any pre-images in the domain set. For example, H. So here, range is a proper subset of codomain because H is not a part of range, but it is a part of codomain. So range and codomain are not equal in this case. Such mapping is called into mapping or into function. So onto and into, I hope you are able to differentiate. And again, I'll say functions are either onto or into. So if a function is onto, it will be not into. If a function is into, it will be non-onto. If a function is not into, it will be onto. If a function is non-into, it will be onto. I hope I'm not confusing at all, and you are able to digest all what I'm saying or stating in this particular one shot. Now, moving ahead towards the next conclusion, 1, 1 onto mapping. Again, if you club 1, 1 and onto, you will have 1, 1 onto mapping, which I will explain with this part only. So this 1, 1 onto mapping means what? X1 is assigned to 1, Y1, X2 and Y2, X3 and Y3, and until Xn is associated with Yn. So first of all, you need to understand if you want to have a 1, 1 onto mapping. So 1, 1 and onto means no element should be left and it should be 1, 1. So all of these have only 1, 1 choice. I mean, technically they'll have, each of them will have, the first one will have n choices, second one will have n minus 1 choices, third one will have n minus 3 choices. So technically, if there are n elements here, there should be n elements here to make it a 1, 1 onto mapping. And first one has n choices, second one has n minus 1 choices, third one has n minus 2 choices. So technically, total number of 1, 1 onto mappings will be n factorial, because n people can be arranged at n places in n factorial ways. So if you are asking about the number of 1, 1, the number of 1, 1 mappings, if the number of 1, 1 mappings in this particular case, 1, 1 onto mappings in this particular case, then number of elements should be same in both codomain and domain set. Because it should be 1, 1, which means 1, 1 mapping should be there, and should be onto, which means no element should be left here. The range in codomain should be equal. So to ensure 1, 1 onto, there are basically the simple case that n elements if are there here, the same number of elements should be there in the codomain set. So n people can be arranged at n places in n factorial ways. So that will be the number of ways in which a function or mapping can be done so that it stays 1, 1 onto n factorial ways. Did you get that part? The same will be explaining or understanding here. That same logic I'll be giving you here, that the mapping of a function. So here, total number of functions, as we have already discussed, r to the power n, which implies number of elements in codomain raised to the power number of elements in domain. We have had a discussion on this, that each element has those number of choices. Second one can also have those choices. Third one can also have those choices. In that same fashion, we'll have r to the power n choices. If you have forgotten it, I'll make you recall it again. See, the domain has A, B, and C, and the codomain has D and E, let's say. So if I approach A and ask how many choices do you have? So A will say, I can either go to D or E. So A has 2 choices. B will say I can go to either D or E. C will also say I can go to either D or E. That's why 2 into 2 into 2, 2 to the power 3 choices. That's exactly what we have written over here. Now, if I were to ask you the total number of 1, 1 functions, then this is also we have already calculated. This is exactly what we have had a discussion upon. Now, Total number of many 1. So total number of functions minus 1 functions. Do you remember that? Now the next conclusion. Total number of constant functions. That will be our constant functions means what? The number of, if everything is also associated to the same value. So that is also there. Now total number of onto functions. That is something which I will try and make you understand through an example rather than making you learn this particular formula. We'll take an example and understand it through this particular scenario. Look at this particular part. What does it say? It says f 0 to 3 to a. So this is its domain and it is its codomain. So f is a function from 0 to 3. It is defined from 0 to 3 only. That is its domain and a is going to be the codomain. B defined by fx 2x cube minus 15x square plus 36x plus 7. Brilliant, that's great. There is another function gx which is having domain as 0 to infinity, where 0 is included, to b. So b is the codomain here. Great, perfect. Now, it is defined by gx. So gx has also a certain definition, x to the power 2025 upon x to the power 2025 plus 1. If both the functions are onto, did you get that? What is the meaning of a function being onto? If a function is onto, it means its range and codomain will be equal. So if I could figure out the range of f of x, then it will be equal to a. If I could find the range of g of x, it will be equal to b. So once you do that, then I need to find something else related to a and b. That I'll work upon later. But as of now, let's try and find a and b. So are you realizing this is a question based on range only? So you need to find range basically, and through range, we'll compare it with codomain because the functions are onto, and when functions are onto, range and codomain are equal. And through that, I think I'll solve this question further. That's the second part of this question with which we'll deal later. But as of now, let's try and finding range. So this is how, while reading the question, you interpret it and then you build an algorithm that this is what is needed to be done. So first step, let's find the range of this. So some of you might say that, sir, since it is an odd functions, it is a polynomial of odd degree, its range is going to be minus infinity to infinity, and that's a problem. No, this is not a problem because its domain is not all the real numbers. Its domain is 0 to 3. That's where you need to be more cautious because its range is going to now vary because its domain is restricted from 0 to 3. I hope nobody is thinking, sir, f of 0 will be its minimum value and f of 3 will be its maximum value. That is also false, as we have had a discussion on it. It could be increasing or decreasing or something like that. So I need to work more cautiously here. Second part of the question here, that is also I'll learn or I'll teach you how to do it, but let's work on f of x. So how to find the domain of f of x? Let me find f dash x. How do I find f dash x? I hope you know. I'm basically checking its monotonicity through AOD, application of derivatives. How do I do it? 2x cube gives you 3 into 2 into x square, which is 6x square minus 15x plus 36, right? Now we find its critical points. I put f dash x equal to 0. This is what you must have done in physics as well. Maxima and minima, first derivative, second derivative test, right? So it is going to give me f dash x is equal to 0 is what I'll do. From here, if I take 3 common, right? So if I take 3 common, 6x square, I'm really sorry, I have made an error. And this is how I do. So I sincerely apologize if I keep doing this constantly because this is what is wrong with me. So I keep committing such errors. 15 into 2 should be 30 and 36 should be 36 only. Right, great. If I'm taking 6 common out of it, so if I take 6 common out of it, I'll be left with x square minus 6x, I believe. Why 6? It should be 30. It's not 36. So it should be 5x plus 6 is equal to 0. Now, if I factorize it, 2 and 3, I think. So it is going to be x square minus 2x minus 3x plus 6 is equal to 0 because sum should be minus 5, product should be plus 6. So the two roots are going to be 2 and 3. What does it mean? It means if I could draw its graph between 0 and 3, I will have a point 2 and I'll have a point 3. So after 3, it will be increasing. Between 2 and 3, it will be decreasing, and before 2, it will be increasing the function because f dash x is, I hope you can see, this is your f dash x. So f dash x, if I notice around 2 and 3, f dash x is positive after 3. It is negative between 2 and 3 if it is positive before 2. So if f dash x is positive, it means increasing. And then between 2 and 3, it is decreasing. And then after 3, it is increasing. So the graph of the function, although I'm not very sure about it, I'm not drawing it very precisely, but the curvature I can draw. So it will be increasing, then decreasing, and then increasing. What does it mean? It means at 2, at x is equal to 2, I may have its local maxima, and at 3, at x is equal to 2, I may have its local minima. I hope you're understanding why. Because from minus infinity to 2, it will be increasing. So this is increasing. I hope you can see it. At 2, it will start declining. So up till 3, it will decrease. And then again 3, it will start increasing, because f dash x sign can help us in predicting its increasing or decreasing nature. Did you get that part? Now, where do I need to look at? I need to look at some other parts as well, because I am restricting it to between 0, 2 and 3. So this is not the exact curvature or exact curve, but I'm trying to give you the idea that I need to look at 0, 2 and 3. So I'll evaluate three things: f of 0, f of 2 and f of 3. Out of which one is greatest will be the maxima, and which one is the least will be the minima. So let's work on f of 0. Here. Let me find f of 0 here. So what is going to be the f of 0? I hope f of 0 is simple, because 0, 0, 0, that is 7. What is going to be the value of f of 2? F of 2 is also simple, because there is some calculation involved here. So 2 cube is 8, 8 into 2 is 16, then 2 square is 4. We are going great. So 15 into 4 is against 60. Then you have 36 into 2, which is 72 plus 7, right? So this is f of 2. So it should be how much? 72 minus 60 is basically 12. 12 plus 16. 12 plus 16 is 28. 28 plus 7 is 35. So f of 2 is going to be 35. So I'll write at 35 directly here. So this is going to be 35. Now let's work on f of 3. What is going to be the value of f of 3? So f of 3 should be 3 cube, which is 27. 27 into 2 is 54, right? Then 3 square is 9. 15 into 9. I hope you know it is 135. Just correct me if I'm wrong. So it should be 135. And then 36 into 3. 36 into 3 should be 108, because 90 plus 18 is 108. So this is plus 108. And then you have 7. So what do we have here? I'll just calculate it simply. So 135 minus 100 would be 35. But 8 is also something which is needed to be subtracted. So 35 minus 8 will be 28. So it gives me minus 28. I hope there is no confusion on it. Minus 28 plus 7. So minus 28 plus 7 will give me minus 21. I hope there is no confusion on it. Minus 21. And 54 minus 21, let me do it separately here so that we don't commit any error. 54 minus 21. So it should be how much? It should be 33, right? So it should be 33. So this should be 33. So f of 3 is 33. F of 3 is found to be 33. I hope I have not made any error. If I have, do put your comments in the comments box. I'll rectify them there, but I think we are going great. This involves some calculation, which is what you should be aware of. And even I can take it casually or lightly here. You cannot. You cannot afford to take it like that. You should be more cautious and alert. So here, what you do is you have gotten the values of f of 0, f of 2 and f of 3. I hope you can see that this is the minimum value and this is the maximum value. So I could crack the range of f of x. So the range of f of x, the set A will be given by 7 to 35. That's your range. So A is basically the lowest value is 7, the greatest value is 35. So that is the values. These are the set of values we have received for A. Now, let's talk about B. This function, x to the power 2025 divided by 2025 was the year in which they asked. So they gave 2025. Brilliant. Perfect. This is what IIT JEE does, right? In the next year, this year, you'll have x to the power 2026. Brilliant. Perfect. Now, what I do next is, this is gx, right? So how do I find its range? It's very simple. Why? Because gx, its domain is given. It is taking all the positive values only. This is all non-negative values. This is the set of all non-negative values. Mind you, everyone, from 0 to infinity. Perfect. Let's say I add 1 to it and I subtract 1 to it. So whenever you see something like that, this is what you should do. So this is gx basically, right? So gx in a better world can be written as this upon this minus 1 upon this. So this upon this will be 1 minus 1 upon x to the power 2025 plus 1. Now, please understand something very standard, which you can learn through observation only. But still, if I could tell you that, yes, we know that x is greater than equal to 0. So even x to the power 2025 will also be greater than equal to 0. But if I add 1 to it, it will be greater than equal to 1. Are you getting my statement very clearly? Now, I hope I'm going great. So if I am adding 1 to it, it will be greater than equal to 1. If I take its reciprocal, we know it will be until infinity only. So it will also reach till infinity only. It will also reach till infinity only. So if I take its reciprocal, I'll say 1 upon 1 plus x to the power 2025 will be greater than equal to 1 upon 1, but it will be less than equal to, I'm really sorry, I think I'm making some error. I'm really sorry. I'm really sorry. I should have written it over there only because the sign has reversed. So 1 upon 1 will be 1, which I'm writing here, and 1 upon infinity will be 0. So this expression will lie between 0 and 1. So if I'm having an expression which is lying between 0 and 1, and if I'm subtracting it from 1, so that will also lie between 0 and 1. Are you getting this? If still you are not able to get it, let me put a negative sign on all the three sides. So this will become 0, -1, -1. But if you are multiplying all the sides by a negative sign, the sign changes. So the sign now becomes this. Now, if I add 1 to all the three sides, if I'm adding 1 to all the three sides, it will become 1, which is greater than equal to 1 minus 1 upon 1 plus x to the power 2025, which is less than equal to 1 minus 1, which is 0. So I hope this is gx. So we have predicted that gx is now lying between 0 and, I'm really sorry, I should not use the equality sign here before 0, right? So this is less than 0. So if this is 0, I should not put a 0 equal 0 here. So that should be removed from here as well. So it is 0 and less than 1. So gx also has a range between 0 to 1. Did you get that part? So gx has this range set b, and set b is basically between 0 and 1, and which should be included? I think 1 should be included, 0 should be excluded. So b is a set between 0 and 1, and that's what you're supposed to take. Now, the third part of this question, which said there is a set S where you are supposed to take only integral values of x such that x belongs to A or x belongs to B. A or B means union. So are you seeing a question on functions which use the concepts of sets and operations on sets? So questions on sets may not be asked directly, but this is how they will keep playing with your brain. So yeah, if I could do it, how will I do it? X should be an integer which is a part of either A or B. So in set A, I have integers from 7 to 35. In set A, I have integers from 7 to 35. So how many integers are there? I'll say 35 minus 7 plus 1. This is how you calculate the integral values, if both of them were supposed to be included. So set A, if I could calculate the number of elements in set A, where A, I'm considering only integral values. So that will be 35 minus 6. 35 minus 6 is going to be 29. So number of elements in set A will be 29, integral elements 29. And in set B, the number of integral elements are only 1. So that's 1. The number of elements in set B, if I'm taking only integral values, that is 1. I hope nothing is common between set A and set B, because set B is from 0 to 1, set A is from 7 to 35. So when I take union, I need not bother about the common values because they are two distinct sets, two disjoint sets. In that case, I'll say my answer will be 29 elements from set A, 1 element from set B. 29 plus 1 gives you the answer 30. Did you get this part? Were you able to understand it? I hope no confusion is there and you have understood it completely. Let us move ahead towards the next question. What does it say? This is something which I am asking you to do. I'll just give you the hint. I'll not solve it completely. This is that bonus or homework question for you. So yes, what am I expecting now? I'm expecting that you will be writing your response in the comment box and I'll be checking your answers. And I'll love to see your comment or responses, and that will help me in understanding whether you have watched this video so far or not. So let's see this question. What does it say? A has certain elements. I'll give you a complete clarity. I mean, I'll do a lot of things for you, but I'll not solve it completely, because I'm hoping that after teaching you this much, you should be able to crack it. So 1, 2, 3, 4 are the part of set A, and 1, 4, 9, 6, 9, 16 should be part of set B. And of course, once you have done this question, do write your answer in the comment box, and there I'll tell you which option was the correct answer to this particular question. And of course, there I'll be more happy seeing a lot of comments pouring in. Now here, what do we have? Set A, set B, these are the elements. Number of many one functions such that f a to b, that 1 is always an element of f of a. So first of all, 1 should always be an element of f of a. That's the constraint. Okay. What are we asked? Many one. So first of all, we can calculate total number of functions. So I hope we have a formula. I'll not tell you again. You know how to calculate total number of functions. Out of total number of functions, if I could tell you how many 1-1 mappings are there, so you can calculate total number of 1-1 functions. That also you can do. So total number of 1-1 functions can also be calculated. So out of total number of functions, if I could remove total number of one functions, I'll be left with many one functions. Now, what I'll get is, after this, from if I subtract this, I'll get total number of many one functions. But that's not my answer. That's not going to be my answer, because there is a catch. JEE loves making you fall into traps. Now, what is that trap? The trap is that out of these many functions, let us remove those many one functions which does not include one. This is the hint. Think, how will you do it? This may look like a question on sets, relations, and more specifically functions mapping, but this is a question on PNC, permutation and combination. And if you're good at PNC, you would love to solve this question. I have given you the hint. I'll repeat the hint. The hint is, you will get the total number of many one functions by this calculation, which you have been taught previously. Out of all of these total number of many one mappings, many one functions, remove those functions which are many one and which do not have one in its range. If you could calculate those, which is very easy to figure out of those total, if that number of many one mappings are removed, which does not include one, then you will be left with the mappings which include one, and that will be the answer. So first of all, calculate this and then this, then take the difference, it will give this. From this, subtract this, which does not include one, and then you'll get the final answer. I have given you the hint, and I'm hoping and expecting that you will do it by yourself. And that's why I'm emphasizing that you need not remember any formula, especially based on mappings. You should understand the logic. And if you have gotten the logic, you can crack such questions with a lot of ease. Let us move ahead. Let us move further towards the next part of our video. There we discuss, when do you call two functions to be identical or equal? Two functions are said to be identical or equal in three cases, if these three conditions are fulfilled. The domains should be equal of both of the functions. The range of both of the functions should be equal, and they should carry the same value for each of the value lying in the domain. I'll take an example and make you understand it more clearly. For example, here, ln of x square and 2 ln x are not same. They are not identical function. They may be true as per the property, but they are not same. Not even through the property they are same. Because ln of x square, some people may be willing to write 2 ln x, but that's false. It is actually written as 2 times ln of mod x. Because x square could have been positive or non-negative, but here, to make it or to keep it non-negative, I should put a mod over here. And that helps you in understanding the domain as well. So here the domain is different, here the domain is different. The domain of this fx will be, the domain of fx will be all the real numbers excluding 0. Because apart from 0, any number you put here, that square will give you a positive value. But here, the domain of g of x will be all the positive numbers only. Because you cannot put negative numbers or 0 here. So did you see that there is a difference between their domains? So there is no point in seeing or delving or checking it further. And the next function, cosec x and 1 upon sin x, they are same in terms of domain, range, and the values. So they are identical. Did you understand it? Moving ahead, composite functions. Now, what do I mean by composite functions? So that's again a different concept, a totally great concept. Let's start discussing this concept in a more detailed format. And how do we learn it? Let's look at that. I'll explain it with a very simple example. Let's say there we have a function. Let's say we have a function something like this. Let's say we have a function something like this, sin x square. Now, basically, this is a composition of two functions. Let's say there are two different standard functions. One of the function is sin x and other function is, let's say, x square. So what if I were to ask you to define f of g of x? What will you say? You will say, sir, f of x is taking g of x as an input. So what is f of x? It is sin x. But instead of x, I'm supposed to write g of x. Are you getting it? And what is g of x? G of x is x square. And that's where I'll be writing it as sin x square. It is not sin square x or sin x whole square. It is sin x square. I hope you're getting it. Similarly, had I asked you g of f of x, what will you say? You will say, sir, in that case, g of f of x, g is taking f of x as an input. What is g of x? G of x is x square. So g of x is x square. So if I'm asking g of f of x, it should be square of f of x. What is f of x? Sir, f of x is sin x. So it should be sin x whole square. So I hope you are seeing the difference. So composite function, I hope it's very well understood by you all, and you must have seen this result as well, that f of g of x and g of f of x are not equal. Now let's talk about some standard properties based on composite functions. First, of course, we know that g of f exists if the range of f is subset of domain of g. Because please understand, let's say I'm stating g of f of x. Now what you need to understand that f of x could have a range, and let's say that range is going beyond the domain of g. So f of x is generating something which g of x cannot accept as an input. So of course g of f of x won't exist. So we need to understand that whatever is the output of f should be smaller than the input of g. Then only g will be able to take, accept or digest it. Are you understanding my language? Now, similarly, for fog also they have given you condition. Composite of functions is not commutative. As we have already seen, this is something you already understood. Composite of functions is associative. What does it mean? It means that either I take f of h, or this is something wrong, I think. Let's say, yes, forget this. There it should have had g basically. So if I take f of g of h or f of g of h, now what I'm trying to make you understand is, let's say I take g of h first and then I take f of g of h. Or if I could take f of g first and then I could take it of h, then it could have been commutative, which means associative, not commutative, which means you take three functions, you perform this operation, and either you do this or this, you will get the same result. That's the second property. Composite of two bijections is a bijection. Please remember, what is bijection? Surjection plus injection. So if a function is 1, 1 on 2, which means the function is invertible, then you will take its composite and then also you'll have a bijective function. Always remember that. Now, moving towards the other part, the second part will be, yes, this. Composition of even and odd functions. So questions are asked on it. I'll simply give you the simple example. If f and g both are even, f of g of x will be even. But if the f is odd and g is odd, so f of g of x will be odd. Third case, if f is even, g is odd, then f of g of x will be even. And if f is odd and g is even, in that case, f of g will be even. Instead of proving them right now, I'll straight away give you that you can put the conditions and you can check it by yourself. So take two examples where one of the functions is even, other is odd, and you can check it by yourself. Even in the examination hall, rather than remembering it like this, you can take two cases, take the composition of even and odd function, and you can draw your own results. And on the basis of that, you can conclude. Even if you forget these possibilities, because it is very confusing. Of course, you cannot remember them very clearly. It is very confusing. Now, moving ahead towards the next case, there we discuss a question and it will give you a better clarity about composition of functions. What is it? Let's have a look at that. 2025 has asked it that f of x and g of x are two functions. Then they're asking you domain of f of g of x. All right. As we have discussed, if f of g of x needs to be defined, then the range of g of x should be the subset of domain of f of x, because whatever output g of x is producing, that output is treated as an input by f of x. I hope you're understanding f of g of x. So there we need to ensure that whatever is the output, I hope you're understanding what is f of g of x. So it is going to be log of this. If you're understanding, you're able to understand. So when you are saying f of g of x is going to be basically log of g of x. So I can very easily conclude that if you are taking log of something, that something should always be positive. So the catch here is that this should be positive, and that will help me in deciding its domain, right? So I'll give you the hint here that this x to the power 4 minus 2x cube plus 3x square minus 2x plus 2 whole divided by 2x square minus 2x plus 1 should be positive. I hope you're understanding it. Two things I need to take care of. First of all, let me look at the denominator, because for whatever value of x, if the denominator is becoming 0, I need to exclude those values as well. So let me take care of the denominator. This expression 2x square minus 2x plus 1, right? Can you help me with its discriminant first of all? Its discriminant is going to be b square minus 2 square is 4 minus 4ac. So 4 into 2 is 8, which is negative. So its discriminant is negative. If its discriminant is negative, which means this denominator is always positive. This is positive. for all the real values of x. Did you get that part? Which means if I want this something upon something to be positive, where this denominator is always positive, which means this numerator should be positive, which means the numerator x to the power 4 minus 2x cube plus 3x square minus 2x plus 2, this should always remain positive. Did you get this part? Now I need to ensure or find the values of x for which this expression is positive. Did you get this part? Now I'll say this very simple result that look at the options. Why can't you seek help from the options? Why? Because option D says all the real numbers, which means for any value of x, this will be positive. I could check it with any values. For example, any value try and put here and check it with. But before you try, the three options are saying 0 to infinity, 1 to infinity, 0 to infinity. So let us check it with any negative value. That's the hint. That is the part I'm leaving you with. So from here, instead of solving this inequality, which you cannot directly at this stage, because factorization would be really difficult at this stage because it is a biquadratic, why can't you seek some help from the options? So option D can be selected or discarded if any negative value satisfies it. So I'll check it with a negative value. And if any negative value satisfies it, then this don't include a negative value at all, which will help me in understanding if any negative value satisfies it, that means this should be an acceptable option, and that will discard these possibilities. Let's say if a negative value does not satisfy it, that means option D cannot be the answer. Now I will choose a value between 0 and 1. I hope you are seeing the difference. Let us decide whether 0 can be included or not. So I'll check it for 0. So if I check it for 0, 0, 0, 0, 0, 2 is greater than 0? Yes. So 0 is acceptable. So 0 is excluded in option C. So I think option D and option C can be excluded on the basis of that. Now I'm left with two choices between B and A. Can you help me with B and A? Are you not seeing? With 0, I have reached to the conclusion that option B cannot be my answer because 0 is satisfying that. So I'm left with two choices, D and A. D you can check with the negative value, A you have already checked with. So once you check it with the negative value, you will reach to the conclusion. I'll do it for you so that you don't say that I didn't do it. Let's do it at this stage. I'm not leaving it up to you. I am doing it. Because minus 1 is a very small value, very simple value. Minus 1 to the power 4 will be 1. This will be plus 2. I hope you can see it. This will be plus 3. I hope you can see it. This will be plus 2 and this will be plus 2. Even if I'm not calculating it, 1 plus 2 plus 3 plus 2 plus 2, it is going to be positive. I need not even say this. So that basis, on the basis of that, I am seeing that it is satisfied by negative values as well. So why should I even worry about these options? Option D would be my correct answer. So I need not even think of option A and C, A, B and C. Did you understand the whole process? Let us move to the next question. Inverse function. What is an inverse function? We have discussed inverse trigonometric functions. There we had a great discussion on bijection, invertibility, which means if a function is 1, 1 onto, its inverse can be found. So if its inverse can be found, let us directly discuss its property, because inverse, I think we have had a discussion while discussing sine inverse x. Do you remember that? Now, the inverse of a bijection is also a bijection, of course. You find the inverse of a bijective function only. So it is going to be bijective only, because whenever the function is 1, 1 onto, then only you can find its inverse. So if its inverse is found, it will also be 1, 1 onto, which means the inverse of a bijection is going to be a bijection only. Will you remember that? I hope that is understandable. If f and g are two bijections, f a to b, g b to c, then the inverse of g of f exists, and g of f inverse will be f inverse of g inverse. Remember this. This is a very important property. I repeat, what I am trying to make you understand is that g of f of x, let's say I need to take the inverse of this. So inverse of this basically changes the order. So you can write it as f inverse of g inverse of x. Remember this. This is true for three composition as well, a composition of three functions as well. All you need to ensure is that they should be bijections. F and G both should be bijective functions. Then only you can apply this, because then only you can find the inverse of a function. Let's look at the other important results. Trust me, this is that second most important chunk which JEE loves on asking. What is it? Let's learn it. These are called functional definitions. So whenever your question says that there is a function which satisfies f of xy is equals to f of x plus f of y, don't hesitate in taking f of x as k times ln x or f of x as 0. They'll give you a possibility in that question only to eliminate either this or this. So of course, whenever you see f of xy is equal to f of x plus f of y, f of x will be either this or this. Remember this. If the question says that f of x is equal to f of x into f of y, then you can take f of x as x to the power n, where n should be any real number. Third case, if f of x plus y is given as f of x into f of y, that is true for exponential functions a to the power kx. So these are the general results which I'm strongly urging and asking you to remember. Take a screenshot of this slide. This will be the most important slide from this particular chapter, the second most important part of this particular chapter, right? Let us move ahead towards the next part. This is also a very important part. Take a screenshot of this part as well. Next definition, f of x plus y, if it is given as f of x is equal to f of y, then will not hesitate in saying that it is a constant function. Then only it is possible. I hope you are realizing it. If f of x takes rational values for all x, then f of x is a constant value function. These are the general results which I'm asking you to remember. And let's solve a question based on functional equations asked by JEE Mains in 2025. It said f is a function such that f of x plus 3 times f of 24 by x is 4x. And then they are asking you f of 3 and f of 8. 3 and 8. Can you help me with the LCM of 3 and 8? 24. I'm given 24 here. So let us work on 3 and 8 only. How? This is the relation. So in this relation, let me replace x by 3 once. So if I'm replacing x by 3 here, what do I get? Let me replace x by 3 here. So it will become f of 3 plus 3 times f of 24 by 3 is 8 is equal to 3 into 4, which is 12. Any confusions on that? I hope it is understandable. I hope there is no doubt on it. Now, next result. I am replacing x by 8 here because 8 can divide 24. So it will be f of 8 plus 3 times f of 24 by 8 is 3 is equal to 8 into 4, 32. I hope you understood it. They will give you the data in such a manner that you can find it. So you need to use your intuition, and by using that, you can work out such results very quickly. Now what I need to do is f of 3 plus f of 8. Are you seeing a relation? If I add both of these equations, I'll have f of 3 plus 3 f of 3, which is 4 times f of 3 plus f of 8 plus 3 times f of 8, which is 4 times f of 8. So this is how, by some adjustments, you can do it. 32 plus 12 is going to be 44, I think. Yes, it is going to be 44. So with that, if I take 4 common, I'll be left with f of 3 plus f of 8, which is 44 upon 4, which is going to be 11. Option, I think there is something wrong. Let's say option B is 14, so option A will be the correct answer. Did you get this part? How easy this question was. Only tricky part was that you should be able to crack how to attain f of 3 and f of 8. And if you are able to look at the pattern here, you can crack it. So such simple questions are also asked by JEE Mains only. Now, let us understand the final part of this particular video, graphical transformation. I'll make you understand through graphs only. For example, this part here. Let's say you have a function f of x, whose graph goes like this. And to f of x, let's say I'm adding a constant value. So the graph will be shifted a units above. And if I'm subtracting a constant value from it, then the graph will be shifted a units below along with y-axis. First transformation, I hope understandable. Let's move towards the next part. The next part is, let's say, from x, if I'm subtracting something, and from x to x, if I'm adding something. So let's say this is your f of x. This is the graph of f of x. If I subtract a constant value from it, then you shift this graph a unit on the right hand side along the x-axis. And if you are adding a constant value to x, then you shift this graph a units on the left hand side. I hope it's understandable. Next conclusion. If I'm multiplying f of x by a, so of course, always remember that only thing happens is that it gets stretched a times if a is greater than 1, and if a is between 0 and 1, it gets compressed. So let's say if this was the graph of f of x. So if I'm multiplying it by a, which is greater than 1, so of course its range will get expanded because it will get stretched because it is multiplied by a certain value. And even during that also, it will touch the x-axis or intersect the x-axis at the same points. I hope you're understanding why. Because they are the roots of f of x. But if a is greater than 1 and you're dividing f of x by a, which means you're dividing it, you're compressing it. Previously you multiplied it, so it got stretched. Now you are dividing it, so it is getting compressed. So when it gets compressed, the range will become lower. The value, the highest value and the minimum value will get compressed. But still, the graph still will touch or intersect the x-axis at the same points. Because at the same points, 1 by a f of x will become 0 at the same values of x. I hope you are seeing and understanding or observing it through this part clearly. This time, when you multiply x by a, previously I multiplied f of x by a. This time I'm multiplying x by a. So when you do that, this time please understand, you shrink the graph a times along with the x-axis. Here, if you didn't get this part, I'll try and make you understand with an example. Let's say you are given graph of sine x and you are asked to write the graph of sine 2x. Now how do we do it? I'll tell you, draw the graph of sine x only. How do you draw the graph of sine x? How do you draw the graph of sine x? This is the graph of sine x. But now just point out these values. On the y-axis, nothing changes. It is -1 and it is 1 only. Don't worry about this. This was 0, so you put 0 here, you get sine 0, 0. This previously used to be pi by 2. I'm really sorry. This used to be pi by 2. But how will I get pi by 2? So put 2x is equal to pi by 2. In that case, what does x give you? X gives you pi by 4. So previously, if it was pi by 2, this time it will be pi by 4. So this, of course, is going to be now pi by 2. This will be 3 pi by 4 and so on. So the graph has been, I hope you can see, is basically, I hope you can see it very clearly. If a was greater than 1, it will be shrunk. I hope you are able to digest this part. And more importantly, are you understanding it that this is how you can plot it? Curvature will remain same, but only difference is going to be the points. The location of points will come into picture. The same holds true for the value. When you divide the x by something, then of course the graph gets stretched. The same logic can be applied here as well. If you are asked to take the value or the graph of minus of f of x, do nothing but simply take its mirror image with respect to the x-axis. Let's say this here is the graph of f of x. I repeat, this over here is the graph of f of x. This is the graph of f of x. So treat x-axis as a mirror and take its mirror image. So this will be the graph of minus f of x. I hope this part makes complete sense. Moving ahead towards the next part, what do we have here? Mod of f of x. That's the most interesting part. How? I'll just give you the final conclusion. How do we do it instead of telling you the theory? Let's say this is the graph of f of x. This here is the graph of f of x. When you put a mod over f of x, the only thing you do is whichever part of f of x which is lying below the x-axis, take its mirror image in the x-axis. And that will be the graph of mod of f of x, which means don't touch the part of the graph which was already above the x-axis. The part of the graph which was lying below the x-axis, take the mirror image of it. And that's how you can draw the graph of mod of f of x. Now, here, the graph of f of mod of x, how do you draw it? So the graph of f of mod of x is also very simple. Let's say this is the graph of f of x. This is the graph of f of x. Now what I do next is, I'll do very simple task that here, whatever part of this graph which was lying on the negative side of x-axis, I'll remove that part. And whatever part of this graph which was lying on the positive side of x-axis, I'll take its mirror image in the y-axis. I hope you're understanding it very clearly. And that will give you the graph of f of mod of x. Did you understand it completely? Are you able to make sense out of it? Now, let us move to the next part here. Mod of f of mod of x. So what do we do here in this case? It is even simpler. First of all, how do we draw the mod of f of x? We remove the part of f of x which was lying below the x-axis and we take the image of it on the above x-axis. Now, what I'm supposed to do, I need to draw f of mod x now. I hope you're understanding it. So what I'll do is, I'll remove the part of the curve which is lying on the negative side of x-axis and I'll take the mirror image of the curve of the positive side of x-axis, and through that I'll be able to generate the result. I hope you are getting it very clearly. So I think it is giving you a complete sense, a complete clarity. Next is, if mod y is equals to fx is needed to be drawn. How do we do it? This is even simpler. I'll just simply give you the complete result instead of telling you all these points. These points will be provided to you during our short notes. Don't worry about it. Let's say this is the graph of f of x. This is the graph of f of x. All you need to do is just take the part of this graph, which is above the x-axis. This is the part. And take the mirror image of that part in the x-axis. take the mirror image of that part in the x-axis. That will be the graph of mod of y is equal to f of x. Did you understand this part? So I hope everything is very well understood by you all, whether it was function, its range, its domain, periodicity, odd even, many one, onto, into, functional definitions, graphical transformations, along with sets and relations. So I hope a great clarity is provided to you in this one single one shot. I hope you know that Elevate JEE Crash Course is a program which we have started at absolutely free of cost, at absolutely no cost, in which we are providing you these one-shot videos of every single chapter from physics, chemistry, and maths for your JEE preparation. And of course, along with these videos, we are providing you these short notes, these handwritten notes at absolutely no cost. And the DPPs as well, the practice sheets, the material in the real test environment format, which you can access on our PW app. The link to the app is already given in the description. It will redirect you to the course only. Of course, you remember that PW is that amazing platform from where millions of students are already preparing for different competitive exams. With that, let's call it a day here. Thank you so much. You have been a great audience.